Like one is the doping of alkali elements or cation substitution or allying with lithium or germanium or the interface modification. So people are looking at different ways to overcome this VOC deficit, but uh, they have not been much successful in this approaches. So if you see like IBM has proposed in 2012, so where they try to introduce germanium, which is they say one of the most possible suitable interesting group 4 element, which is added to the casterite. So what have the efficiency has improved from only 9.07 to 9.14, whereas with the 40% of germanium incorporated. But the VSE has not changed much, so this was not very successful. So they suggested like VOC increase related mainly to the band gap increase. There's another work in AIST Japan. They have tried to incorporate germanium. Yeah, so the highest efficiency what they have achieved is around 12.3, but open circuit voltage has improved to 530 volt, 0.53 volt. In another work in 2018, again they have tried to incorporate different germanium like 0.05, 10, 25. Have tried to introduce the thickness of germanium layer in between that. So still like VC deficit is still there, but they have achieved efficiency of 11.8. So not much success has been done in this case also. So we have also like in our work we have also tried to incorporate germanium in one of our work. So what we have done like uh, we have incorporated germanium at two places. Like we started with the glass, then the back content, then we have put germanium. Generally our target was to around 30 nanometer, but now what we have found is around 28 nanometer. And then we have deposited the copper tin in this sequence. And then in another case, after moly, we have deposited copper tin, and then after that, we have deposited germanium, and then the other layer. So in the XRD, you can see like you get a better. We'll try to explain like if this is there is certain shift into this. So what it says like for germanium 1 and 2, like where we have in the at the back contact and in the middle, there is enhancement in crystallinity as with no germanium. Means germanium is helping in the growth of the crystal, which has been shown by the earlier also. So it was observed that the germanium dot films G1 and the band gap increases by around 5% as compared to there is no germanium. This we have recently published. Then people also try to put the silver. So with the silver, what they have said like optimum substitution silver reduces the copper to zinc related defects, but there is not much improvement in the VOC. You can say it's around only 11.7%. This work was recently published by, and then like one of the method is to deal with the alkali metals. Again, there was not much improvement in this. It's only 479 VOC deficit is still there. People have tried another try to align with the potassium. This is also not helped much. Yeah, I'm not going to detail of that because they have tried to have different thickness of potassium, right? So if you see like I have collected like data from the different literature. So like, people have tried to dope with lithium, sodium, potassium, rubidium, cesium, indium, germanium to enhance, but you can see like VOC deficit there. Not much improvement in the VOC, and the efficiency are still limited to around 10 to 12%. Now, for the when they are trying to include the extrinsic allying elements like silver, they are trying to replace some of the copper by silver and some of the uh, sulfur by selenium. So this is, and some people have used magnesium, some people have used cadmium, some people have used germanium and the magnesium. But you can see like even here the band gap has increased to 1.38. The VOC has increased to 650, but I think the current has gone very low, so the efficiency is still around 11.5 only. So still not much improvement is there. So still people are below 12%. So related to we have also tried this our work. We have also tried to do like how the annealing or annealing time can affect this to get the avoid the secondary phases present in this. So what we have done, like we have deposited on the glass, we have deposited moly, and after that sequentially we have deposited other matter to form the copper zinc tin selenide material. So in this case, what happens, like initially we have annealed 230 for 10 minutes and then 450 for different timing, 5 minute, 10 minute, 15, 20, 25, 30 minutes, just see like which time is much better than, which is give a better result in this case. So XRD, we don't get too much, like if you have MCs, you have a better facility. So what we try to deconvolute the curve. Okay, so even till M5, which has been annealed for 25 minutes, we still see some secondary phases are there. But in M6, which is annealed for 30 minutes, we find there is no secondary phases. So maybe if you are annealing at 450, 30 minutes is more suitable. If you are going again increasing in temperature, you may again you have to optimize like how much time you need to for this annealing. So the device, we have also fabricated a device out of this, but we are only reached to around 4%. Still, VOC is too low in this case. So we have not done any analysis like why VOC is so low in this case. So during the pandemic, we have also started the work, some work on the simulation work. So we have also proposed a tandem structure here, like to capture more of the solar spectrum. We have proposed a tandem structure, like you can start with the CJTs, which is a lower band gap, and then pure sulfide, which is a higher band gap, and then you make a junction and the other format. And we have also proposed, like because you are annealing at a very high temperature, so there may be certain intermixing, or you can your stoichiometry can be disturbed. So we have tried to introduce a insulating layer in between that, so there is no interdiffusion between these two to avoid this interdiffusion. And this has been recently published in Solar Energy. So it has shown like if you don't have any interfacial layer, the efficiency is around 15.71. But if you increase this, if you give a intrinsic layer, then efficiency has improved 20. So major improvement is in the fill factor. So we conclude like there may be certain changes in the shunt on series resistance which may be better. So recently, like if you see the technology mission division of DST, they have also come up with the different project proposals. So in that case also they have given a target, like somebody is proposing like tandem bilayer castride based solar efficiency more than 80%. But I don't think it is feasible. Like even theoretically, it has been shown like it may go to 20 or 21%. But what the target they have given, I think is very difficult to achieve even on the small scale. So I will come to end to this my slides. So what we say, like stride materials is a new emerging technology. A lot of work has been done, but still long way to go, because a lot of material properties has to be studied so that the efficiency can be increased for this. Because last 7 years there is no improvement in the efficiency for this. Otherwise, within 1 or 2 years, people will forget this stride. So I thank DSTSRB for the financial support and all my research scholars who are doing the work. Thank you.
Thank you, Professor Singh. It's very timely you have completed. So we have time for a couple of questions if
Yeah, sure.
anybody asks. Yeah, very timely.
Yeah, Professor Dalvi, can I ask?
Yes, sir. Please, please. Professor Bhattacharya.
Sir, at the end you just talked about intermixing.
Inter?
Intermixing
Yes.
of the layers.
Yeah,
When
yeah.
you are depositing layer by layer and then heating it to a very high temperature,
Yes.
then I feel that it is obvious to expect that the layers will be intermix.
No, because when you deposit this absorber, after absorber you anneal it. Because after that you deposit CDS and this. You are not annealing at this point. Only at the absorber layer you anneal to make the compound. So if you are having a bilayer, then there is a possibility of interdiffusion. So what we have proposed, like to avoid this interdiffusion, if you put a thin layer of insulating layer, which will not hamper the current. So there
Yes.
may be chances that there will not be any interdiffusion between this, and you have an intact band gap of 1.5 and 0.9 or 1 electron volt. That's our proposal. We have not done any experiment till date. We are trying to do that so that we can.
Will it not introduce more series resistance into the system?
More series resistance, I don't know. Like unless we do some experiments, then only we can tell.
Okay.
What is the typical thickness of these layers? That will also decide what is the.
Yeah, because the absorber layer is mostly around 2 to 3 micron, and then cadmium sulfide is only 30 to 50 nanometer, and then the top layer is around 300 nanometer.
Okay. Thank you. Thank you.
Is there any other question? So I have a simple question. I mean, for university researchers and at undergraduate level also, for learning purpose, let's say this polymer-based solar cells can also, of course, the efficiency may not be very high because of these, but then can you comment on, because I understand that the preparation synthesis process will be simple for for laboratory-based experiments on polymer dye-synthesized solar cells.
No, people are working on dye-sensitized solar cells at the lab scale. So lab scale, you can get a good result, but stability is a big problem with the dye-sensitized.
Yeah.
So if you measure today, maybe after 1 week, it may die. I think Dr. Bhaskar can comment more on that.
One company has started selling now the dye-sensitized solar cells. They are selling that for indoor applications, diffused light absorbing system. It is stable.
Yeah, but they are giving a warranty for, let's say, for 4 or 5 years, so that you can replace. Cost is low, but not like this silicon or the CIGS solar cells, where they can give the warranty till, or cadmium toluene where they give warranty for 20 years.
And the efficiency is also low.
Yeah.
I think we can stop here and we can thank Professor Singh for such a nice and elaborative presentation. Thank you very much, sir. And you can remove your slides now.
Okay.
For the next talk.
Professor Dalvi, there is a minor change. I just.
Acha.
No, sir. I am available, sir.
Oh, you are available. Oh, great.
Yeah.
Great. Then it is fine. Let us go ahead.
Professor S.P. Pandey or.
Yes.
Yes, he's there. Yes. All right. So the next talk is by Professor S.P. Pandey and Tirthankar Mahavir, Muradabad University, UP. And I can brief about him before he starts his presentation. Dr. Sri Prakash Pandey obtained his PhD in 2001 from Banaras Hindu University. And during his PhD, his area of research interest was swift ion irradiation effects on electronic devices such as metal semiconductor devices and silicon solar cells. Dr. Pandey has postdoctoral experience from National Taiwan University, NTU, and there he got expertise in the area of crystalline and polycrystalline silicon solar cells. Dr. Pandey has a vast teaching experience of more than 20 years at UG and PG levels at science and engineering for the science and engineering department students. And he has also worked as visiting professor at Kano University of Science and Technology, KUST, in the Nigeria. He has published several research papers of national and international repute. Dr. Pandey has completed 3 DST projects, sponsored projects, on the development of solar cells and related materials. And he has participated and presented papers in several national and international conferences. Dr. Pandey is a potential reviewer of national and international journals. And he is working currently as a professor in the Department of Physics at Tirthankar Mahavir University of Moradabad, Uttar Pradesh. And he will be talking on solar cell technology optimization of processing parameters of crystalline silicon solar cells. Floor is yours, Professor Pandey. Please go ahead.
Thank you, sir. Thank you, Professor Dolby. I am very much thankful to organizers, especially Professor Neelam Srivastava and Professor Bhaskar Bhattacharya. Actually, I belong to that group where I learned a lot from these two people, Bhattacharya and Neelam Srivastava. And the previous speaker, Professor U.P. Singh, and the coming professor, Professor Kamlesh Pandey, all are related to me, and I started my research career with in their presence, and they have guided me a lot to come up in this shape. I am very much thankful for giving me opportunity to deliver my talk in the conference, International Conference on Energy Materials and Devices. Okay, as you see on the slide, my topic is solar cell technology, optimization of processing parameter of crystalline silicon solar cell. This because energy is more required, and however, we can see here the conventional sources of energy such as fossil fuels, oils, they have limited in nature. So some alternative is required, and on the basis of that alternative, solar energy is a very efficient and effective source of energy we can grab from the sun. Now come to our topic. First, we have to discuss about what is solar cell. Solar cell, that is a simple device based on semiconducting material, and that can harvest the sun radiation and convert into electrical energy. So if we see the solar cell work on the principle of photovoltaic effect, because this device takes the photon energy from the sun and supplies the voltage and current to resistive load may be battery, motor, whatever. And solar cell, and that device can supply the DC power. It may be of different shape, different model. We can create solar model, solar panel to increase the more and more power from the sun. So the fundamental function of this device is photovoltaic, as I told you. In this case, when light falls on the surface of solar panel, the charge carriers are separated, and photo-generated carriers that that is arises due to absorption of light in semiconducting material. And the absorption of photons that separate the charge carrier, and that is converted into electricity. So how this solar cell works? Generally, solar cell is simple PN junction device in which there is two different kind of semiconductor material, P-type and N-type, and depletion region. It is very well-known process of formation of PN junction. And when junction is formed, then as soon as light incident on this surface of this junction device, then electron hole pairs are generated within the depletion region as well as near the diffusion length region. And in rest of the region, electron hole pairs generated, they recombine. So these electron hole pair generation that goes opposite direction according to their polarity, P-type and N-type. It means it will work like in the reverse bias, and reverse bias current is generated because of the minority carriers. These are the some structure, and this is the how the solar cell is fabricated.
Professor Pandey, sorry to interrupt you. Can you speak little closer to the mic? Because sometimes for some of the people you are not audible little bit. There is some mic issue, it seems.
Okay, I am increasing the volume.
Closer to the mic, it will be fine. Though you are audible to me, but then
Yes, it is fine now. It is fine.
I think the sound is.
Yeah, it is fine.
I have increased this. Okay, so photovoltaic effect, basically the light incident on the device and electron get excited, it depends upon the condition, what is the condition of energy of incident light. If energy of incident light is less than the band gap of the material, then it will not work. Electron hole pairs are not generated because it will incident light will be transparent for that device. And electron hole pairs are generated if the incident light energy is equal or a little bit greater than the band gap of the material, so that these photons are absorbed and electron hole pairs are generated. And if it is greater than, then some extra part of the light is lost in form of the heat. Then this electron hole pair generation takes place due to the absorption of photon at the junction as well as near the junction in the diffusion length region. This is a basic characteristic of solar cell or device. The total current that will be expected. This is the IL light current from this relation. Here V, RS and shunt resistance, that they will create little bit disturbance for the flow of carriers. So this part is neglected. Total current is little bit less than the whatever the photo current are generated because of these resistances. And ISC, it is a light induced current. This is the maximum current which is generated. And VOC, open circuit voltage, these voltage generated at the end of the device, end part of the device, because of the at the depletion region, due to this field, the carriers are repelled towards the front and rear side. So a voltage is generated because of the light incident on it. The characteristic in ideal characteristic of such diode that without, sorry, it is hidden here. And this curve represents the IV characteristic when it is illuminated with the sun radiation. Yes, you can see here from this diagram. This is ISC is the maximum current, and VOC, this is the animation. Okay. And from the cell characteristic, we can find the maximum output by considering the this IV curve, where the maximum power is achieved with the maximum voltage and maximum current, and a fill factor that defines the ratio of these two. Why we need solar cell? Solar cell, that is a kind of device that can harvest the sun radiation. Why we need this one? Because the sun has abundant sun is abundant source of energy, and the energy of the sun is in order of 10 power 24 joules in a year, and that is very high, and it is more than 1,000 times than our population consumptions. This solar cell also very much useful because it can harvest the energy from the sun, and the availability of sun, if I think in India, it is a very long period sun is shining, about 8 months in a year. So this energy is direct, and this is that energy does not impact on environment, so that solar cell device is very important to use and harvest the sun radiation to minimize the this conventional sources use. Generally, sun radiation, because this device is also useful to observe, because from the sun radiation we can see there are different kind of radiations: ultraviolet, visible, and infrared, and these radiation can be used to convert into electrical energy with the help of such device. If you see the radiation spectrum from the sun, then it contains IR, ultraviolet, and visible. So IR can also be converted into thermal part, because the infrared part is around 49%, and visible ultraviolet range is 51%. So it can be converted with the help of this device. The device is made from different type, based on semiconductor devices, solid, PN junction, MOS, and basically we are interested here to photovoltaic devices that is very, very useful to convert the sun radiation into electrical energy. So there are, if you see the progress of a silicon solar cell, it started from 1839 from Becquerel, when this Becquerel used to prepare a cell that light-dependent voltage is generated when two electrodes are immersed into an electrolyte. So, but it was very, very small photovoltaic effect it was observed. Then after around 40 years later, Fritz also used the selenium semiconductor and coated with a gold layer, and it was a photovoltaic effect observed. And it is a kind of a thin film device that time, but efficiency was very, very low. The present solar cell came, it starts from around 1941, based on the silicon solar cell. It was little bit better efficiency than the selenium based solar cell invented by Fritz. And finally, when diffusion process in silicon starts from Bell Laboratory, then the solar cell based on silicon material is come up into with better efficiency. It is around 6%. It was around 6%. And then after many progress has been done by different scientists, different researchers, by creating the junction between P and N type semiconducting material, and making the contact in different ways to increase the efficiency by taking the rear contacts and back contacts, and by maximum light absorption. To achieve maximum light absorption, the front surface was textured and it was made some different kind, so that whatever light comes on the surface, it will trap into the semiconducting surface. So progress of solar cell based on silicon, then silicon was very costly because the processing of silicon into a solar cell structure, it was very costly. It was bulky also, it was heavy. So in order to reduce the cost of the bulky silicon solar cell, people have tried to find the thin film solar cell. I think previous speaker, Professor UP Singh, has described thin film solar cell in detail. So by reduction of the cost, the thin film is a good alternate, but the efficiency was not so good in comparison to silicon solar cell. And it was classified as a second generation solar cell. Nowadays, people have tried in different way, that is to prepare the solar cell from some different material. Some materials are insulating material, and by synthesizing and modifying that material into a photovoltaic device, that is another kind of solar cell that is lying in the third generation solar cell. Because in third generation solar cell, people are not very much interested to create the junction type of structure or to create the field nearby the junction to separate the charge carrier, but it is a different kind of solar cell. Some advantage and disadvantage of every generation solar cell. For first generation solar cell, if you see, the advantage is it has very broad spectrum range, because the band gap of silicon is 1.12 electron volt. It can absorb maximum visible radiation. It has only disadvantage is high cost. High cost is because of the processing of silicon solar cell is very costly. Second generation solar cell, no doubt, because if we are talking about the thin film material, is very less material is used, so that material cost is reduced. But still, it has a problem of low efficiency. It has advantage of manufacturing cost. It has advantage of lower cost per watt. It is very much flexible because it is thin, it is lightweight, so it can be transported very easily. So, but efficiency is its disadvantage, because if we are talking about the thin film, the inherent defects due to lower quality of processing method, that efficiency goes down in comparison to first generation solar cell. Similarly, in third generation solar cell, it has also advantage, disadvantage. I'm not going to describe it, because I have other speakers have already described in detail. Because third generation solar cell, Professor Bhattacharya is expert of that area, and many speakers like Professor Gupta has also explained, and Dr. P.K. Singh, Pramod Kumar Singh has also explained about third generation solar cell. If you see the progress of efficiencies year by year, then Martin Green have shown this chart. Silicon based solar cell is still leading with high efficiency, even though many research is going on in thin film solar cell as third generation solar cell, like anti-synthesized solar cell and prescribed solar cell and different solar cells. Again, still now silicon is leading with efficiency. Now I would like to describe my work, what we have done. Actually, I did my silicon solar cell processing and fabrication process at National Taiwan University under the supervision of Professor C.W. Len, Chung-Wen Len. In this presentation, I would like to describe a little bit about the silicon technology, how the silicon is converted into a silicon wafer on which we can process different steps to fabricate the solar cell. Silicon technology. Silicon is a material which is the second kind of material available on Earth after oxygen. So availability of silicon is very much, and that silicon when semiconductor was discovered, the first material silicon was used as a photovoltaic device in Bell Laboratory. So silicon availability of silicon is also very large, and purification. Silicon is purified in different stages, and after purification, it is converted into a crystal form, and that crystal is grown in different specific orientation, cutting, polishing, and details we will discuss in this presentation. So silicon, this processing of this silicon sand, from sand to chip, or to device, it is a very long process and very costly process, but therefore its processing cost is very high. How can we convert? First of all, we can take the quartz. Quartz, it is a sand, and quartz is basically silicon dioxide. And as a basic ingredient, we can use, and this quartz is melted.
Sorry, sir, you have 5 more minutes just to.
Yes, 5 more minutes. Okay, my process is very long. So I would like to describe it. This is method of preparation of silicon chip. This is described here. First, it is melted. Sand is melted in the crucible, and it is a seed crystal is pulled very slowly, nearly about 1 millimeter in a day upward, and it is taken in form of an ingot. It is polished, grind, and finally it is made in form of a wafer here. And this wafer is used for different classification. The processing parameter, what I did in Taiwan National University. First, we take the wafer, it, then prepare the front surface by diffusing phosphorus. Then we can have, sorry. Then we can have anti-reflection coating deposition, then front contact. Finally, we take the back contact with a different material. We did boron, we did aluminum, we did stack of boron and aluminum for making the back contact. And finally here, our cell is ready for characterization to get the output. Generally, processing parameter, we have already described here. This is the layer, sun resistant, and final picture of the solar cell is here. It is shown. The front surface. It is this color, pink color, represents the emitter region or diffusion region for N-type, and the basic, the bulk of the material is P-type silicon, and back contact is taken rear bottom side. So wafer cleaning, we can use a solution of 12% NaOCl at room temperature, ultrasonically cleaned, and surface damage removal. We can use 8% of NaOH at 80 degrees centigrade, and finally wafer is arranged in this solution. And surface texturing, we use this IPA solution with NaOH. IPA is a very fast surface diffusion. So this solution diffuses at the surface, and this NaOH that creates the, because it depends upon the layered etching. Layered etching means, suppose if silicon having 100 orientation or 111 orientation, then NaOH is having different etching process for different layers. So we have used here 100 cut silicon substrate. So this NaOH can create the pyramidal structure at the surface. The pyramidal structure is essentially made for maximum light harvesting. So emitter junction for creating, we can use PuCl3 liquid with the in the presence of nitrogen bubble, and phosphorus is diffused into the silicon in a controlled way. And there are two methods. Either we can use spin coater. First, we put a drop of PuCl3 liquid and rotate it with very high speed. And this is the formation. This profile represents the depth profile of diffused phosphorus into the silicon. So generally, front surface, so many dangling bonds or unwanted defects are created during the phosphorus diffusion. So we can have to optimize it or to passivate those bonds. So we can have different passivation method. We can use silicon oxide as a passivator. We can use a silicon nitride using PECV method, and we can use stack also, silicon oxide and silicon nitride stack. That stack can also passivate the surface of emitter region. And the method, I have not done this one, but cyanide treatment has also been useful, done by Kobayashi. And he showed that the Kc and potassium cyanide is very good passivator for the silicon substrate. And from his result, it has been observed that the defects which are created, that has been reduced by cyanide passivation. So what I did, I have also used the similar pattern based on silicon oxide and silicon nitride stack, as well as we have used ITO as a passive. ITO. Yes, just I am reducing to minimize the surface recombinations. The passivators are used. The ITO, it has a very good conductivity, so there is no need of metal fingering at the surface. So ITO as a used as a connector as well as the passivator. So I'm not going. Yes, this is the very important processing parameter for better solar cell efficiency. I need just 2 to 3 minutes more. So back surface field is very, very important process, because at the back surface, if we have little bit doping, that minority carriers are combined at the end surfaces. So back field is very, very important, because at this here, this is the front part, if you see my cursor, and this is the back part. If back doping is very strong, it is heavily doped, then there is also a low-high junction. And that low-high junction can also create the field, and which can reflect back the minority carriers, so that open circuit voltage of the device can be enhanced. So we have also used this aluminum as well as boron separately, as well as boron and aluminum alloy for creating the back surface with different method, different route thermal, rapid thermal processes and conventional furnace process. And we observed that rapid thermal process is for better process to create the back surface field. Yes, what I told you. So we have seen here the screen printed back surface and a rapid thermal. Yes, we have taken the same diagram. If this back surface field is very much uniform, then we can get the better open circuit voltage or better cell efficiency. And sometimes the disturbing here at the back surface field diffuses randomly into the silicon substrate, then it can create the recombination centers, so that efficiency goes down. So this is boron doped, and this is boron and aluminum alloy we have used here. And on the basis of our result, we can so the standard aluminum screen printing VOC was quite good, but current was not. It was very, very small. So that efficiency, it is around. Efficiency was around 18%. But if you do boron and then aluminum screen printed, then VOC should not decrease, but efficiency is a little bit increased, because the current has been increased. And if you use the paste, then again we can get the better efficiency for our solar cell. Though this decrease in open circuit voltage, it is because of the disturbing doping profile at the back surface. If I in conclusion, what we observed that from our experiment, the emitter surface specification as compared with SiO2, SiN, and ITU, we can have the better open circuit voltage and better result with the help of ITU, because it is transparent, it is very high optical band gap, so, and it is also conducting. So we can have no need of metal finger to take the contact. In comparison of solar cell with aluminum, boron, Ly, BSF, we can have the better efficiency. Boron doping back surface helps to create the homogeneous BSF because the boron is liquid part. So, which is not good in aluminum, because there's some rappelling also taking place with the help of aluminum. Aluminum has the advantage over boron, P contact, but as the shortcoming of P plus layer, non-homogeneous and even the locally absent. So on the basis of result, we obtain less voltage because the aluminum boron paste BSF is may be of non-uniformity at BSF layer. So thank you. This is all my presentation.
Thank you, Pandey sir. But I think we'll not be able to take questions because we have one more session that will be delayed. So others who are interested can personally interact with Professor S.P. Pandey, and we can have some more inputs and interaction with him. So
Okay,
without any delay, please allow me to thank you very much, sir, Professor Pandey.
Okay, sir. Thank you. Thank you so much. Thank you.
So now you may please remove your slides so that other speaker.
Okay, sir. I'm moving.
Now I introduce Professor Kamlesh Pandey of University of Allahabad, and he will be speaking on synthesis and application of polymer nano diamond composites. Before he begins, let me introduce him. Professor Pandey is a scientist in National Center of Experimental Mineralogy and Petrology University in the University of Allahabad. Dr. Pandey has completed his PhD in 1995 from Department of Physics, BHU. Dr. Pandey has the expertise of polymer nanocomposite materials and high pressure, high temperature research particularly. He has 22 years of research experience in Walker type multi-level equipment, which is a unique instrumentation facility in India. Piston cylinder and hydrothermal high pressure equipment is his another expertise. Dr. Pandey has published more than 80 international papers in the journals of international and national reputes, and he has received various awards. Without any delay, let me call
Yes,
Professor Pandey.
sir, I am trying, but some problem with screen sharing.
I see. So, do we have someone to help him out?
Okay.
Nilamji, you are on mute, it seems. So, he is the presenter. Possibly there is some other issue. But is he there? Is Kamlesh Pandey sir there? Is logged out, it seems. Okay, if is the next speaker, Professor Rajan Josh, available here?
Yes. I'm here.
Very nice.
It's
So
me.
can we go with the next speaker, and we will come back to Professor Kamlesh Pandey a little later?
Okay.
Is it fine, sir? By that time, we can resolve separately that issue. All right. So thank you. So let us go with another speaker first. Very privileged to have with us Professor Rajan Josh. He is a senior professor in the University of Malaysia, Pahang, UMP, and is the associate editor-in-chief of the Springer Nature Journal, Material Circular Economy, and editor-in-chief of Current Science and Technology. He has served as a Dean of Research of UMP during 2016 to 19 and a member of various committees of the university and Ministry of Higher Education in Malaysia. He has investigated nanostructured perovskite ceramics for microwave and superconducting electronics during the doctoral research at the Council of Scientific and Industrial Research CSIR Trivandrum, India, and has received PhD degree in the 2002. He has contributed to science and engineering of diverse range of materials, including inorganic and organic semiconductors, polymers, metals, alloys, materials for molecular electronics, biomaterials, glasses, and glass ceramics. He has employed a scientist at Indira Gandhi IGCAR, this Indira Gandhi Center for Atomic Research, and then AIST Japan, Toyota Technological Institute Japan, and NUS Singapore before joining the UMP. He has more than 260 papers in journals of international repute and more than 13,000 citations, and he has a very high H index of 61, and he holds 25 patents. He has supervised 6 postdoctoral and 23 doctoral students and 10 master's researchers. Stanford University places him at a very high level and material scientist in the list of lifetime achievers 2021 in the world representing top 0.76%. And he is interested currently in the sustainable materials, textile, electronics, and circular economy, data science, renewable energy devices, and most of his researchers are on the structure and property correlationship in the materials and devices. So welcome, sir, Professor Rajan Josh. Welcome for this presentation.
Thank you.
Floor is yours, sir.
And Shuman, this has been a long reading for you. And I appreciate it. You had that patience to do so. Thank you very much. And my sincere thanks to Prof. Neelam Srivastava for finding me out from, from this part of the world and asked me to give a lecture based on my activities here. Thank you very much. Things that I'm going to share is on my activities during the past several years, and why past several years also I would be outlining. So we had a lot of lectures in the morning, section on supercapacitors or electrochemical capacitors, and we have seen that there are 4 types of what can be called a supercapacitor charge storage. One is electrochemical double layer where the ions are reversibly adsorbed. And the second is a surface redox reaction. We call it as redox pseudocapacitance. And the third type is intercalation pseudocapacitance, where in layered materials, some ions like lithium, sodium, potassium, it can go to the layer structure and give rise to a capacitance without necessarily reacting with the electron material. And one another very recent is growth pseudocapacitance, which we have again seen the inventor of this kind of capacitance this morning. But we had a recent analysis on this. Is it how simple is this supercapacitive charge storage mechanism? Is it simple like a simple ion absorption? In fact, it's not so. This is again, even if it is an ion absorption process, it's a complex process. The electrolyte ions are in the pores of the electrode material, even in the absence of an electric field. They are there. And the ions occupation there depends on the local charges of the surface material and so on. And the moment we apply a potential, then typically there occurs three processes like counter ion absorption. Counter ion is if we have in normal case we have both kind of ions, and the positive electrode should get the negative ions. That's counter ion absorption. Ion exchange between positive and negative, so that we get only one type of charges in one of the electrodes, and the fourth one is co-ion desorption. Sorry, third one is co-ion desorption. So each process will have a determinal role in the charge storage through pseudo-capacitive or electrochemical double layer charge storage mechanism. We will be seeing it shortly. And before going in details, let me tell you why I switched to renewable materials. In fact, during the past 2 decades, most of my work is on inorganic metal oxides, semiconductor metal oxides, chalcogenides, glasses, and so on. And we very lately we have synthesized different types of materials in different morphologies, like microcubes, nanowires, nanoflowers, for two typical applications. One is solar cell by means of third generation solar cell, like what the previous speakers have been introducing here, in terms of dye-sensitized solar cells and perovskite solar cells, and of course for the polymeric solar cells. And we were developing those materials. And it is in our laboratory we first realized banded type electron diffusion in nanomaterials by judiciously engineering the material properties. And in another development, we have developed a material system that's a composite nanowire, which can store energy, means charge, simultaneously with high energy density and power density. We achieved it using having two types of component in a single nanowire, one offering high energy storability and the other offering high power capability. So we have all these kind of exciting materials. And in our laboratory, it is we who have developed world's first nanoroad solar module in a perovskite solar cell architecture with efficiency 15%. And that received a gold medal for engineering excellence from INPEX in United States in 2016. And using these nanowires that can simultaneously store energy and power capability, we developed a battery supercapacitor hybrid system, and that received a gold medal and invention of the year from British Invention Show in 2015. With all these exciting discoveries and materials, we have approached several companies and detailing them. These materials are excellent, and these can do these kind of works. Of course, all of them appreciated us. We have published this work in high impact journals. They are well cited also, but none of these companies buy our materials. And that's where we started realizing our failures. What is wrong with us? And find that our materials, our approaches has two typical drawbacks that cannot be accommodated by industries. One is high cost, and all these materials we produce using exotic, highly expensive, rare materials, and industry cannot afford it. It's too expensive. Okay, and it doesn't provide any competitive advantage than the existing technology. And the next one is to process them is heavily carbon emissive. Most of these materials were developed through a polymeric processing. And if you want to have 1 ton of material, we probably have to burn another 4 tons of polymers that add a huge carbon load to the environment. And no company was ready to pay the carbon tax. So none of these companies, none of these materials are actually adopted by industries. And we realize our failures. It is high carbon load and highly expensive. That's where we went to renewable materials and looking into nature. And of course, we cannot use this edible material as industrial materials except for food processing. Otherwise, we need to look into wastes. So we have looked into waste of different types. Most of them are shown here in the slides. And among them, it is the palm kernel shell. The waste from palm kernel shell is the one we most developed. And of course, we have a reason for that because oil palm plantation is the largest agricultural sector in Malaysia. When this largest agricultural sector produces means oil palm plantation, when they produce 2.5 kilogram of crude palm oil, it creates 100 kilogram of biomass as waste. Among these, 5 to 6% is palm kernel shell, the hard central core inside it. Probably you can well imagine when you compare it with coconut shell. And the other one is empty fruit bunch. Okay, and all of them is good source of cellulose, good source of carbon, and we can synthesize a lot of industrial materials like carbon, cellulose, starch, kernel oil, and so on. But things are not that straightforward when we start doing it. And we primarily approach this work to develop a material for supercapacitors. So we went for this palm kernel shell. It is very hard, and we can get high quality carbon. And we carefully characterized it, looking into what are the elements present in it, and how much is the percentage of that, and what kind of structure is that, what kind of properties it offer. We find that the carbon that we can synthesize from palm kernel shell is graphitic oxide. So graphitic oxide is basically it is tiny nano graphitic domains. The details of that is given in this paper. Can refer that. So there are tiny graphitic domains, and since they are tiny, means their domain size is about 2 to 3 nanometer and layer width of about 1 or 2 layers width, means that that's small. And when we look into the crystal structure, it is not perfectly amorphous, it is semi-crystalline. Okay, so we can actually develop a lot of materials, useful materials, because it can be a good precursor for graphene. That's what we are working on currently. And develop this carbon processed in variety of ways like chemical activation, physical activation, and looking at its properties. What are the surface area, how much charge storage it can offer, and so on. The details are there. When we look into that one, we did a comprehensive study on this and find that this curve shows the energy density versus power density. You can see that the energy density of the palm kernel shell is something similar or inferior to the supercapacitor electrochemical capacitors available in the market. It's currently available. So its energy density is little or something like 8 watt-hour per kilogram, but its power density is something similar to what we can get from the commercial domain. And we find that probably the reason is high resistance offered by oxygen there. So we started searching for methods to purify this one, or when we look into that chemical structure, most of them, about 50% of this one, 46+% of this carbon contains oxygen. And oxygen is a well-known additive adder of electrical resistance in materials, in solid state materials. So we need to get this oxygen out. First we did is heat the oxygen out, anneal it. And when we did annealing and compared with the commercial activated carbon, the original means commercial activated carbon give us about 50 milliampere milliampere per gram in 1 ampere, 0.1 ampere per gram rating. And it has an electrical resistance of series, total resistance about 2.93, less than 3. Whereas ours is pumpkinal shell carbon. It is done in lithium half cell configuration using lithium hexaphosphate electrolytes. And this our pumpkinal shell carbon gives lesser capacitance and because of its higher resistance. When we annealed it, things have changed because most of this oxygen gone out and our capacitance has increased dramatically and resistance has gone down dramatically also. We have explored different types of ways to purify them physically, not chemically, because purifying them using chemically will create a lot of chemical waste. Even purification will need a lot of water, and we will use up make a lot of wastewater reserve in our laboratory or in our university campus. So we went for physical ways of purifying them. And one of them is use a laser treatment and use the laser to remove the oxygens there. And our work shows that this work is there in this alloys and compounds last year, 2020. And can see that when you look into that XPS, you can see that the amount of oxygen is keep on reducing with laser intensity. And we could reduce the carbon to hydrogen ratio of graphene oxide. This is on graphene oxide from 1.9 to when it reduced to graphene oxide, the carbon to oxygen ratio was improved to 4.8. And when we fabricated a supercapacitor using that one, we get much higher, almost double energy storability than we get even using the simply heated carbon. One another work that we published last year is using a Fresnel lens to heat a graphene oxide surface and remove all this oxygen from its surface so that we can remove it using physical ways so that we don't have to harm environment. Okay, and this work was quite interesting, and this is really scalable because of the size of this Fresnel lens. We have used nearly 20 milligram sample in a disc of about spread over a silica disc of about 4 inches, and entire this silica graphene oxide could be reduced in less than 30 seconds time. So it's quite fast, and when we compare with our lasers, it is much efficient. For example, our carbon to oxygen ratio in using solar reduction has improved to 5.1 than 4.8 there. And when we compare fabricate a solar cell, supercapacitor using this one, we get about 60 watt-hour per kilogram energy density, about almost 10 times higher than the conventional one. Of course, we have used a different electrolyte there. We have 3.5 voltage, and we have much improved power density. The details of this work are here in this paper. And one another way we have looked at the carbon surface is its physical surface. As we have seen in the first slide, the capacity for capacity storage is ion absorption. The ions are absorbed on the pores. So there is a relationship between the pore and the size of the ion that is going to absorb on the surface. And what if the size of the ion is too large than the pore, or the pore is much larger than the ions? It doesn't contribute any charges. For example, when you look into a carbon surface, it looks like here, and we can see that there are pores. Actually, we cannot call it as pores; they are voids. Voids about 3 to 4 orders of magnitude larger than the size of solvated or unsolvated ions. And this doesn't contribute any charge storability, and they are really passive surface. And what we have done is to activate them. To activate it, what we have done is make hierarchical structures like something like a flower using titanium or some other cheaper materials and incorporate them into these voids. While doing so, we actually increase the ion diffusion paths or ion diffusion sites and ion storing sites. We can increase that one tremendously. And what is the result? when we look into the resultant voltage, we have much higher voltage. When we look into the total charge storability, we have 5-fold enhancement in capacitance. About just 10 weight percentage is this flower on the voids of this carbon increase the charge storability by 5 folds, and that's really considerable amount of charge storage. And when we have did the same work using non-aqueous electrolytes, the commercial electrolytes for commercial batteries and supercapacitors, we find that the same thing was there. We can have much enhanced voltage. For example, in this case, we can have up to 4.5 volts. This is when a half lithium half cell configuration. That's why it starts from 2. And we can see that the rate capability of our flower incorporated carbon surface is much higher and superior. The stability is high, storability is high, rate capability is high. All these means a simple 10 weight percentage metal oxide flowers in porous carbon can change the properties very drastically. And very recently, we have fabricated dual hybrids, 2 types of hybrids. One is the device is a hybrid, combining electrochemical capacitor and battery. So the device structure is hybrid, and the supercapacitor electrode itself is a hybrid material. So we call it as dual hybrid because we need to have some magic words to attract and to fascinate these editors. The editors always want fascinating things, not necessarily useful things. Okay, so there, when we have fabricated a dual hybrid, we have very good voltage, like see, for example, 4 voltage we have. But when you look at carefully here, we have a loss of about 0.5 voltage in the downstairs. And from where it is coming? And we can easily identify that it's actually coming from the impurities and resistance that most of those resistive elements present in our carbon sample, because all of them are bio-resourced carbon. And when you look here, the energy density and power density, we have energy density something like 60% of lithium battery. But power density, it can be as high as 10 times of lithium battery, but not simultaneously. When the power density is increased, energy density goes down. That's conventionally you observe in most of the supercapacitor research, and this is coming. This poor rate capability is coming from the electrical resistance of the electrode because of this non-ideal electrolyte system. Another way we approach this problem to functionalize our carbon surface is developing small metal oxide films. Why we always think of this small is we cannot afford the high amount because it's going to add a lot of cost. And this kind of small amount, the small amount used here is about 10 weight percentage. And this type of 10 small amount we can synthesize or we can derive by recycling the used materials or electronic waste. So this small 10% can be derived from there, and we have developed a chemical technique to develop a thin metal oxide film on porous carbon. And when we have looked at these properties, it is quite fascinating. And when we presented this to the industry, Norithake is a Japanese industry who invested in this project. So they are interested because our materials are not expensive, and it is actually a low or no carbon material in terms of processing. So they have invested for this metal oxide coated carbon. We have systematically studied its property. The details are here in this paper. And when we look into this energy storability, we still see that we have an increased voltage and much enhanced, not 2 or 3 times, much enhanced charge storability than pure carbon and pure metal oxide. And we again find that we did systematically which combination is best. Is it with our increase in metal oxide, is it going to be increase in capacitance? No. We have an optimum amount of here also 10 weight percentage And using that 10 weight percentage, we get very high quality carbon that can give us about 3 times higher power than.
Excuse me, Professor Josh, you have 5 more minutes to.
Yeah, fine. That should be okay. 3 times higher energy density and something similar to the power density of commercial supercapacitor. So we have developed a much better system. And in another way, we looked at the same way, but we have done, instead of metals, metal oxides, we coated metals here. Here, the metal we have coated is cobalt oxide. The details of that work is here in this Journal of Power Sources published last year in 2021. Here also we have much higher power density and storability than metal oxide because metals offer much the electrical response than metal oxides. Next, we have started looking into the cellulosic parts, the other part of biomass from palm kernel shell. So the empty fruit bunch that we can get after plugging these fruits out is a rich source of cellulose. We have derived cellulose from there and did a lot of work on developing them into membranes, cellulosic membrane. And in a typical work, we added some curcumin to this electrospun cellulose membrane and check whether it is good for wound healing. And very recently, that work is published in International Journal of Biological Macromolecules, is published in this year. And we have did a lot of work on cellulose derived from empty fruit bunch. And we have developed them in membranes. We have developed filter membranes, and we have developed separators for energy storage devices, patented it, but this work we did not publish it so far. We don't want to publish it. And the details are also not here, not shown here because of the commercial interest, but this can be done from renewable and sustainable materials. Well, another work we have done is dispersing carbon nanotube in a cellulosic gel and develop a flexible electrode for flexible or textile electronic or energy storage in a textile electronics, and developed a energy storage device, and it is giving exceptionally higher energy capability up to 90 watt hour per kilogram and specific power of about 1500 kilowatt per hour in this flexible by engaging silicon. The paper is currently under review. One another work we are currently doing is getting cellulose from waste tissues and convert them into useful carbon, graphitic, and other types of carbon and use for energy storage capabilities. One another thing people can think about is metal organic framework, and we have also done some metal organic framework. We have shown that a triple cation metal organic framework is good for an energy storage device using in a supercapacitor mechanism or a lithium-ion capacitor mechanism. And very recently, we have shown that this metal organic framework is a very good electrochemical sensor for a nilutamide. That's an anti-cancer drug used for treating prostate cancer. All this work is published recently. So to conclude, we have biomass carbon on that a sustainable source of carbon for supercapacitive energy storage, or that chemical purity is not up to a level required for practical use. Intense efforts are required to purify them via eco-friendly methods. And large voids could be beneficially used for charge storage via filling them with hierarchical structures with many diffusion layers. And we have shown that charge storage in carbon could be enhanced by developing thin metal or metal oxide structures over them. Or metal organic framework also offers sustainable electrochemical storage and sensing medium. Once again, I thank for Prof. Neelam Srivastava and her team, ICEMD, for inviting me, and my funders and team. And moreover, thank you very much for the attention of all the participants. Thank you very much.
Yeah, thank you, Professor Josh. Now the floor is open for one or two questions we can take quickly. So I have a question, Professor Josh.
Yes, please.
Audience of, those who are beginners in this field of supercapacitors and batteries, particularly for pseudo supercapacitors and the battery, one would like how to differentiate between these two actions. There is a Faradic charge transfer,
Yeah.
and if you have a cyclic voltammetry or any other technique, there is a very salient. How do you differentiate that this is a concrete, conclusive, how do you conclude that this is a Faradic process and this is a pseudo Faradic process and this is a EDLC, like double layer, I can understand, but
Okay.
rest of these
Okay.
two,
So that's actually that's a good question, Prof. Dalvi. It has been a widely discussed topic in this literature of supercapacitive charge storage. Where should we look into differentiate them? Basically, we can see them what type, categorize them what type from our cyclic voltammetry and galvanostatic charge discharge cycling. So if the cyclic voltammetry shows non-linear voltammetric current under the different voltages, then obviously that there is some sort of Faradic effect. And similarly, if the galvanostatic discharge and how far it is from non-linear linearity, perfectly linear is capacitive, and nearly linear is pseudo-capacitive, and non-linear is definitely not belong to any of them. It is battery type.
Oh, yeah, very nice, very nice.
Yeah,
Thank you
thank
very
you.
much. Yes, sir. Any other question? Uh, all right. If there are no more questions, then let us thank Professor Josh for such a nice talk and very informative, things, and bringing us to many new things, whatever he has been doing. Thank you very much, Professor Josh.
Okay, thank you.
You may remove your slides now. And now we are going back to Professor Kamlesh Pandey's presentation. I have already introduced to him, so without wasting time, sir, can we start now the presentation?
Yes.
So, yeah, floor is yours now, please.
Yes, ma'am. Yes, ma'am.
Please start.
Yes, ma'am.
Thank you, Professor Dalvi, for the nice introduction before Professor Jess. Now, first of all, I would like to thank the organizers, especially Professor Neelam Srivastava and Professor Bhaskar Bhattacharya, for inviting me to deliver a talk in this ICEMD 2022. Now, first of all, I will introduce myself. I am Dr. Kamlesh Pandey and working in a unique center of the India where we have the facilities of high pressure and high temperature. And this talk is based on the in material like nano diamond, which is make the composite with polymer, and this composite has different application for the industrial as well as the medical application. Now we can divide our talk into three parts. First part is the polymer composite, basic of the polymer composite. Second part is the main part, that synthesis of the nanodiamonds. And third, the experimental results with some polymer composite with the nanodiamonds. Now we start this next slide. Next. Now, what is a composite material? Simply, composite material is a material in which two components are used, and this one is mixed in the another. It is either synthetic or the natural. The best example of the natural composite is the wood, in which the cellulose and lignins are the two material which is inside the wood. And for example, we can say the bamboo is the very efficient wood composite structure. Next. The composite materials can be classified with these parts, like the one is the reinforcement materials and other is the matrix. The matrix can be either polymer, metal or ceramics, and the reinforced materials can be glass, carbon, organic, boron, ceramic, metallic material. Next. These composites can be classified into two parts. One is called the micro composite and another is the nano composite. The nano composite had the property that multi-phase material comprising a matrix, polymer and dispersed inorganic materials. These are the inorganics and like clay, silicon, zeolite, carbon, molybdenum oxide, sulfide, etc. And now these materials, these nanocomposites had the property for the different industrial and other application. Now I will discuss about the a material which has some basic and unique properties like for the industrial as well as the medical application. Next. Now we skip some slide and directly come to the synthesis of the nanocomposite, nano diamonds. Now come next. Here is the some type of composite like the polymer composite. Next, the composite of the metals. In this, we can use the matrix like this: aluminium, magnesium, lead, copper, and these are the fibers: graphite, boron, alumina, and these are the materials which can be mixed with the matrix. Next. The other composite class is the composite ceramic matrix, in which we can make the one part is the ceramics and other is the polymer matrix. Next. These are the some application of these materials. These materials are the lighter materials and this can be used for the different fire resisting property, and we can use these material for the other applications. Next. Escape some transparency, please, madam. Next. These are the advantages, and these nanocomposites are found in nature also. It is found in this abalone, and these are the some bio nanocomposites. Next. The process of the synthesis of the nanocomposites are the chemical synthesis, gas phase synthesis, chemical vapor deposition, combustion flame synthesis, liquid phase synthesis. Next. These are the process of gas phase synthesis, and this is the equipment by which we can synthesize the composite materials. Next. The chemical vapor deposition techniques. In this, the precursor vapor is passed through a hot wall reactor and the precursor decompose and nanoparticles nucleates in the gas phase. And this is the instrument by which we can make this. Nanocomposite materials can be also synthesized by the ball milling or mechanical alloying method. For this, we put the materials in a ball mill and give some certain timing, and by which we can make the nanocomposite materials. Next. This is the liquid phase synthesis process, in which the two chemicals are fusion such that they react and produce the material as we desire. This type of instrument we are using for the liquid phase synthesis. Next. Now we come to the second. The second part of my talk is the synthesis of nanodiamonds. This is a very typical process by which we can synthesize the nano diamonds or diamonds. And this facility is very difficult facility in which we can synthesize this. In our lab, we have high pressure and high temperature, different equipments which are discussed in the next slide. And then we can start this research in 2004. First, this research was used to make some diamonds powder for the industrial application. Secondly, we start some try to color some tiny diamonds for the jewelry application. Now we are preparing some nano diamonds for the composite materials which are applicable for the different industrial as well as the medical application. For the development of diamond, we start the carbon. Carbon is crystalline carbon, and this is the carbon has two allotrope. One is the graphite and other is the diamond. Graphite has sp2 bonded carbon and diamond has the sp3 bonded carbon. And the interlayer distance of the graphite is 3.35 angstrom and the carbon diamond is the 2.19 angstrom. Next. If we go to the phase diagram of the carbon, next, then we found that this graphite can be converted into diamond at a certain pressure and temperature. For this, we use approximately 50 kilobar pressure and 16 to 1800 degrees centigrade temperature. This is the range of the formation of diamond where we can form the diamond. Now, next. Diamond has some specific properties. Diamond has the hardest natural material which has the hardness of at Mohs scale is 10 and the another scale that is loop hardness it is 8000 to 10400 and their Young modulus in between 1050 to 1200. Now thermal conductivity is 20 watt per centimeter per degree centigrade. Coefficient of fraction is 0.05. Refractive index is high. Some other materials can be also show some properties like to the diamond like zircons. Now, if we come to the history of the diamond next. History of the diamond, then we found that first natural diamonds come from the earth at a very long depth of the earth. But after 1950, some companies had tried to make the synthetic diamond in which in 1952 Union Carbide first of all trying to make the some high pressure diamonds and then after this in 1954, Sweden General Electric Company synthesized the diamond at high pressure and high temperature. In early 80s, some institute make some CVD synthetic diamonds. Next. These are the journey of synthetic diamond from 1952 to present time. These from 56, there are some years in which the development has the very important role, that is 1956, 1960. After in the decade of 1960, some Soviet scientists has developed the powder diamond by the detonation technique, and these development is not came to the world up to 1980s. In 1980s, there has some publication in 1983, first time most probably, the first publication which shows that there are some diamonds present in the synthetic form that has the size of the nanometer. Next. These are the complete journey of the development of synthetic nano diamonds. Next. We can classify diamond into two main groups. One is type A diamond and another is the type B diamond. So for the classification, the word type is most important in the case of diamond. Next. Type 1 diamond, which were visible in UV radiation below 300 nanometer and absorb strongly in the part of IR region in the range of 7,000 to 20,000 nanometer. The type 2 diamond, which transmitted UV wavelength and displayed little or no anomalous birefringence when viewed between crossed polarizer, means type 2 diamond were nearly perfect in the term of their structure. Next. Now we come to the different types, and another classification is based on the impurity present in the diamond, and these diamonds are also important. If we have the nitrogen impurity in the diamond, then its color will be yellow, and if in the latex there is some boron based impurity, then its color will be blue. Next. These are the type 1 and type 2 diamond classification. Next. There are some techniques by which we can sensitize the nano diamonds, because our aim is to make some nano diamond powder and disperse in the polymer matrix. For this, the first technique is the CVD techniques, by which chemical vapor deposition technique, in which we can make the nano or micro polycrystalline diamond through the large high quality single crystal diamond are coating on the variety of shapes with control the grain size. Next. These are the CVD diamond fall into two of these. One is the polycrystalline and another class is the single crystal diamond. Now the polycrystalline diamond is typically formed when the growth occurs at a non-diamond substrate. Next. This is the important part of the nano diamond synthesis, is the detonation technique, in which we use the TNT and RDX in the composition of 40-60 or 70-30, and detonation in a cylinder the size of this detonation chamber, and we can form the nano diamond. Next. These are the process that rapid cooling must be followed the detonation, rapid chemical purification is needed, and then we can get the nano diamond by the detonation technique. Next. These are the setup for the nano diamond synthesis by the detonation technique, and now we come to the our part by which we can synthesize the nano diamonds. Next. Here, high pressure, high temperature technique. These 5 techniques are the high pressure, high temperature technique by which we can make the nano diamond. One is called the piston cylinder apparatus. Second is the multi-anvil apparatus, belt type high pressure, high temperature apparatus, Biar's apparatus, and diamond anvil apparatus. Diamond anvil apparatus is present in the BARC in India, and this multi-anvil apparatus is the only one instrument which is present in the National Center of Experimental Mineralogy and Petrology, University of Allahabad. Next. This is the bars first. Before this. This is the bars apparatus. By this technology, first of all, in 1989 to 1991, by the scientists of the Academy of Science USSR has developed this type of instrument. This high pressure, high temperature apparatus is usually used for growing processed minerals, especially diamond and boron nitride. Typical pressure generated by this is the 10 GPa and 2500 degrees centigrade. Next. This is a glimpse of the bars apparatus. Next. And these are the parts of the bars apparatus. Next. The piston cylinder apparatus. This apparatus has the capacity to generate a pressure up to 40 kilobar and 200 degree centigrade temperature. By this we can generate the 20 kilobar pressure and temperature, and this can also perform further synthesis of the diamond. Next. This is the total layout of the instrument, in which this is the sample capsule, and then we take some pressure medium and give the pressure from one side, this side and this side, and then we can make phase change of the graphite powder or carbon powder. Next. The another instrument is the belt apparatus. Belt apparatus also has the two opposed piston compressed as a simple retained in a strongly reinforced multi-layer cylindrical or belt in the uniaxial press. And by this we can also generate the pressure up to 10 GPa. Next. This is the ray cross-sectional ray diagram of the bar apparatus. Now we come to the multi-anvil. The first multi-anvil is called the Hall tetrahedral apparatus, and in which we can generate the pressure up to 70 GPa, 12 GPa means 120 kilobar. Next. This is the structure of the instrument. Next. Now the cubic anvil press, by which we can generate the pressure up to 10 GPa also. Next. Next. The another type is the octahedral anvil press. This is the first development of the octahedral called the Kawai type apparatus, in which the octahedral press medium was compressed by 8 equivalent tungsten carbide anvil started by the middle of the 1960s. Here it is important that the multi-anvil apparatus has giving the pressure on the material by 3 sections. This is also called 268 type of system. Means first we press the material by the upper and lower part, that is the 2, and this pressure transfer into the 6th side of a octahedral press, and then this can be converted into very high pressure. As we know that P is equal to F by A, pressure is equal to force by area. So we cannot increase force beyond a limit. So we can change or reduce the area of the material, and by which we can increase the pressure. Next. 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 This is the octahedral press assembly, where we put our sample, and this is the two type of the upper and lower type of press. Next. Next. Here we see the range of pressure range by the different high pressure instrument. One is the piston cylinder, gas apparatus. This range is the red range is the multi-anvil pressure range. Next. This is our multi-anvil apparatus, which is present in our laboratory. Next. This is the planar view of the putting the sample inside the multi-anvil apparatus. Next. This is the sectional view. Next. Here we see these are the anvils. These are the 6 anvils of the multi-anvil. Next. Here these are the octahedral tungsten carbide tubes, where fins are these. Now this is called the TEL, truncated edge length, and this depends the truncated edge length start from 2 mm to 10 mm, and this truncated edge length also responsible for the generation of high pressure. Next. These are the parts of the multi-anvil apparatus. One is the one hydraulic press provided the force, a high pressure module that contains anvils, and third is the sample assembly and the sample assembly of the material. Next.
You can take few more minutes to wind up, please.
Okay. Dipti, in last some slides. One. Now we come to the polymer nano diamond composite. The first we try to show there are 6 allotrope of the carbon, that is nano diamond, fluorine, carbon nanotubes, and graphene and graphene oxides. Now we take a case of the polyester carbonious nanofiber composite. Next. First is the polystyrene graphene nanocomposite. This has the some optical, electrical, mechanical, and thermal property. Next, the polyester graphene oxide nanocomposite, and the next is polyester carbon nanotube composites. Next. Next. There is some results where here is the TEM structure of the nano diamonds. Next. This is the same and TEM structure of the PAN and nano diamond composites. Next. The UV structure, UV spectroscopic study of the pan ND film with different content of the nano diamonds. Next. Now we come to, these are the solution in which we disperse the nano diamond in different ratios. Now we come to the last part, the application of the nano diamond, polymer nano diamond. Stop. First is the EMI shielding. By this nano diamond, the electromagnetic interface shielding is an emerging application for the polymer nano diamond composite. Several carbon-based nanomaterials have been used for the enhance the electromagnetic interference shielding efficiency of polymeric nanocomposite, including graphene, graphite, carbon black, carbon nanofiber are used. The another field, as the topic of this conference, is the energy materials. For the energy harvesting, we also use the polymer nano diamond composites. And the next, in fuel cell, for the electrolyte purpose, we use the nano diamond polymer composite materials, and by this we can make a slightly hard polymer composite, as we say before, the polymer electrolyte membrane fuel cell. We use some support for the membrane, but in case of this material is hard but not brittle. So we can use for the better electrolyte material of the polymer nano diamond composite for the making the membrane for the fuel cell. Next. We can also use this membrane for the supercapacitor, as we discussed. So many speakers I discussed earlier for the supercapacitor. Next. This can be used in the textile industry. The textile industry, in which the polyester and carbonious material, nanofiber based material can be used, and this polymer and nano diamond material is better, have the potential for these type of application in the textile industry. Next. The future potential of this polymer nano diamond composite is the development of some instrument, development of some membrane for the environmental friendly materials, and this can be used for the different energy application. Thank you.
Thank you, Professor Kamlesh Pandey sir, for a nice presentation. Now the floor is open for 2-3 questions we can take quickly. There are questions. Sir, I have a query. When we say
Okay.
that you are preparing a diamond by pressure, high pressure, so it's a very, very important area of physics, high pressure physics. And then when we go and you have shown the phase diagram that there is a particular pressure, particular temperature, I think, where you are able to transform the graphite into diamond.
Yes.
And now if you remove those pressures and other conditions, then whether the structure of the newly formed diamond crystallite will relax to the previous one, or it will remain stable forever?
Remain stable forever. But in this case, this instrument, that is multi-annual high pressure apparatus, we only make some powder type of diamond.
Powder type of this.
Powder type
What
of
is the
diamond,
packing
which
fraction? The atomic packing factor, typically we have 34% for the conventional natural diamond. So how much is the packing in a unit cell of this?
this is very low, because there are some graphite impurity also present in that powder.
I see. All right. So thank you. Is there any other question? If there is no more question, then let us thank Professor Kamlesh Pandey for such a nice and informative presentation and lecture. So thank you very much. So this way now all the talks of this session number 8 are done, and thank you very much for giving me this opportunity to hold. So floor is over to you now, Neelamji. So I'm done.
हम कुछ था प्रिय प्रिय
You're on mute.
Sorry. Yeah. Thank you, Professor Srivastav, for inviting me and also for giving the chance to chair a session. So, and of course, for the nice introduction about me. So, but this is not about talking about me. This is actually, the session is now for us to listen from our speakers. So I can see that there are 4 speakers, but I have been informed by the organizers that one speaker is having difficulties. So she has recorded a video for sharing on YouTube. I think the organizers will share the video at some point of time, and perhaps they will share the link with us so that the participants can see. But apart from one speaker, which is, I think, Dr. Maria Bono Mena, she will not be here today, but her video will be available. All the rest of the speakers are available. So now, according to the list that I have, I think the first speaker that we have is Dr. Yogesh Kumar. I hope Yogesh Kumar is here.
Yes. Good afternoon to all of you. I'm here.
So I would begin by brief introduction to Dr. Yogesh Kumar, and I request Yogesh Kumar, please start sharing your slides so that we don't lose any further time while I give the brief introduction to you. Okay. So Dr. Kumar is an assistant professor in the Department of Physics, ARSD College under the University of Delhi. He has 10 years of teaching and research experience post PhD. He did his postdoctoral research fellowship at from University of Poznan University of Technology in Poland during 2013 and 14. He published more than 50 research articles in various published by various scientific bodies, scientific publishers, and he visited several countries like Poland, Italy, Germany, Turkey, etc. for research purpose. Presently, he is working on energy materials and devices with and working in several committees of the college. He has also organized several short-term courses, and he is worked in Nissan Renault battery material related project in 2012, and have also worked briefly at Bhabha Atomic Research Center as a visiting academic fellow. He got selected for an international scientist position at National University of Science and Technology, Moscow, Russia in 2014. And he participated in a workshop organized by ICTP Italy. So the floor is for you, sir. Please present your topic, your lecture.
My presentation is visible to you?
Yes.
Okay, fine. So this is once again one more presentation on the supercapacitors. And
Okay.
you all know about the introduction of this device, electrode and electrolytes. So I directly start with this one slide only.
Sure.
This is the target, that the energy density. We all are working to increase the energy density of the supercapacitors. All the supercapacitors are having its own unique properties. So this is the focus area, and for this we need good electrolyte and good electrode material also as well. So in this series that we have prepared, once again, this is the not a very new material, carbon polyaniline composite. Characterize them and try to make them supercapacitors and compare with the activated carbon one, and we use this synthesis approach to make this composite of activated carbon with the polyaniline, and we have chosen such type of composition, or we found such type of, ultimately after that analysis of composite materials. This is the FTIR of pure carbon, and we found this similar to the reported ones in the literature. And this is the FTIR of the composite materials, and there is no abnormality in that, and we found it compatible. This is the ACM pictures of pure carbon, the picture A of electron microscope image. So this is the typical carbon picture, and when we increase this polyaniline composite in the carbon, so it shows it's fibrous polyaniline structure. Sorry, analysis also changed with this. And I will show you the few results on the phosphorus mixed activated carbons also. This is the FTI result for that. This is the TM of the pure activated carbon, and you see in the TM of pure activated carbon, it is my first observation that there is a spherical type of spherical nanoparticle of carbon are observed in this TM image. For the, and its size is about 10 20 nanometers. And when we mix this activated carbon with the polyaniline, doped shape of the this is the Raman spectrum of the activated carbon, the black one, and other two are the polyaniline and one of the composite. And you see that carbon retain its bands, D bands and G bands, even in this mixing with the polyaniline. And this is the supercapacitor result for the activated carbon, pure activated carbon. This is a supercapacitor result, and we found the capacitance maximum 82 farad per gram for this pure activated carbon. Okay, at a 10 millihertz frequency. Because it is EDLC, it is a double layer type of thing, and we have done impedance spectroscopy and CV and charge star all, but we reported and we found this 82 farad per gram value constant throughout. These are the X-ray diagram for such composites. May I skip them? This is the repeated, I think, once again. May I skip them? Yes. Okay. This is the surface area and porosity measurement for the using the same carbon with the polyaniline, and we made the composite, and we see the how the porosity and the surface area get changed when we are increasing the loading of polyaniline. Although the polyaniline itself, you can see in the figure A, the green diagram, which is for the polyaniline, it is a very low surface area material. The black one is the surface area diagram for the carbon material. So in between for the blue one, which is the optimized one, that we have enough microporosity and mesoporosity both. So we found this APA 29.4 as a good electrode material for supercapacitor application. In the figure B, you can see this pore size distribution of all types of carbon materials and composites with polyaniline and pure polyaniline also. And you see that pore volume is maximum for the APA 29.4. So this is the, once again, from this pore size distribution also we can see that, we can say that this material can be good for supercapacitor application. This is the list of the parameters. According, this is the data extracted from these graphs. This is the comparative plot of supercapacitors prepared from activated carbon, polyaniline, and its composite. And this APA 29.4, we found it comparatively good. Even it is having the polyaniline in it, but even it is in the lower frequency region, it is just parallel to the imaginary impedance axis. And you see that variation of the capacitance with the cycle number, we have done the charge discharge studies also, and we found that after the 2000 cycles, it is retaining 80% of capacitance, 80% of 800 farad per gram. This is the capacitance value that is coming with the mixing activated carbon with the polyaniline. As I can remind that the pure activated carbon was giving almost 80 farad per gram. Now it is 800. So it is 10 times improvement in the capacitance value. And this deterioration in the capacitance value can be controlled, but I need some facilities which I don't have. So it is a matter of future research, how I can maintain this degradation of the performance. For, you see, this is the cycle for the composite. This is the cycle stability for the composite. But for pure activated carbon, we have cycled this pure activated carbon up to 1,20,000 cycles. And it was only 95%. It was stable up to 95%. Only 15% or only 5% of deterioration in the specific capacitance value. But the shape of cyclic voltammogram get changed. This is the cyclic voltammograms of polyaniline composites compared with polyaniline and activated carbon, pure activated carbon one. As we mixing, we keep on increasing the component of polyaniline, and we found that it is, the shape of the curve get changed as we increase the scan rate. And you see, this is the deterioration also. With the scanner rate. But you see, the composite is performing, if you see, for the low scan rates, the composite of polyaniline and AC is giving you huge better capacitance in comparison to polyaniline alone and activated carbon alone. This is the all parameters calculated from these all studies of electrochemical studies of these cells based on composite and pure polyaniline and activated carbon. This is the galvanostatic charge discharge studies. We compared once again all three. The graph A, it is almost linear and it is a double layer feature of activated carbon. B belongs to the polyaniline and C belongs to the composite. This is a similar plot for the current density. Earlier was for the scanner rate. And we found the similar behavior. Composite is performing better than all other devices. And this is the parameters extracted from the graphs. This is the Ragon plot. This is showing its standard shape, the energy density versus power curve. So in the conclusion, I can say that these activated carbon having low capacitance value. So low capacitance value is a problem to increase energy density, because energy is directly proportional to the capacitance value. So the composite is the one of the option, but these composites do not perform not much durable for the cycling and for the shelf life. So there is a need to stabilize their performance. In the objective 2, that the doping of heteroatoms in the activated carbon may also increase the capacitance value of activated carbon. So we have chosen as a base material in this study activated carbon, our base material, and we are trying to change this activated carbon with the making composites or mixing some heteroatoms in this in this activated carbons. Okay, so in this way, what we have done, that we mix this SBAC. This SBAC is our pure activated carbon with these two acids. First with the HNO3, and with HNO3 is not doing nothing, but it is just cleaning the surface of activated carbon. Oh, it can little bit oxidize the carbon surface. Then we treated this with H3PO4, and H3PO4 is generally an activating agent for the high temperature activation of the carbon materials. But here I can yes, this is the method we have adopted from some paper, that H3PO4 can treat this carbon, and the surface can be functionalized with this phosphorus heteroatoms. So there is some mixture of phosphorus can be present in the surface of carbon after this treatment. So this X-ray diffraction doesn't change much after the treatment of nitric acid and phosphoric acid. We are getting almost same parameters. There is a little bit change. I will not go in the detail of that, and you can see this is the you see this D band and G band, how this affects, how this treatment of nitric acid affects these two bands of activated carbon. And these are the grains of activated carbons after the treatment of nitric acid and phosphoric acid, and you see there is a no much change. It is almost similar. And this is the evidence that phosphorus is attached to the surface of carbon. This XPS spectra for the phosphorus, we can see in the two ways there is a possibility that phosphorus can interact with the carbon, and we have deliberately inserted or mixed this phosphorus with the activated carbon to increase pseudoactive surface, to introduce redox reaction in the carbon. Okay. And this is the surface area studies of activated carbon with the, you see, after the treatment and before the treatment, you see this is the change. In earlier case, when we mix this activated carbon with polyaniline, you can see that there is a huge changes in the surface area. But when you mix it with some phosphorus and treatment with nitric acid, there is no much change. Yes, this initial one, this is the ACT, this black one, this is the nitric acid doped. So this drastically reduced the surface area of this activated carbon. But when the phosphorus treatment, phosphorus mixing, it recovers its loss and now it's become more mesoporous. And this is the, this is the, oh no, yes, this one. This is the porosity parameters for all type of carbon. AC is the pure AC. ACT, this is the nitric acid treated carbon. Surface area reduced drastically, and micropore volume also.
Dr.
Mesopore
Kumar,
volume also.
please wind up within a couple of minutes. Please wind up within a couple of minutes. Huh?
Okay. So yeah. So this is the CV curve, and we found that it is, in this case, the capacitance value goes to the 350 from the 80 farad per gram, just treating with the nitric acid and the phosphoric acid. Okay, and the carbon is the same, carbon material is the same, and this is the impedance, galvanostatic data at higher current densities also. This is the impedance spectra for all these cells. So phosphorus heteroatoms are successfully mixed with the nitric acid trade biomass derived porous carbon, and all these studies had been done with 1 molar Na2SO4 electrolyte. So we have used the liquid electrolyte in that. The few studies we have done with MnO2 nanostructures prepared using the hydrothermal technique, and this beta MnO2 we have prepared. The X-ray data is match with the beta MnO2, and this is the rod-like structure we obtained. XPS also further, FTI also further confirms this, and we finally make this electrode material out of this, and we characterize them with all 3 techniques, electrochemical techniques, and we found it is, we are getting almost 288 farad per gram of the capacitance value, which is further improved to the 437. So this is the maximum we got for the beta MnO2, and when we compare this beta MnO2 with the literature, we found that this is the, we are comparable to the literature, and this is cycling performance also, we are getting better results when we compared with the literature. This all data is published, previous one also, what I have shown you for the polyaniline and carbon, and this data is also published. So you can check with the references if you will Google this beta MnO2 based. One another way that we mix this.
Dr. Kumar, I think we We are short of time. We have to finish.
Okay. So I may skip. I may conclude that out of this, these, this is the finally we have prepared this carbon doped MnO2. Sorry, carbon mixed MnO2 also, and we found that this carbon mixed MnO2 is performing better than the beta MnO2 pure and silver mixed MnO2. So carbon is still, a material of interest, and it is useful in many ways. So thank you very much for your patience. Thank you, Chairman.
Thank you for finishing in time, because we are, as you know, we are running half an hour late. So anyway, so we are pretty bound by the time. So the session is open for some quick question, one or two. Well, if there is no question, I will ask a question. You showed some phosphorus data. Can you have you made any estimation of the phosphorus content in the activated carbon that you tried with?
Yes.
What is the typical phosphorus content?
I could show you.
No, it's not important. Maybe I have missed out.
Yeah, we have estimated this. Yes, EDEX.
From the EDEX, okay.
Yeah.
And no, because I saw you also showed some XPS images, right? XPS spectra. So from the
XPS also I have shown.
XPS, did you estimate?
Actually, you see, this phosphorus is 20. In the weight percent, it is almost 20. It is coming.
Atomic
and in
percent?
Atomic percent, it is 11.
11%, yeah. So my next question was related to XPS, because in the XPS you have shown phosphorus 2p spectrum. So there, from there also you can possibly estimate, and this should be matched whether your estimation from the EDEX is matching with it. That's one aspect.
Yeah. Maybe I may ask to my student to compare it. Yes.
Okay. Yeah. The other question is, what is the chemical state of phosphorus? Is it pure phosphorus 0, phosphorus? What is this? I can see some components you have developed by curve fitting, but the main peak is what? What is the main peak? What is the phosphorus peak? Is it P what?
This
P0?
is the COP peak for this blue one.
Yes.
And this is the P bond O peak, this red one.
Yeah, I got it. Okay, the main peak is basically the convolution of all this together, right? So you have some phosphorus bound with oxygen and some phosphorus bound with oxygen plus carbon. So a single
carbon.
bond. And okay, fine.
Actually, this is the way. First we treat it with the nitric acid, and nitric acid is known for oxidizing the carbon, introducing carbon into the carbon surface. So it is a well known. There are thousands of reports that if you treat the carbon surface with a nitric acid, then it introduces oxygen in there. After that, it can attract phosphorus. So the oxygen is necessary when if you want to easily bound your phosphorus to the carbon surface.
Sure. Okay, thank you. Fine. Okay, may I request you to unshare your slides so that the next speaker can start sharing with it.
And I stopped sharing.
Thank you once again. I think our next speakers are waiting because we are running half an hour late. I think the speakers are assuming that their times are now half an hour delayed. So let me tell the two speakers who are present, Dr. Santos and Dr. Paulina, right? Angieska Paulica. Yeah, both of them are present, I can see. So we are running half an hour late. So I think the first speaker here, the second speaker of this session, that is my next speaker, would be Professor Agnieszka Paulica. So Dr. Santos, you have to still wait for about 25 minutes. Okay. So Professor Paulica is already sharing the slides, which is very good. So let me briefly introduce Professor Paulica to you. So Professor Paulica has obtained her master's from Warsaw University of Technology in Poland, and her PhD was in physical chemistry at the University of Sao Paulo in Brazil in 1993. She is currently professor at the University of Sao Paulo. She has published 189 full papers in professional journals and 22 conference proceedings. She is the author of 3 books and 4 patents and has received 17 awards. In 2014, she has received the scientific title of Professor of Chemistry from President of Poland, Bronislaw Komorowski. Yeah. She participated in several scientific international events and was a visiting professor of Warsaw University of Technology in Poland in 2008 and at the University of Malay, Malaysia in 2011. In 2012, 2013, and 2015, she was a visiting scholar at the lab of Professor Jerzy Kaniki of the EECS, University of Michigan, USA. She is a member of the editorial board of 4 international journals and referee of more than 30 magazines and Brazilian and other international science sponsoring agencies. The keywords related to her works are mainly solid polymeric electrolytes, natural polymers, electrochromic devices, thin films conducting polymers, electrochromism, and conduction, etc. So I think that's a lot she has done, and I am very eager to meet her for the first time and eagerly waiting to hear to hear her presentation. Thank you, Professor Pawliska. It's over to you, Paulika.
Sure. Sorry. This is the first time I am using this platform, so I had my presentation. I shared my presentation, but I couldn't unmute my phone. So now I lost my presentation from my screen. So this is. Just a moment, please. Sorry about that.
Coming? No.
No, I just lost it.
You try again.
Yeah, but my PowerPoint just closed.
You can unshare and reshare.
Okay, I got it. So now I can share it. Okay. Yeah. Thank you so much. Yes. Well, this is the first time I am using this platform, so I have no experience. Good afternoon for everybody. Thank you very much for so nice presentation. Of my person. Yes, and first of all, I would like to thank Professor Neelam Srivastava for inviting me to present my work. It's sure I can't present all of it. I will just present a few.
Professor Paulika, you may have to turn off your video because the internet is very slow, it seems.
Oh, okay. So now video. I don't know. I lost the access.
It's fine. It's fine. We can see her. We can see the presentation also.
Okay. So I will show you only a few of my research, most recent research we did in our lab.
Yes, you can start. We can see the presentation.
Okay, so this time I will present eco-friendly polymer electrolytes for electrochromic devices, and the outline will be a little bit about natural macromolecules. This is the base polymers we work with, their sources, advantages, and modifications. Then I will be talking about polymer electrolytes and electrochromic devices we make with this polymer electrolytes. And finally, I will show you also some electrochromic device we made a few years, a little bit more, which is very interesting, and conclusions. So sources and advantages of natural polymers are very vast. Actually, the natural polymers can be obtained from plants like cellulose, starch, pectin, agar, DNA. We can also have them from animals like gelatin or DNA, and from bacteria. This is a less known source, but it's very nice because we have examples of bacterial cellulose, which is produced by Acetobacter, and it's already produced in the membrane form. So it's very interesting for several applications, mainly, for instance, they're researched for medical application. But we also did some research for polymer electrolytes, which I am not going to show today. The other one is Galen gum, which is from Pseudomonas elodea. And this gum is also very nice for polymer electrolytes. Actually, there are many polysaccharides. Galen gum is kind of polysaccharide, and so many polysaccharides are very interesting for polymer electrolytes. Why are they interesting? This is because most of them are soluble in water, and so they can be obtained in aqueous solutions, and also some of them in organic solvents, which is not exactly very common. But I will show you today the work we did with some of, actually it's a modified polymer, it's a modified polysaccharide, which is soluble in organic solvent. So they can produce homogeneous gels and film membranes, which are very interesting and very desirable for devices applications, especially those the electrochromic devices or electrochemical devices, because they're solid or semi-solid, so they're kind of safe. The other advantage is that they are human being compatible and biodegradable. So biocompatibility, we know that is important for devices that are applied in human beings. So this is also very interesting advantage for those polymers. Then they have also they're mechanically stable and strong. And the other advantage is their price. Here I put that they're cheap, but it's not always like that. Actually, some of them, like starch, cellulose, are relatively cheap. But when we look at other polymers like or macromolecules like DNA, agar, or Galen gum, the price is not so interesting. Not because I think this is because they're mostly used for food industry, so they're not so much spread out in other fields of applications. But if they were, probably the price would be dropping down. So natural polymers. Natural polymers can be modified. So as we look at the polymer field, we know that there are natural polymers, there are modified polymers, and there are synthetic polymers. So the modified polymers are kind of in between of both the natural and synthetic. And modified polymers are exactly the chemically modified natural macromolecules. And those polymers are also very widespread out because they're applied in various industries, in cosmetics, in medical industry, in pharmaceutics, and food industry too. So we have like modification of natural polymers, like modification of cellulose that gives hydroxyethyl cellulose, hydroxypropyl cellulose. There are also modified starch, and so on. And so we can produce networks from these polymers by grafting, but we can produce or cross-linking, networks by cross-linking or grafting. We can produce blends by plasticization with other polymers or some small molecules, compatible small molecules. And also it's possible to produce nanocomposites with mixture with carbon nanotubes, clays, etc. So as we know, they're used, and I already said this, they're used in food, like thickeners, softeners, texture modifiers, in cosmetics, like thickeners and cream additives. They are also in food, like they're used as stabilizers for food. It's very common. In medicine, they're used like drug delivery carriers, capsules, scaffolds, etc. And also, this is also our field of research in agriculture, as hydrogels for controlled water and fertilizer release. So I would like to talk a little bit about polymer electrolytes. We have different types of polymer electrolytes, and who works with them knows that everything started with polyethylene oxide, and the development grew up for other polymers too. But the main polymer for this kind of applications is still polyethylene oxide. So, but beside this one, we have also nanocomposite polymer electrolyte. We have gel polymer electrolytes, and the conductivity of this kind of materials can be up to 10⁻². Sometimes we see the works that there are even higher, so 10⁻1 Siemens per centimeter. The other property is sometimes required is a transparency. So some of them are transparent, some other not, or more opaque. But in the case of natural polymers, we mainly obtain the transparent membranes. And another property is good adhesion to glass and some other metal surfaces. And advantages are of using this kind of gel polymer electrolytes or polymer electrolytes are accommodation without phase degradation, without physical degradation, without cracking of the interfacial contacts. And also, this is important due to the volume change during an electrochemical cycling. So during these years, I am working with natural polymers as polymer electrolytes. We have developed different systems. Here we didn't work, actually we work also with PEO, but we grafted PEO on natural polymer, as we can see here on this picture. We have hydroxyethyl cellulose or here. It's actually, yeah. So we grafted PO on this. We actually cross-linked this polysaccharide chains with PO molecules, and which is also possible to do with other polymers. And we did this also for hydroxypropyl cellulose, so for two kinds of polymers. But it was the beginning of our work, with which we started in collaboration with French scientists from École Française de Papeterie et des Industries Graphiques de Saint-Martin-d'Air, which is close to Grenoble in France. It was with Jean-François Lenest and Alexandre Gandini. But the problem was at that time that these samples, they're very, very nice. We had many problems to synthesize them, and the ionic conductivities were very, very low. So they were not very interesting to apply them in electrochemical devices. But it was very nice as organic chemistry reactions, samples. So then we started to work with blends and plasticized systems. First, we started with addition of plasticizer. Then we did more recently, we did some mixtures of polymers. And we observed that these systems are much more interesting, easier to obtain, and also there are they have interesting high ionic conductivity values that range from 10-5, 10- to 10-4, 10-3 Siemens per centimeter. And the most recent work is to work with composite-based systems, where usually the researchers add some nanoparticles like alumina, titanium oxide, SEI2, etc., or also carbon nanotubes. So I will show you some other work we did with clay. Electrochromic devices. I have worked during my postdoc many years ago with electrochromic coatings, especially with niobium pentoxide. And so this was the idea to working with that was the idea to then to join, like to combine these coatings, electrochromic coatings with electrolytes. So as we see here, these systems are composed basically of 5 coatings. When we have ITO coatings, electronic conducting coatings. Then we have ion storage, which is obtained from thin films of cerium oxide and titanium oxide coatings, thin coatings. And so we have in between, and the other side of the electrode, this is one electrode, then we have the other electrode. The other electrode is also ITO on glass, and with electrochromic coating, which can be tungsten oxide or niobium oxide. So in between, we accommodate our membranes. We press them, everything, clamp them, everything together, and we measure and we apply the voltage to see the change of color. So these electrochromic devices now, nowadays, they are more available. As we can see in the market, they're mostly seen in cars, more expensive, more luxurious cars, but still available for common people. So the cars like Ford Fusion, or the biggest car, or some Toyota Corolla, they already have these devices as rear view mirrors, which were developed by Gentex in Michigan, United States. And and other cars. BMW, they have, initially there were only installed in the more luxurious cars. Nowadays they're in more common cars. So we see that this kind of devices is coming closer to us, and probably we will soon, maybe in few years, we will have more of this kind of devices in our surroundings, like in our houses, or some other our buildings in our cities. So we also see many of us travel worldwide, and we see these devices in airplanes. The airplane, which is equipped with this windows, electrochromic windows, is Dreamliner from Boeing 787. So it is also produced by, these windows are also produced by Gentex. And there is growing number of companies that are producing and investing money to develop this kind of devices. There are also sunglasses. So what about polymer electrolytes? Today I decided to show you some more recent work about DNA-based solid polymer electrolytes membranes. DNA is not very when I say to people that I am working with DNA, they're a little bit afraid. But I say also that it resembles DNA we have for this research, which has considerable mass weight. So this is kind of, it looks like cotton. So the problem is that it smells not very good, but the appearance is like cotton. And it is produced from waste in salmon processing industry in Japan. So actually we can obtain DNA in our labs very easily, but not always this the molecular mass is high. And for our application, this is very important because of this we can obtain the membranes. So we made the samples of DNA, we plasticized it with glycerol and added a little bit of lithium perchlorate. Actually, we made tests with different quantities of lithium perchlorate, and we observed that the ionic conductivities were not very high. So actually at room temperature, it was 10⁻⁷. And as the temperature went up, the ionic conductivity went up too. So, but it was interesting that it was still stable at high temperatures. And we made the electrochromic device with these membranes. We made two kinds of electrochromic devices with DNA polymer-based polymer electrolyte and Prussian blue as electrochromic material, and also tungsten oxide as electrochromic material. And here we can see that these devices didn't work really well. Actually, it worked. We had the color changes, but it was very, very small color change when we see here in the case of, it is not the, sorry for this tungsten oxide. Actually, this picture is from tungsten oxide. So we have here the change about 3.5% at 686 nanometers. And here we have 7, so double of Prussian blue. And usually we have, with other polymer electrolytes, we have bigger changes. So we were a little bit, we wanted to know what happened. And for that, we analyzed the contact angles of the samples. So for the first time, we measured the water angle contact of the ECD electrodes, as we can see here, of Prussian blue on ITO glass, cerium titanium oxide on ITO glass, and tungsten oxide on ITO glass. And we wanted to evaluate wettability point to see the affinity between the electrode and the polymer electrolyte. And as we can see from this data we obtained, the water angle contact was around 70 for different media for both, for Prussian blue and for tungsten oxide. So it suggested that both films are more hydrophobic. Therefore, they have a lower chemical affinity for DNA when compared with cerium titanium oxide. We did also surface, we measured also the surface free energy, and we observed that this surface free energy value is higher for is higher for cerium titanium oxide than for electrochromic coatings. So the large contact angle. So from these measurements, we concluded that for large contact angle evidences a low solid surface energy or chemical affinity between the liquid and the solid surface. So in our case, the interaction between the electrodes and the SPF and solid polymer electrolyte was very weak. So this was the reason why why we got probably so low transmittance difference in our ECDs.
Professor Paulika, sorry to interrupt. You have about a couple of minutes, 5 minutes maximum.
Okay, so I will be faster.
Okay.
So then the other work we did, it was with hydroxypropyl cellulose. This was very nice work, and we patented it. This work was why it was very interesting, because hydroxypropyl cellulose is soluble in organic solvent. So in this case, we dissolved it in dichloromethane as solvent, and we got the values. We add some other additives. We add polyethylene glycol, and also for dodecylbenzyl sulfonic acid. And we got very high ionic conductivity values ranging from 10-5 to 10-4 in between 25 and 50 degrees. So this is why it is interesting, because in some devices the water can damage the device. So this was the work to show that it is possible to do to use natural macromolecule dissolved in organic solvent. And as we see in, we also did electrochromic devices, and we got about 35% at 650 nanometers in the case of Prussian blue, and in the case of polyaniline, we made the device with polyaniline. We got the color change between 20 in the range of 30% too. So here's are some stability tests during 600 seconds, and we can see that it works nice. So it is very promising material to do to work with. The more recent work also is the work with gum arabic blended with polyvinyl alcohol, and with addition of a little bit of acetic acid. Actually, in this case, it's not so a little bit. It's a little much of acetic acid. We also displayed the ionic conductivity of 10-5 Siemens per centimeter, and we didn't do any electrochromic devices because this work was is more recent, and during this pandemic we had our labs closed. So, but as we can see, the transparency of these membranes are very good. This is the other work with alginate-based nanocomposites containing montmorillonite clay. And in this case, we got the ionic conductivity reaching the values 10-2 Siemens per centimeter. So there were a little bit about about the solid polymer electrolytes. We also, in our work, developed this active color change ECD, which we call a chameleon. And this is a movie. There is no time to go, but this chameleon, it changes the color from yellow to green. So it has a very good application and very promising application in military field. And it was also recently patented. So, this is active. So this is quite interesting. First active electrochromic devices. So there are some memory tests we did of with this device. Here are some examples of color change, so we can modulate the change. And also we propose to do this digital color management using the digital color management system to use it for military purposes. So the idea here is to take a picture, analyze the picture in the terms of color parameters, and then transform this to the potential, applied potential, so we can change the device and the pixels. We can use them as pixels, and we can change actively in time in the field. So conclusions. My conclusions are that there is a possibility to obtain ionically conducting membranes with natural macromolecules. My co-workers and my friends from Malaysia, from India, they work with this kind of membranes, so they know this very well. There is a possibility to blend natural macromolecules with synthetic biodegradable polymers or clays. So there is This is also very nice, interesting topic. Chemically stable and are successfully applied in electrochemical devices. And also, the most important thing is that they're environmentally friendly. So finally, I would like to acknowledge all my coworkers and my friends for scientific discussions and science sponsoring agencies for funds to develop our research. So thank you very much for your attention.
Thank you, Professor Paulika, for such a wonderful lecture where I think you covered diverse applications of from electrochromic to membranes. So it's very exciting actually. So I hope there will be some questions from the audience. So this session is now open for any quick questions. Yeah, I can only see one question.
So, yeah, actually, yes and no. So no, because you know, it doesn't oxidize. The only problem is for yes is because they're natural macromolecules, so they're susceptible for the fungus attack or some microorganism attacks. So the humidity and heat, you know, especially in our country and your country too, you know, we have to to prevent from these factors. So sometimes principally now, when we have a rain season, and it is raining every day and a lot. So we have problems. We have problems. We have to turn on our air conditioning, and we have to put in the glove box because it attacks, you know. And we see this clearly when we work with hydrogels.
Can I ask? Dr. Chakravarti, can I ask?
Any more questions?
Yeah, can I ask?
Yeah, sure.
Professor Paulika, thank you for such a nice presentation. My question is regarding the humidity or other temperature fluctuation on the biopolymers. We had used Galan gum earlier in our dye-sensitized solar cells. But once you use in any of the biopolymers for that matter in the devices, what is your opinion about the humidity fluctuation, temperature fluctuation?
Yeah, this is very good question. Yeah, and actually, when I didn't mention this, but when we do the ionic conductivity measurements, we always heat, and also we apply a little bit vacuum. So we try to avoid the humidity entrance, and we put our samples in closed containers, you know. So when we assemble the devices, we soon after we assemble them, we seal them. So there is I think we avoid the humidity. But if you look at some works, they're a little bit old works about some electrochromic coatings. A little bit of humidity is desirable. So it increases the electrochemical reactions that occur in these systems. So you know, the problem is to wait, you know, how much it can be, because natural polymers, they tend to absorb humidity, and actually the modified polymers, actually they're derivatives, so they tend to absorb humidity, and who works with that, he knows. So certainly we have to avoid them, but not not to zero.
Correct.
Not
Correct.
to end,
Correct.
not totally.
Yes. Thank you.
Okay. So once again, I would like to thank Professor Paulika, and
Thank you
I would
very
like to
much.
welcome. I'd like to welcome our new speaker, next speaker. I have seen him waiting for quite some time. So it's my pleasure to welcome Dr. Diego Santos. Dr. Santos, you may start sharing your slides, please. Okay. So Dr. Santos is an invited assistant professor at Institute Superior Technio, I think it's IST, University of Lisboa in Portugal.
Yeah.
Researcher in the Center of Physics and Engineering of Advanced Materials, which they call CEFAMA, studying electrodes and membranes for application in direct liquid fuel cells. So this is the new topic that we are going to learn this time, direct liquid fuel cells. Dr. Santos got his PhD in electrochemistry in 2009, focusing on the development of direct borohydride fuel cells, DBFCs. He did a postdoc in chemical engineering to study materials for hydrogen production by alkaline water electrolysis. Then he did another postdoc in material science and engineering to develop cathodes for DBFCs. And then he developed low-cost electrocatalysts for low-temperature fuel cells. He has authored 120 journal papers and 90 conference proceedings. He has also delivered more than 50 conference presentations, and with a current age index of 29. He is a member of several international societies and serves as reviewer for multiple journals. And he is also supervising several PhD students, supervised some PhD students as well as MSc and MTech students as well. Okay, so with this, I would welcome Dr. Santos once again to this session, the last speaker of this session, but not the least, I hope. I hope people will be enjoying and will be able to learn some new exciting science from this session. Thank you. Welcome.
Thank you, Dr. Amit, for your nice presentation. And I also want to thank Professor Neelam Srivastava for inviting me to present at this conference. So today I will talk about efficient green hydrogen production by alkaline water electrolysis. In fact, we have several works on the development of catalysts for direct liquid fuel cells, but we also have a line of research related with electrocatalysis of water electrolysis, and that is a topic that I'm going to discuss here today. So this work that we are doing on hydrogen production on this specific topic I'm talking today is being done in collaboration with our group in Lisboa, and also with the two research groups in Serbia, with the University of Novi Sad and the University of Belgrade. So this is just a picture of our group in Lisbon, in the Instituto Superior Técnico, Universidade de Lisboa, in Portugal. And this is a picture that we managed to get right before this horrible pandemic started, and in a moment where we could all be together attending conferences. So our group works in electrochemical energy conversion, mainly focused on the development of electrocatalysts for fuel cell reactions and for water electrolysis. So related with water electrolysis, our motivation, of course, is related on the hydrogen production as a solution to the current energy crisis. We know that hydrogen is the compound with the highest gravimetric energy density. Its energy density per mass, it's about 3 times that of diesel or gasoline. It's a compound which is environmentally friendly. It has been demonstrated to be safe in most applications and can be used to power fuel cell electric vehicles. So the idea of using hydrogen is based on this concept of the hydrogen economy, on the use of hydrogen as an energy vector. And hydrogen, of course, on this cycle can be used to power buses, like to be used in mobility, generate electricity and heat whenever it's needed. Its combustion generates water, and then from this water, we can apply renewable energy sources to promote electrolysis and then get more hydrogen and which has to be stored. I will not focus today on the hydrogen storage, which is a big issue, one of the problems related with this hydrogen economy, but it is something under development, under study, and under improvement to establish this greener economy. So the basis of this is the hydrogen production. Of course, we know that most hydrogen is still produced by steam methane reforming. That is based on fossil fuels. It has large CO2 emissions. So if we want to go green, hydrogen has to be produced by water electrolysis. So in fact, if we talk about green hydrogen, we are talking about hydrogen produced by water electrolysis, in which the electricity that is being used for electrolysis is only based from renewable energy sources. So we know that water electrolysis, in principle, it's a simple process. Water is something abundant, not dependent on fossil fuels, does not emit any carbon emissions. So it has several advantages, but it also has some disadvantages. And at this point, the major problems are related with the energy efficiency of the electrolysis, which is still relatively limited. And those problems are related with the stability of the electrode materials, with the low kinetics of the electrode reactions, the hydrogen evolution reaction, and mainly the oxygen evolution reaction, which is the reaction with the sluggish kinetics. It's also related with the low conductivity of the alkaline aqueous solutions. That has to be something that we will discuss here today. And also problems relate with the removal of gas bubbles, because if you see that gas bubbles are getting absorbed on the electrode surface, of course, that will also decrease the active area for the electrode reactions. So at the industrial level, this technology is already working. These are the main three types of electrolyzers. Solid oxide electrolysis cell is still under development. It's not being applied. It works at high temperatures. We have some presentations on this conference that were on solid oxide fuel cells, and this is basically the opposite reactions of the solid oxide fuel cells on this solid oxide electrolysis cell. But it's very promising, but it's still not being used. These two on the left side are the ones that are currently being employed at the industrial level, the alkaline electrolysis and the PEM electrolysis. Alkaline is the most mature technology. It's been here for over 60 years. People sometimes discuss hydrogen as being a very recent technology, but this is technology that is already been working for a long time. This is mature and trustable technology for hydrogen production. PEM electrolysis appears as quite competitive with higher purity of hydrogen and higher ability to work with fluctuating energy sources, because the cold start of this PEM electrolyzer is lower, like it's faster than the one from the alkaline electrolysis. But still, since this process is the most mature, the most trustable, a lot of projects, at least starting in Portugal, that have received funding to promote this hydrogen boom in Portugal are betting on the alkaline electrolysis, because it's the one that is known for a long time, and it's already working well, and it's more mature. So our work, it's also focused on the alkaline electrolysis, on the improvement of this technology. We are focusing on both electrode reactions, both the hydrogen and the oxygen evolution reactions in alkaline media. As for the hydrogen evolution reaction, the process is very well known. So it always starts like with this Volmer step, which is related with the absorption of the water on the electrode. And then you get first an hydrogen absorbed at the metal surface, and this is called like the Volmer step, which is followed either by the Tafel step or the Airovsky step. So the Tafel step means like two adsorbed hydrogens get together to form one hydrogen molecule, or the Airovsky step means like one other molecule, water molecule comes and is reduced at the electrode surface and generates the hydrogen molecule. So this process is well known. As for the oxygen evolution reaction, the process involves 4 electrons, and this is like a multi-step reaction in which 1 electron is exchanged at a time. So that means like since each step is not 100% efficient, of course, the overall efficiency will be much slower. Like it means the kinetics of this process will be much lower, and that's why we know that the oxygen evolution reaction, as it has the sluggish kinetics, it often is more problematic, and it will control the rate of the water electrolysis overall reaction. So in our group, for some time, we are working on electrocatalysis of hydrogen evolution and oxygen evolution reactions. The requirements for this electrocatalysis mean lowering the overpotentials for both hydrogen evolution and oxygen evolution reactions to maintain the stability of the electrode's activity and to lower the electrolysis process price. So this problem of the stability is quite critical because a lot of studies reporting electrocatalysts for these reactions sometimes do not demonstrate stability for a long time. So they show good activity in the beginning, but if you work with them for after some hours, this stability comes down and they cannot be applied at the industrial level. So this is something that has to be worked. And for that, our group for several years is working on the development of efficient electrode materials that have both high activity and stability for these reactions. But in the last few years, we have adopted another line of research that has been related with the improvement of the properties of the electrolyte solution, not just focused on the electrode materials, but also focused on the electrolyte solutions. And for that, we decided to test additives on the electrolyte solutions. Room temperature ionic liquids have different applications, and we wanted to also test them and investigate what would be their effect on hydrogen evolution reaction or on oxygen evolution reaction. So these ionic liquids basically are salts that melt at room temperature. They are known as ring solvents. They have very good stability. They have high ionic conductivity, which is very important for electrochemistry studies. And they are already been used in different electrochemical applications. And one thing very important is that they are able to modify the electrolyte interface. So what we wanted to test on this study was their effect on the hydrogen evolution and oxygen evolution reactions just by adding very small amounts of the ionic liquid. There are some studies that are simply based on electrolysis in ionic liquids. That's not what we think it's important. That's not the way. The idea is to use the alkaline electrolyte, the KOH electrolyte, which is the one typically used in industrial alkaline electrolysis, but with very small amounts of these ionic liquids. We're talking about 1 or 2% in volume. So in the first study, we we first tested these commercial ionic liquids where we used the 1-ethyl 3-methyl imidazole cation, and we tested with different anions. We could see a beneficial effect of the addition of the ionic liquid on the hydrogen evolution reaction, but since the anions were only the anions were different, we could not really assess the main advantage because it's in fact the cation that mostly affects the hydrogen evolution reaction, because it's the cation that will absorb at the interface between the electrode and the electrolyte, and of course it will affect the hydrogen evolution reaction. So in the following study, what we did was to maintain the same anion. Here we use bromide, but with slightly different cations. So we use one here, like in this case, with an ethyl chain, and in the other with a butyl chain, slightly larger alkyl chain. So in this first study that we did, well, first not first, but this last one, the previous to the one that I'm presenting here after it, which is the most recent. But in this one, we could clearly see that the addition of the room temperature ionic liquid in 2 volume percent lead to substantially increase the cathodic currents. So what we do in the lab is polarization curves by linear scan voltammetry, and these cathodic polarization curves show a significant increase in the cathodic currents compared with just the KOH solution without the addition of the ionic liquid. So based on this, we can calculate we can make the TAFEL analysis with these TAFEL slopes. We are with these TAFEL plots, we are able to calculate the TAFEL slopes, the exchange current densities, the charge transfer coefficients, and we could see that there is clearly a change in the hydrogen evolution reaction kinetics. So we see a beneficial effect of the addition of the ionic liquid. We also use the electrochemical impedance spectroscopy to check what was the effect of the ionic liquids. And in both 1 and 2 volume percent additions, we saw a significant decrease of the overall impedance of the system. So with 1%, we see here a decrease of the semicircle in the Nyquist plots. They are much smaller after the addition of 1% compared with just the simple KOH solution with no addition. And when we go to 2% ionic liquid, you see a very big decrease compared with the initial situation. So we can clearly see that this decreases the impedance of the system. So this previous study shows us that higher current densities were always obtained, or in most cases, when they were obtained after the addition of the potential liquids. The impedance always showed a remarkable decrease in the overall impedance of the system after the addition of the room temperature ionic liquids, and this is related with the absorption of the ion of the electrolyte. So on this new study, we asked our colleagues in Novi Sad not just to send us some commercial ionic liquids to test, so we tested some new ones that had to be tested before, but also some tailor-made ionic liquids. So what they did was not only to provide these commercial ionic liquids with ethyl and butyl chain here on these methylimidazole-based cations, but also to modify them and prepare these homemade ionic liquids with methoxyethyl and ethoxyethyl change to check what would be the effects of these modifications. So all of them have this fluoride anion in common, and the cation was slightly different. So they prepared the ionic liquids in Novi Sad, and we did in Lisbon the electrochemical characterization done with a simple 3-electrode arrangement with platinum electrodes.
Santos, sorry to interrupt.
Yeah.
You have about 5 minutes maximum.
Okay, no problem. Thank you. We did the characterization in KOH solution, which is the typical electrolyte in alkaline electrolysis before and after the addition with just 1% of ionic liquid. Besides this, we also wanted to do a different approach here, where we also tested in a small cell with nickel electrodes, because nickel electrodes are commonly used in alkaline water electrolysis, opposite from PEM electrolysis that requires normally noble metal electrodes. Alkaline electrolysis allows the use of transition metal based electrodes, which are much cheaper. So we tested with these nickel electrodes and measured the gas that was produced, so that we could also check if it was improved with the addition of the ionic. So just to quickly show you these the voltammetric studies we did at 2 temperatures. This was also a difference between to our previous studies, where we also here we wanted to test the effect of temperature. So we saw that both at room temperature and at 80 degrees Celsius, there was always an increase, substantial increase of the cathodic currents for hydrogen evolution reaction after the addition of the ionic liquids. And for oxygen evolution reaction, we could also see an improvement at room temperature, but not at higher temperature. And this is related with degradation of the ionic liquids that we tested after after a given temperature. We saw that around 40-45 degrees Celsius, they became to have some problems with degradation, and at high temperatures, they show a detrimental effect on oxygen evolution reaction. Although for hydrogen evolution reaction, they always seem to be good, not for oxygen evolution reaction if that is not true. So just to show you some the kinetic parameters that then we calculated from TAFEL analysis, we saw a significant increase of the exchange current densities after the ionic liquid addition. Based on, we also saw the increase of currents. Also for the oxygen evolution reaction, we could see that there was beneficial effects at room temperature, but not at the 80 degrees Celsius, as I mentioned. We also did some studies on the stability of these materials. They were stable for hydrogen evolution reaction, but for oxygen evolution reaction, the results were also, as I mentioned, at 80 degrees Celsius, were not so interesting. So these materials can be very effective, but if we want to do electrolysis at lower temperatures. Just to show you the volume measurement that we did, the volume, I mean, both we measured simultaneously the produced hydrogen and oxygen. We did not separate the gases in the cell. And when we did constant current measurement on these small electrolyzer, both with and without ionic liquid, we didn't see big differences, but we could see increase of the volume of hydrogen produced when we did measurements at constant potential in the cell. Just to summarize the results, so we could see that there was some degradation of the ionic liquids for temperatures higher than 40 degrees Celsius. And that had a negative effect on the oxygen evolution reaction kinetics. This should be OER, not HDR. But even with that negative effect, the addition always increased the hydrogen evolution reaction kinetics. So by discussing with some colleagues, we proposed some properties from tailor-made ionic liquids. And well, based also on the literature and some discussions we're having, the next steps would be to test also with the bulky anion. The idea is also that if the cation can modify the properties in the interface and improve the hydrogen evolution reaction, we also need a bulky anion that can also modify the properties on the oxygen evolution reaction side. So that would be the next step. Also testing some materials with body parts, like both polar and non-polar, that can also help the ions and to move the solvation layer and also improve the kinetics, and also testing compounds that can act as a hydroxide donor and acceptance that can also improve. So I just want to thank the funding from both Portugal and Serbia to this work, and thank you very much for your attention.
Thank you, Professor Santos, for such a wonderful, and especially what I liked about it is that even for a beginner, from your first 5 minutes of in the introduction part, somebody can think of moving to your research area. Even I am thinking whether I should start researching on this topic as well. So I hope students, especially the beginners, can get excited about the topic, and also they can. I can already see some questions have been raised. So I open the session. The session is open for questions, and I already see some questions, and I can read some questions from there. Does the RTIL remains unaffected during electrolysis? That is one question asked by Dr. P.K. Shukla.
So what we saw is that it had good behavior, and we could see some stability at low temperature. So, and when we did experiments at 25, 35, and up to 40, we could see stability on currents and on the volume of gas that was being produced. So based on these experiments we did, we could see stability. Clearly, for higher temperatures, these ionic liquids we tested on this study, they are not stable. So if we want to implement these results, these that we found, these specific ionic liquids from the blood study applications can only be used if alkaline electrolysis is run at room temperature. So as I demonstrated, like for hydrogen evolution reaction, they work fine even at higher temperatures, but they show a detrimental effect on oxygen evolution reaction at higher temperatures. So in that case, I wasn't fine. It doesn't mean that there are other ionic liquids that have other stability, and that's what we want to look for. And probably if we can find those ionic liquids with the anion that can also improve the oxygen evolution reaction side, we can increase the temperature and then do electrolysis at higher temperature at the stable rate.
Okay, there is one more question here. Why reference electrode is used in the case of EIS?
What is the reference?
Why, in the case of EIS, do we use reference electrode? That is the question being asked.
So when we are controlling the potentials, these are all done in 3 electrode electrochemical cells. So in 3 electrode electrochemical cells, you always need a working electrode, a counter electrode, and a reference electrode. And with the reference electrode, you are able to control what is the potential of your working electrode. So the counter electrode is there, but it always should have a much larger area than the working electrode, so it does not affect the reaction occurring at the working electrode. And on EIS, on electrochemical impedance spectroscopy, you change the potential of the working electrode, and to know what is the potentials that you are changing, you always need to have a reference electrode connected to the potentiostat, so that you know what are the amplitudes or what are the potentials that you are scanning to measure the corresponding currency.
Yeah. So is there any more question? Okay, madam has one question. Okay.
Yeah. Yeah. So we did not do that cost analysis study, but I think that we saw that with these small amounts we could improve. The thing is that the ionic liquid is supposed not to be consumed during the process. So it is likely that you are consuming water during water electrolysis for the hydrogen and oxygen production, but the ionic liquid is supposed to not be consumed. So it will stay there, just modifying the electrolytic interface. So of course you will need to do some backup of ionic liquid, but that is something that we still haven't been reached that point. But it will not mean that for each liter you will need to consume 10 milliliters. We assume that it will stay there, and so the consumption will be lower than that. Well, at the industrial level, we always have continuous feeding of water. So in that case, the concentration will remain constant. At fundamental studies in our lab, the consumption of water is not relevant, because since we are doing fundamental studies, we that doesn't mean that it would take a long time to see a decrease on the hydrogen evolution on the water to decrease, because we are working with the small electrode areas, so the consumption is not significant. It remains fine. Okay, thank you.
So thank you once again, Dr. Santos, and I thank all the participants, all the audience, all the people who have interacted with you through questions in the entire session, for being there and making this session successful. And once again, Professor Srivastav for organizing the entire thing so nicely. And I think I have taken little extra time from Professor Srivastav's expectation. One speaker has not presented, so it was probably expected that the session will end faster. But I think somehow due to the interaction, it did not happen so early. Okay. Sure. So this is my request to all the audience who are present in this meeting right now, that a link for the YouTube link for the video is just now shared in the chat box. So you can click on the link to see the lecture of Professor Bruno Mena. So I'm going to read out the CV of her so that you know what is she about and what is the lecture about. So Professor Bruno Mena has graduated in chemistry in 1998 obtained the license and status of professional chemist in 1999. She was awarded a research fellowship in membrane materials and operations in 1999 from the Institute on Membrane and Technology, ITM, former IRMERC, National Research Council of Italy, CNR, and a PhD in Chemical Engineering and Materials in 2005 from the University of Calabria. In February 2014, and for the second time in October 2018, she obtained the qualification of Associate Professor in Chemical Fundamentals of Technologies from the Italian Ministry for Instruction, University and Research, MIUR. Her research activities relate to membrane science and technology for sustainable processes. She is author of more than 70 scientific papers in peer-reviewed journals, one book, more than 90 contributions published in conferences, 10 chapters of scientific books, editor of one book on the advanced membrane materials, guest editor of 9 special issues in different peer-reviewed international journals, and she is also a member of the editorial boards for a number of international journals. She has been an invited speaker also for different number of conferences. She also serves reviewers for many scientific bodies and expert evaluator for international funding agencies. So you can see that Professor Bonomena has done a lot of work on membrane science. So if you are interested in membrane science, then definitely it's worth to have a look at the video that she has shared with us, because in spite of her busy schedule, she could not attend the presentation live, but she has done the effort to record a video and share with us. So that's very important for us to give respect, that we should have, if we can spare some time to go through the video, that will make her effort successful. Okay, thank you all. My pleasure. Thank you.
Yeah. Yes. Let me first look at whether all the experts are available. Professor Rajan Jose, if he is available. May not be available. Dr. Pritam Singh. I can see our friend Professor R.K. Gupta. He is there. Yes, and Professor Mohanlal Verma. Oh, yes, so nice. Professor S.P. Pandey. Sri Prakash Pandey.
Yes, sir.
Okay, sir. And Professor Piyush Kumar Sonkar. Okay. So the participants, please note that we have gone through, all the experts have gone through your video recording that is already uploaded. Therefore, don't waste time in presenting the introduction and all those things. Directly come down to the final findings that you want to present and discuss. We are bound to cut the presentation at 5 minutes. We will not be able to allow it more than 5 minutes at any cost, because you must have seen the long list. This will continue till 8 in night. We are already 38 minutes late now. All right. So if perchance your network doesn't work, let us know that it is not working, or if it is at all not working, we will put it at the end again and we will scroll it down. All right. Don't try to jump in between, and please start sharing, discuss, close it. All right. First presenter is Dr. Sujit Kumar Chaurasia. We can see Dr. Sujit here.
Yes, sir. I am present.
Yeah, please share.
Yes, sir. My slide is visible.
Yes, it is visible.
First of all, I would like to thank the convener of the conference, Professor Bhaskar Bhattacharya sir and Professor Neelam Srivastava madam, for giving me this opportunity to present my work here. Myself is Dr. Sujit Kumar Chaurasia, working as assistant professor at the Center for Nanoscience and Technology, VVS Purvanchal University, Jaunpur. The title of my presentation is the impact of in situ fault silica nanospheres on physicochemical and ionic transport property of PO-based polymer electrolytes. My presentation is divided into the following section. First one is the introduction, in which I will briefly describe about the solid state electrochemical devices, and then electrolytes, in which the different types of the electrolytes, and how the organic inorganic hybrid electrolytes will form, and the method of preparation, and some lab experimental results, and last one discussion. As you know that in the present scenario, energy generation and storage is one of the major problem of the current world because of the enormous consumption of the fossil fuel. Therefore, we need a clean energy resources. So there is an electrochemical devices generally consist of an electrode and electrolyte material. And so therefore, in order to get a high performance devices, we need a new functional material. My present work is basically based on the organic inorganic hybrid electrolytes. Why we make these hybrid material? Okay.
Yeah.
Okay. Yes. Uh, there are two synthesis routes for the preparation of these hybrid materials. First one is the building blocks, in which the solution building, melt blending method, and powder building, and in situ synthesis followed by the sol gel technique. This is the organic component, in which we have taken polymer PO and lithium salt, and these are our synthesized hybrid material. This is the X-ray diffraction pattern of the pure PO along with hybrid electrolytes. Here we can see that uh, the the diffraction pattern of the pure PO riding over a broad halo. This halo is increasing with the concentration of the lithium salt. So we can see that the emulsivity of the membrane increases, and this is the some thermal techniques are used for the characterization of membrane. This is the DSC thermogram, which shows that, and this is the thermogravimetric analysis. We can see that these hybrid electrolytes are thermally stable more than 280 degrees centigrade. This is the ATR spectroscopic analysis, which confirms the formation in order to find out the possible complexation between the constituent between the organic and inorganic hybrids. Uh, the FTR spectroscopy shows the formation of SiOC and SiOS group by enabling the vibrational band appearing in 1023 and 791 wave number, as well as the complexation of the polar group of PO with the lithium cation of the dopants are. This is the same micrograph our synthesized hybrid material, which shows that the layered structure along with the some crystalline domains consisting of the silica nanoparticle embedded in the layers of the polymer PO matrix. Here we can clearly see the formation of the SiO2 nanospheres. And this is the 10 micrograph over the pure SiO2 as well as the hybrid electrolyte containing 5% of the lithium salt. Here we can see that the SiO2 nanoparticles are clearly seen here. This size of these particles are approximately 15 to 20 nanometer in size. This is the temperature dependent ionic conductivity. Here we can see that the ionic conductivity increases with increasing the temperature and follows Arrhenius type of the activated process. Here we can see that the activation energy decreases with increasing the lithium salt content in the membrane, which shows that the higher salt loading samples can follow the easier ionic transport behavior. This is the electrochemical measurement of our synthesized sample. This is the LSV profile. Here is our hybrid electrolyte film containing 20% of the lithium salt is placed between the stainless steel electrode and lithium foil, and we can get the electrochemical stability window of 5.2 volt. And using the combined AC-DC technique, we have also measured the cationic lithium ion cationic transport number, which is approximately 0.39. And this, at last, I will conclude my results. In the present investigation, organic inorganic hybrid electrolyte membrane, by combining the organic polymer PO and inorganic silica nanospheres, by in situ method dispersed in the polymer electrolytes and characterized by different experimental technique. This shows the formation of the silica nanospheres of 15 to 10 to 20 nanometer diameter, as observed by the same and TEM analysis. DSC results shows the decrease in melting temperature and degree of crystallinity with the salt content, and ionic conductivity of these hybrid electrolytes is increases with the lithium salt content and found to be 4.6 into 10 to the power minus 6 Siemens per centimeter at room temperature, and the cationic transport number is found to be 0.39. Thanks for your kind attention.
Good, very good. Any question or any comment?
Yes. So you use the Sol-Gel, you use Sol-Gel method for conductive.
The solution cast technique followed by the Sol-Gel method, as discussed here. The first organic part will be prepared by dissolving the polymer, lithium salt, and then inorganic part is separately prepared by the tetraethyl orthis silicate, and glymo is used as a cross-linking agent between organic and inorganic, organic part and inorganic part.
If you don't use, then what will happen? Glymo, if you don't use glymo.
I use glymo. Glymo is this, which structure is here. This bond is broken during the synthesis process, and there is some cross linking between the organic part and inorganic part have been achieved using this. This is glymo used as a cross linker
Only.
Or for the formation of the gel.
For the formation of gel.
Basically, it is a Sol-Gel method actually.
Sol-Gel method, and
then you are drying. Then you are drying.
Actually, we prepared the SiO2 nanoparticle by in situ method within the solution.
From TOS you are getting. This is in
TOS. We hydrolyze the TOS and some acids and some waters, and then hydrolysis.
So it is just a Sol-Gel method.
Just a Sol-Gel method.
Yes, because you have to dry. Then it will give you a film. That's it.
Yes. No, sir. Actually, first we have taken the use the solution cast technique here, and this is another inorganic part are prepared separately and then mixed these two solution here.
Okay.
And then we does not add the external filler particle. By the in situ technique, they can be dispersed inside the matrix, SiO2 matrix.
If you mix together, what will happen? If you mix together PEO, TOS, LITF, glymo all together.
भैया रविंदर भैया,
हाँ,
मैं ये कह रहा हूँ वो मेल में लिख के भेज देगा, बच्चे को क्यों डरा रहे हैं?
Then it is a very good work. Good work. Actually, he synthesized silica using this Sol-Gel route, and that was added to the PEO-LI system.
Yeah.
It is a good work. Good work.
Yeah.
Badhiya, Sujit.
But it is possible to get higher conductivity.
Yes,
it is a composite. Ultimately, it is a composite.
The pH condition of the solution, we can tailor the size of these dispersed nanoparticles. SiO2 particles.
डॉक्टर सुजीत, इसके पहले वाला स्लाइड 1 मिनट दिखा देंगे और थोड़ा पहले मैं शायद मिस कर गया. Anyway, we will talk later.
Okay, sir. No problem.
Thank you so much.
ठीक है. Thank you.
Thank you, sir.
Next is Pawan Singh Dhapola, if he is there.
Yes, sir. My name is Sushant Kumar. I'm going to present on the behalf of him because of his health issues.
All right.
And you didn't put the video actually, Pawan.
Sorry, sir.
There is no video actually.
Yeah, sir. Actually, he was not able to make that video. That's why.
चलो कोई नहीं, प्रेजेंट कर लो सुशांत.
It's okay, no problem.
Okay. Sir. Am I visible?
Yes, it is coming slowly.
Is it visible now? Hello.
You are audible, but your presentation has not appeared so far. Your network is poor. Try once, or otherwise we will put it at the end. Huh?
Okay, sir. Okay.
Yes, it is coming. Carry on.
Oh, okay. 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 So the presentation I'm going to present on the behalf of Pawan Singh Dhapola. So it is on the development of porous carbon from polyvinyl chloride and its application in supercapacitors. So in this screen, you can see that there are three types of energy storing devices: capacitor, batteries, and supercapacitor. You can see the different mechanism, the energy storing mechanism in these figures. They follows, and the other differences you can see in this table. So this is the synthesis process which is followed to synthesize the PVC-based porous carbon. So first of all, PVC is taken as a precursor, then it is dissolved in THF. THF is tetrahydrofuran. It is a solvent. Then it is mixed in H3PO4 and COCl2 for activation. Then it is dried at 90 degrees Celsius for 2 hours. Then it is carbonized, and then it is washed, and then it is vacuum dried, and we got the doped carbon. Here we made pure carbon and also the doped carbon, and we compare both of them. So there are the results, characterization result. So in XRD pattern, you can see that at the value of 2 theta of 21.46 degree, 40.54 degree, there are two peaks showed by the pure carbon, which are corresponding to the hexagonal graphite planes. And in case of doped carbon, there are three peaks for at 41.02 degree, 43.48 degree, and 52.31 degree, which are at the planes of 222, 400, 002. And the reduction in the crest broadening in these peaks implies the defects and large graphitization degree. There is a Raman graph in which we have calculated the D by G ratio for the HCCO carbon. HCCO is the symbol for our doped carbon. It comes out to be 0.85. And we have done a BET isotherm also. So in BET, we got a BET specific surface area of 4.9 meters square gram inverse for the pure carbon, and when we do the BET for the doped carbon, it comes out to be 738.283 meters square per gram, which is very high. And both samples does not have micropores in it, since the N2 adsorption isotherm doesn't show any raise in pressure area at P by P naught greater than 0.9.
Sorry, Sushant. Directly come on conclusion. Just by showing video.
Okay, sir. Okay.
Yeah.
Okay, sir. Okay, so here is the in this slide you can see the conclusion and also the electrochemical results. So here we our carbon we have made a supercapacitor by using the PVC based carbon and ionic liquid 1-ethyl 3-methyl imidazolium thiocyanate ionic liquid as the electrolyte. And this supercapacitor shows this 127.4 farad per gram capacitance at 5 millivolt per second. So I have concluded that activated carbon are easy processable and can be efficiently synthesized in laboratory scale from polymers. And activated carbon, porous carbon, very efficient material for supercapacitor. As we can see that it is showing a very good capacitance after 15 days also. So here we use low viscosity ionic liquid as the electrolyte material. Thank you.
ये आपके कार्बन का जो रामन आपने दिखाया है सुशांत, उस पे इतने सारे पीक किस चीज के हैं?
सर ये जो
जी
सर इसमें
HCCO is showing only 2 peaks. That is very nice, but in
Yes, sir.
carbon you have got too many bands in Raman. You should check for its purity.
Okay, sir.
Okay, there must be something very nice going on. Your XRD is very clear, but Raman is showing something very interesting.
Oh.
Maybe impurity.
Maybe.
आई थिंक सर वो इस समय इसलिए कमेंट नहीं कर सकता कि नाउ साहू इज कोविड पॉजिटिव।
Yes.
और
first.
और वो पवन भी
पवन का तो कुछ और प्रॉब्लम है,
वो भी आइसोलेट हो गया है। मुझे लगता है कि इसका जवाब सर पवन के पास होगा।
नहीं, बहुत अच्छा है।
Professor Bhattacharya, I want to request one thing to the experts. Please fill the marks directly in the Excel file, and the moment it ends, immediately
we need the result.
Immediately send it to the group experts.
Yes.
But unfortunately, we don't have the Excel file.
Excel file I have already shared, the same one in which you are.
I think Professor already yes shared.
So you also have the copy shared. Doesn't mean that it is a hard copy which came to me. You must be having that copy, na?
गुप्ता जी बना लो, आपने तो शेयर किया था। Thank you, Sushant. Meanwhile, let us call Dr. Vijayata Pal.
Hello.
Yeah, please start presenting.
Good evening. Hello, good evening.
Yeah, yes.
Am I audible?
Yes, you are audible. थोड़ा जोर से बोलिएगा.
Yeah. My screen is visible?
Yes, it is visible.
Okay. A very good evening to all of you. My name is Vijayata. I'm working from School of Material Science and Technology at IIT BHU. Today I'm going to talk about structure, microstructure, and dielectric properties of lanthanum nickel magnetite double perovskite ceramic. These are the overview or outline of my presentation. First, I would like to briefly introduce about the background, then objective, experimental method which has been adopted to prepare the sample, then result and discussion. And I'm working double perovskite materials. And here,
Vijayata, kindly go to the result.
Okay.
We have already declared that here you have to only present the results.
Yeah.
See,
Okay.
after 5 minutes, we will be bound to close it.
Okay, sir.
So please come down to your results.
Okay. Let me talk about the objective. We have tried to propose the design to fabricate the lanthanum nickel magnetite double perovskite materials by using a high energy ball bearing method. Then a detailed investigation on structure, phase formation, surface morphology, and electrical properties has been investigated for suitable technology application. The process parameters like stability, calcination temperature, centering temperatures with the appropriate time were optimized separately for the design systems. Here the experimental method, which is not discussed here. And now coming to the result and discussion, here we can see here the X-ray diffraction pattern of the double perovskite materials, which is calcined at 3 different temperatures, 800, 900, and 1000. From the X-ray diffraction that we have observed that all the samples are single phase structure And all XRD shows that XRD patterns indexed on the basis of monoclinic structure, basically. In order to confirm the structure and symmetry, furthermore the ritual refinement has been carried out, and all the ritual refinement fits well with the observed and calculated pattern of the theoretically calculated patterns of the XRD, and which is confirmed that it confirmed that the monoclinic structure of this X-ray diffraction patterns are at 3 different temperatures, which is calcium. Here the ball and stick molecular models, which is drawn with the help of CI file, crystallographic information file, which is obtained from the ritual refinement method. And this ball and stick molecular model was drawn with the help of Vesta software. And here we can see that the nickel Ni2 plus and Mn4 plus ion exhibit at the octahedral position, and in second one polyhedral position, lanthanum exhibit at the docahedral position. This is the extractive lattice information from the ritual refinement. Here the detailed lattice parameter and unit cell volume. At different calcination temperature, the unit cell volume is decreased, and the monoclinic angle is also decreased. And a very slight change in the lattice parameter has been observed with increase in the calcination temperature. This is the detailed atomic coordination positions of this monoclinic structure, which is obtained from the ritual refinement. And here we can see the variation of the crystalline size of the double crystalline materials at 3 different calcination temperature. And from the graph, we can clearly see that the crystalline size, which is obtained from the Divisorer formula, and crystalline size increases with increasing the calcination temperature. And from the insert shows the SAM micrograph of this material, which is centered at the 1450, and a granular size has been obtained, which an average grain size of this grain size is in the range of 0.8 to 0.9 micrometer. Here the temperature dependence of dielectric constant and dielectric flows property for this at high frequencies, basically. We have taken the data from 2 megahertz to 10 megahertz, and it's quite interesting that the dielectric constant and dielectric loss of this sample is almost constant up to 100 degrees centigrade. And what we observed as we increase the temperature, and as low frequency, which is up to 2 megahertz to 5 megahertz range, there are only one broad hump is observed, and while there are the 2 broad hump is observed in the frequency range at 6 megahertz to 10 megahertz at high temperature. And what would be the reason behind that? This may be explained on the basis of charge ordering of the nickel 2 plus and amine 4 plus cation. What would happen? Basically, the electronic distribution between two sides break the local inversion symmetry and thereby give the formation of polar region. And the polar region, when we apply the electric field, and that is responsible for the contribution of the high dielectric constant at high temperature, low frequency at high temperature. And below the peak temperature, dynamics of the polar region becomes slow down, thereby decreasing the dielectric constant. And this is the unique characteristic characteristics is mainly responsible for the reason of B-site ordering of 2 plus and Mn 4 plus cation. These are the summary. Basically, we have synthesized double perovskite aluminum ceramic by using a high energy ball milling method, and further phase formation, crystal structure, microstructure, and dielectric property of the system was systematically studied. And XRD shows the single phase formation without any secondary phase, and triple refinement structure analysis confirmed the monoclinic structure. and crystallized size increases with increasing the temperature. And the spherical-like grains are obtained for this material. And temperature-dependent dielectric study demonstrated the unique dielectric characteristics, which is due to the opening of nickel 2+ and carbon 4+ cation at the B side.
Good.
For your kind attention.
Thank you.
Didn't mention the size of the particle at 1450.
Wait, the 1450 is the sinking temperature.
Okay,
Actually,
I'm sorry. Okay, I got it.
The average grain size is in the range of 0.8 to 0.9 micrometer.
Okay.
Okay.
I hope you have considered the strain while calculating the size.
Yeah.
So this is for the SOFC. This double perovskite, why you have prepared? Is it for the SOFC, solid oxide fuels?
Actually, it has different production. We are going. Yes, sir. We are planning to do that.
Okay. Nice work.
Okay.
Thank you,
Next
sir.
is Manisha Chauhan.
Yes, sir.
Please share. मेरा फोटो क्यों दिखा रहे हो?
Yes, sir.
अरे यार मैं अपना फोटो देख के क्या करूंगा?
सब बढ़िया लगता है सर आपका फोटो।
अरे अंकित मानोगे नहीं तुम। आबिर साहब आज है ना?
हाँ बिल्कुल है भाई।
ठीक है। मनीषा जी, if there is any problem, we can change the serial. आपको थोड़ा बाद में कॉल करें?
No, sir. Actually, just give me 2 minutes.
2 minutes is not there, no. We have the 5 minutes. उसमें 2 minutes अगर आप ऐसे लेंगे तो you have already taken 1 minute.
आप चेक कर लीजिए, आपको मैं थोड़ी देर में फिर कॉल करता हूँ।
Okay, sir.
Okay. रघुवीर कुमार प्रजापति, if you are there.
I have started with stopwatch.
Yes, sir.
Please start presenting. जी बोलिए।
I am Raghuveer Kumar Prajapati, under supervisor Professor Horesh Kumar, Department of Physics, Institute of Science, Banaras University. I am presenting to study DC conductivity, dielectric property, composition, PVS, CS, PV, AgNO3 based on biopolymer electrolyte film. Outline. Introduction to motivational material and sample preparation, characterization, conclusion, references.
Please go to the result. Please go to the result.
Okay, ma'am. Factorization technique, the impedance method. Using the impedance method, calculate the RB. RB can be estimated from the Cole plot. So the figure is a Cole plot. Nyquist plot give the semicircle plot. So the high range resistance intercept of the real axis give the bulk resistance. The low frequency spike that due to accumulation the free charges at the electrolyte interface. The maximum conductivity is found biopolymer based electrolyte at 30 weight % salt concentration, which is the order of 10 to the power -4 Siemens per centimeter at 30 degrees centigrade. Now next, AC conductivity is AC conductivity variation of the AC conductivity sigma is AC is denoted with the frequency for the composition of the different composition, and second figure so that the different temperature. Frequency dependent conductivity in this case the experimental frequency range 4 Hz to 8 megahertz, and figure so that the three regions, the low frequency region, dispersion region, and mid frequency plateau region, and high frequency region. The high frequency region behavior represents the bulk relaxation, and low frequency dispersion region appear which arises due to the polarization effect. Hence, AC conductivity in spectra of the prepared biopolymer based electrolyte may be given by the Johnson power law. Johnson power law is so that the equation sigma AC equal to sigma DC plus A F into F to power n. Temperature dependent conductivity and relaxation frequency. Temperature dependent, first figure shows the bulk conductivity. Now second figure direct electric relaxation with frequency sample biopolymer with different composition AgNO3. This figure shows that the conductivity increasing with increasing the temperature over the Arrhenius type of behavior. Table further show that the conductivity different amount of AgNO3 x equal to 0, 10, 20, 30, 40 in a weight person, so that figure increasing DC conductivity but decreasing the activation energy. Dielectric permittivity. Dielectric permittivity is figure A and B. Epsilon dash and epsilon double dash. First figure is the real part. Now second figure is the imaginary part. Different composition AgNO3 at 30 degrees centigrade. Figure D, C and D, real and imaginary part at different temperature. It is noted that the sigma dash and sigma double dash electrolyte system, the first increasing with increasing frequency and reaches at the constant value in high frequency range at 8 megahertz. Electric modulus study. Electric modulus study, which is a very important study. M-dash spectra has a long low frequency for the AgNO dependent film as well as biopolymer based electrolyte at different temperatures. Small peak observed which is found to shift toward the high side with increasing temperature. M double dash spectra have the distinct relaxation peak shifted with AgNO3 concentration as well as by the changing the temperature to conductivity relaxation. Ionic transference number measurement. Generally, ions are actually especially the biopolymer based electrolyte figure show the ionic transference number. Ionic transference plots observe the optimized sample point 98 show that the ionic pressure. This figure is a show that the ionic transference measurement and follow the Wagner DC polarization technique was used the determination of the ionic transference number. Ionic transference number equal to the I is initial minus I the final upon the I initial. Linear shift voltammetry LSB analysis. It was to determine the electrochemical stability of an electrolyte. Figure for the plot.
Prajapati, please go.
Plot scan rates are different conclusions.
Prajapati, conclusion पे जाइए, already you have
Differences,
taken.
and thank you, ma'am.
Conclusion, please. Conclusion is the important thing. You should conclude what you have to do.
ये जो आपने
Conclusion,
एक्टिवेशन, एक मिनट, आपने BPB4 के लिए जो एक्टिवेशन एनर्जी दिखाया, what is the ion that is moving? Silver ion.
Silver salt magnesium, silver ion group.
The activation energy that you are showing is very close to proton. उसको जरा ठीक से चेक करिएगा, ठीक है?
Okay, sir.
Okay. Thank you. मेरे तरफ से ओवर है, बाकी एक्सपर्ट्स अगर और कुछ पूछना चाहें.
ठीक है सर, प्रोसीड करिए.
Okay. Manisha ji, are you ready?
Yes, sir. Yes, sir.
Okay. Please share.
Which Manisha? Previous one or next one?
Manisha Chauhan.
Yes, please start.
Enter screen, but where is?
घबराइए नहीं, शेयर करिए आराम से. हाँ, गुड. आपने पूरा स्क्रीन, हाँ, यस.
Okay. Is it visible, sir?
Yes, it is visible.
Yes. Okay, so this is Manisha Chauhan. I am working as a research scholar in the Department of Physics under the supervision of Professor Prabhakar Singh in the IIT BHU. So my topic of discussion in this presentation is the influence of co-doping on structural, morphological, and electrical properties of RP-type samarium strontium nickelate material as application of cathode in IT SOFCs. So the outline of my work is the introduction of SOFC RP type of materials, method of preparation, result and discussion, and conclusion. So as we know that the world is growing, so the demand of energy is also increasing, and because of the uses of all the fossil fuels, we have left very limited amount of sources. As we can see, we have left only the oil sources of next 50 years, and similarly the natural gases and coal for the 52 and for the 100 years.
Miss
So
Manisha, go directly to the objective and then your results.
okay, sir. Okay. So basically, okay, let me go to the result. Yeah. So basically, I have chosen a RP type of material because of some advantages. Because as we know that we use generally the perovskite and double perovskite materials, but RP material has the structure. Because of that, they can accommodate extra oxygen in their interstitial sites, and because of that, they can have large ionic conductivity or electronic conductivity as compared to the other samples. So that is why I have chosen this material. So my parent material is samarium strontium nickelate, and I have co-substituted with lanthanum and calcium. So we have synthesized this material using solid state method, and we found a phase pure sample, and all the peaks are indexed well with the well-reported data, and we found that both the samples have the same structure, that is tetragonal, and refined with the Ritwell refinement method using the F-triple-M symmetry, I4 by triple M symmetry, and the value of chi-square lie appreciably within the experimental's error, that is 3.25 and 4.48, and so from here we can see that we have found a phase pure sample, and then we also perform microstructure analysis using the SEM, and we found that the grain size is decreasing as we are going from 0.0 to 0.05. I have taken the substitution of lanthanum calcium in the places of samarium and strontium. As we have substituted by the amount 0.05, the grain size has been decreased. It is very visible from this graph, and we have also taken the conductivity spectra. So one interesting thing we got that is that the conductivity has been increased by the order of 2 times. So as we can see, the conductivity in the parent sample is nearly about 70 Siemens per meter, and in case of 0.05 it has been increased nearly 2 times. So this substitution is very useful. And then we have also performed the electrochemical studies to get to know the electrochemical activity of these materials. So we found that as we can see, the graph is the current or the graph is similar. There is no such difference in the value of current, but there is a high cathodic peak in the region of in the fourth quadrant, as we can see in the case of 0.05, which is indicating a better electrochemical activity for this sample after the substitution. And we have also calculated the specific capacitance. So let me conclude all the things here, that the sample has been prepared using the SSR route and sintered at 1250 temperature. Both the samples are phase pure and has been refined using the I4 by triple M symmetry. And from the microstructure, we can see that both samples have the porous morphology, which is very important parameter for a cathode material to use in a SOFC. And we have found that with the co-substitution, the grain size is decreasing from 1.7 to 1.2 micrometer, and also the conductivity increases by the 2-fold with this co-substitution, and oxygen reduction reaction is nearly same for both the sample, but we are getting a high intense peak in the cathodic region in the case of 0.05, which is showing the better electrochemical activity for the ORR, and having the specific capacitance of 400 and 420 farad gram inverse. So this substitution has make the better cathode for the application in SOFC, and this is all about. Thank you.
Good. What was the electrolyte in your electrochemical study? Was it KOH?
Yes, we have taken the neutral electrolyte, Na2SO4.
Na2SO4.
Yes.
Good.
I have one question. Here you have put SM, Samaria, at
Yes.
LA. Okay.
Yes.
And SR is at the CA side. And you also have nickel. Okay.
Yes, sir. Yes.
So is it actually LA is always with SR? When we put SR, it goes with the LA side. And you also have actually SM. So can you explain this thing? Where is
Yes,
the
sir.
what?
Yeah. Okay. So the parent sample for this structure is generally SM2NiO4. We know that the formula for RP structure is A2BO4. So my parent sample is SM2NiO4. But this sample is not stable because of the very small ionic radii of samarium +3. So what we do to stabilize this material is we doped strontium to increase the ionic radii. As we know, the strontium +2 have the big ionic radii as compared to SM +3. So what we did is, so SM and SR are actually on the same side. Then
So all are going at one place.
Yes.
Really? You have 4 cations, SM, LA, SR, CA, all at one place.
Yes, sir. Yes, sir. Actually, this doping, actually, when we did this doping, and then when we performed the electrochemical experiment, so we found a very good result. Actually, I have presented only here the one sample. We have synthesized this
ये
whole
ठीक है, ये
series.
बात बिल्कुल आपकी बात ठीक है, लेकिन जो डॉक्टर साहब पूछ रहे हैं,
Yes, sir.
so all cations you are assigning to the same cationic position. Is it not something which is too heavy? Thermodynamically stable?
Yes, sir. It is a stable material.
I think there must be some problem in stability.
Absolutely.
Okay, sir. For that, we will also do the chronoamperiometry to get to know the stability for at least for 4,000 to 6,000 seconds.
Mechanical stability, thermal stability, and structural stability.
Structural stability.
Structural stability, there may be some problem.
But actually, we have, sir.
XRD is good actually.
Yes, sir. We have found a
very
phase pure XRD.
Very smooth.
Okay, thank you so much.
Okay.
Next is again other Manisha Sharma.
Yes.
यार ये सब लोग मेरा फोटो क्यों लगा दे रहे हैं? Manisha Sharma, are you there? Yeah, please.
Is it visible?
Yes, it is visible.
Okay. Good evening all. My name is Manisha Sharma. I'm a research scholar in IIT BHU, and here I'm working on structural and the optical property of erbium and ytterbium core-doped calcium yttrium vanadate. Here's the overview of my presentation. Now, to study the optical property of this material, first we synthesize this material by using solution combustion method. And here's the whole procedure that I have followed to synthesize this material. After synthesize this material, we do XRD analysis. And here the figure 5 shows the XRD pattern of our sample when it is calcinated at 600 degrees Celsius and 900 degrees Celsius. And the part A of this figure shows the JCPDS file of our sample. And from this figure, we can say that when the sample calcinated at 900 degrees Celsius, it is well matched with its JCPDS file. And according to JCPDS file, our sample has a rhombohedral phase. And the part D of this figure shows the XRD pattern of our sample when it is co-doped with ytterbium and erbium. And it is confirmed from this pattern that doping doesn't induce any impure phase in our sample. Now we do this. Now we do the FTR analysis of our sample, and here figure 6b shows the FTR spectra of our sample. Basically, FTIR, we do FTIR to detect the presence of functional group and the molecular bond in our sample. And here in figure 6b, the strong peak at 750 shows the presence of YO bond in our sample. And there are some other peak which shows the stretching vibration of water molecule and NH bond. Now, from here we study the optical property of a prepared sample. And first we study about the upconversion spectra. Here here when we irradiate our sample with the 980 nanometer laser diode, then our sample shows this type of spectra, which consists of green emission band and red emission band. And here it is clearly visible in this figure that the intensity of green emission will be higher than the intensity of red. And now in this slide, we will discuss about how do the single doping and co-doping affect the upconversion emission. Here in figure 8, the part A shows the upconversion spectra for sample when it is singly doped only with erbium. And part B shows the upconversion spectra of our sample when it is co-doped with both erbium and ytterbium. Here, it is clear from the figure that the intensity of upconversion in case of co-doping is higher than the single doping. And the reason behind this deviation in intensity in case of co-doping is the presence of YB as a sensitizer, whose absorption cross-section is relatively higher than the erbium. And now in this slide, we will see the effect of tuning YB concentration on the intensity of upconversion. So here in the figure 10, if we fix the concentration of erbium and vary the concentration of YB, then we will see that as we increase the concentration of YB, the intensity of upconversion will increase up to 15%. But if we further increase the concentration of YB, then the intensity of upconversion will decrease. And this phenomena of decrement in intensity with increase in the concentration of YB is known as a concentration quenching. And here, the two processes, the cross-relaxation process and the back energy transfer process, are the main process which are responsible for this concentration quenching. Now, here we will discuss about the number of photons that involve in the red and the green upconversion emission. To find this number of photons, we draw a plot between a log plot between intensity of upconversion and excitation power. And the slope of this line give us the number of photons. And here the slope of this red line and the green upconversion line is around 2. It means the 2-photon absorption process is responsible for the green and the red upconversion emission. And here we'll see the power dependent upconversion emission. As we discussed in former slide, that at 30% concentration of YB, the concentration quenching process will occur. Which is responsible, and this concentration quenching process is responsible for the decrement of intensity. But here, if we increase the excitation power, we will see that the intensity of upconversion will increase. This increment in intensity is due to the reason that at higher excitation power, the cross-relaxation process and the back energy transfer process become less efficient. Now we will discuss about the PL spectra for sample. Here the part A of this figure show the excitation. Yes, ma'am.
कंक्लूड करिए, आप टाइम आपका बीत चुका है.
Okay. Here the figure show the excitation spectra and the emission spectra for sample, and we'll see that the strong excitation band at 380 nanometer. And here we can conclude that with up conversion, our material also show the down conversion emission. Here's the conclusion of my study. Here we successfully synthesize our material by combustion method. We found by XRD analysis, we found that our sample is prepared at well matched with JCPDS file at 900 degrees Celsius, and its space group is R3. And FTI spectra show the strong peak at 750, which confirm the presence of YO4 molecule. And at 980 nanometer excitation, YB and ER code of sample produce the green and red emission upconversion luminescence. and the emission intensity increased significantly with the concentration of YB, and its optimum concentration of YB is 15%. And here the both green and red emission are two photon absorption process, and along with the up conversion, our material also exhibit down conversion emission. There are some references. Thank you.
Good. Very important material, very interesting material. Did you try any application of this material so far?
Yes, sir. For detecting fingerprint detection and temperature sensing.
Good, good. बहुत बढ़िया. Or any question? No. Let us call Uma Sharma. Uma Sharma.
Yes, sir.
हाँ, मनीषा जी आप अपना क्लोज कर लीजिए.
So now it is visible?
Yes, it is visible.
Okay. So good evening, everyone. Myself, Uma Sharma, going to present my on my contributed paper on the topic electrical properties of LaSrTiO3 as SOFC electrode material. So my motivation, as we all know that we all are familiar with the nickel atrial stabilized doped zirconia based anodes. We all are familiar with the which is used as for the long time as anodes or as electrode, but it has some drawback like carbon deposition and the contamination issues, and also the less compatibility. So I have used the doped SrTiO3 to here. So my aim to analyze the electrical conductivity or the conduction mechanism of the SiRTiO3 doped with lanthanum. So what I have analyzed here, that we have seen the frequency dependent conductivity spectra of LST at the various temperature, and here the plateau at the low frequency region, followed by the increase in the conductivity at the high frequency region, which shows that clearly shows that the bulk conductivity caused by the random motion of charge carriers at the lower frequency region. At the further dispersal region, there is some AC conductivity, that means there is the correlated forward back hopping motion of charge carriers like unsuccessful charge carriers. So here we have also the Arrhenius representation, the reciprocals of temperature dependence of the conductivity and the hopping frequency, where we have seen the activation energy for this hopping 1.77 electron volt, and this electron which shows that there is the conduction of the concentration of mobile charge carriers is it means that here the conductivity is due to the mobile charge carriers, and again here when we see the activation energy for the bulk conductivity, which implies the conduction is due to the oxide ion through oxygen vacancy. It means that there is some migration of oxide ions. And when we see the exponent which is fitted from the Johnson power law of the previous data, that means the conductivity spectra, it shows that there is a decrease in the exponent value with the increase in the temperature, and which shows that there must be some possibility of the large polarons in the LST. And again, when we see the concentration, that means the variation of the concentration of mobile charge ions with the temperature, what we see that there is the increase in the value of the concentration of mobile charge and with the temperature, it shows that there is the charge carriers which are thermally generated. And when we see this graph, the DC conductivity versus hopping frequency, we get the approximately the slope is unity, which is approaches to unity, and which shows that DC conductivity and the hopping frequency is proportional to each other, and which shows that the conductivity is due to the hopping frequency. And which so other study shows that there is the conductivity is not only through the ions but they are also through the charge carriers which are dependent on the temperature. Again, when we see the IV curve of these undoped SrTiO3 and the doped LaSrTiO3, what we see that the leakage current for the La doped SrTiO3 is increased. Is more than the SrTiO3, which generally shows the conduction, more conduction in La doped SrTiO3 than the simple SrTiO3. So what we conclude from this that though IV curve has a higher leakage current, and also there is a much electrical conductivity or increase in the electrical conductivity of pure SrTiO3 in comparison to the LaSrTiO3, and it may be possible that it may be a promising candidate for the electrode. So These are the references. Thank you.
Very good. You have taken care of how to present in a 5 minutes important things.
Absolutely.
Absolutely.
You are repeatedly using a word charge carrier. What charge carrier do you expect?
Yes, this is my
Sorry,
question.
sir.
आपने बार-बार कहा चार्ज कैरियर. What charge carrier do you
Iron and
expect?
charge carrier. There are two kind of.
It is a mixed
movement.
conductor.
So here we have those La here in SRTiO3. Here the La3 ions are taking the SAR to our sites to create a situation of charge imbalance. So we have the two La3 plus and SR2 plus ions.
You mean lanthanum ion is moving?
Yes, sir.
You mean lanthanum ion is moving? ऐसा नहीं बोलना.
नहीं lanthanum क्यों move करेगा?
But if you are talking about hopping of ions, then there must be some ion, no?
Yeah, she is talking about oxygen ion, and in addition, other word is charge carrier. You had measured in terms of activation energy. You have measured in terms of their hopping frequency. Think about it.
It is Uma. This is mixed conductor. It is electronic plus ionic both.
Electronic.
Yeah.
Yes, sir.
It's a mixed conductor.
Good.
Yes, sir.
Good. Jyoti Vijayan.
But
ज्योति विजयन नहीं है. डी लक्ष्मी. D. Lakshmi, if you are there, from Bhartihar University. No. Then Dr. Tabish. Tabish Saab.
What about Lakshmi?
He is also not responding. I cannot see her in the list. Tabish was there in the list a few minutes ago.
Sir, you are on mute. Dr. Tabish, you are on mute.
Dr. Tabish, start presenting.
What's about Lakshmi?
Lakshmi and Jyoti, they are not in the list. We could not see them in the participants list. Let us hear Dr. Tabish.
Yeah.
Tabish, we cannot hear you. आपका स्लाइड दिख रहा है लेकिन आवाज नहीं सुनाई दे रहा है.
तो सेकंड में रख देते हैं इनको.
अंकित.
Are you there?
एक प्रेजेंटेशन पहले और ले लेते हैं, उसके बाद ताबिश साहब कर लेंगे. ठीक है.
नेक्स्ट किसको लेना है?
नेक्स्ट डोना बाजी.
Dona Baji, are you there?
Yeah, I'm here.
Yeah. Tabish sir, please unshare. Yeah. Okay.
So is it visible, sir?
Yeah, please go ahead.
So myself, Donna Susan Baji. I'm from Nano Energy Division, Center for Nanosciences and Molecular Medicine, Amartya Vishwavidyapeetham. So I'm presenting my work on rechargeable alkaline batteries, chemically reduced FeFeCN6 for cathode. So among various energy storage system, lithium-ion battery is known as the cornerstone for various applications ranging from small to large-scale energy storage system. However, the uneven distribution of lithium-ion batteries resources ahead with depletion of resources and escalation of price demands at least partial replacement of lithium-ion battery for large-scale accomplishments. So the researchers have shifted focus to sodium-ion batteries since the abundance of resources and similar electrochemical characterization of lithium-ion battery. So basically the work focus on depression blue and its analogs. We have synthesized from the advantages of inspired from the advantages of Prussian blue analogs. Here we have synthesis chemically sodiated as well as lithiated FeFeCN6. CN6 was prepared by a single ion source, followed by a chemical sodiation and lithiation of the same, which was performed subsequently, and followed by we have taken sodium iodide and lithium iodide salt were used for sodiation and lithiation process, and we had to note that it is in a solvent medium which is having which take only a rapid process which is less than 10 minutes, and it should noted that the method only utilizes a mild temperature and atmospheric condition, and the pair going to the result, the Bayer and sodiated as well as lithiated Prussian blue analog possess same crystal structure of cubic structure, and sodiation affected in the lattice expansion, whereas the lithiation has affected lattice compression. And from the electrochemical analysis, you can see that there is a the initial charge capacity of sodiated FeFeCN6 reveals a sodium-rich resultant compound, and this is an expeditious, scalable, cost-effective method which can be considered as an accomplishment for sodium-ion battery applications. And the sodiated FeFeCN6 manifested a capacity of 78 milliampere hour per gram over 500 cycle with a retention of approximately 70% at 100 milliamp per gram rate. And even though the lithiated Prussian blue analog was not incomplete, you can see from the graph that it is an incomplete process. Still, the cell maintained 92% retention for overall 300 cycles, which is calculated from the third cycle. And we have done an ex situ analysis also XRD for the same sodium-ion battery for FeFeCN6. Sodiated FeFeCN6, and from this ex situ XRD analysis, which you can see that the Bayer electrode has similar XRD profile of the powder electrode, and which is having a cubic structure and which is similar to the powder, and the end of the first charge, the sodiated Prussian blue analog, belongs to well-oriented cubic structure, which is also similar to the electrode before cycling. And you can see the closer view of X2 XRD, which confirms the phase transition. You can see that high index 200 peak shift to the lower angle upon chemical sodiation, and which is indication of the lattice expansion, followed by a high angle shift during the first charge, which is due to the lattice compression upon desodiation. And this lattice expansion again happens when the sodium is inserted back at the end of first cycle, along with the phase transition. Similar observation was also found in 220 plane. So we have observed that chemically sodiated NaX FeFeCN6 with X is equal to 1.22 based on the first electrochemical desodiation capacity to a monoclinic phase transition at the end of first cycle, when the high sodiation of NaX FeFeCN6 with Na 1.4 through electrochemical discharge was attained. And based on these results, it may be described that the structural phase transition from cubic to monoclinic possibly happens with a critical sodium concentration around 1.3 NaX FeFeCN6. The transition is confirmed by peak splitting of 220 to 420 peak, and this monoclinic phase was retained even at the end of fifth cycle. You can see from the graph, the Stauffer's chemical analysis was also conducted, and you can see that both prepared and cycled ones are there. Apparently, the sodiated PBA Prussian blue analog and the first cycle shows Fe2P spectrum of Fe2 plus state, which is due to the sodiation induced reduction, which is quite similar for the both electrode with only the trace amount of Fe3 plus. And in spite From all the advantages Prussian blue analog process, most effort are focused on sodium-rich Prussian blue analog. However, there are reports on Prussian blue analog with incomplete sodiations, and this demands a sodiated anode for practical application, which again leads to several hurdles for the commercialization perspective. So a previous study has reported sodium ion could be chemically sodiated into FeFeCN6, but predominantly in the presence of reduced medium, and this also includes various sophisticated steps. On the other hand, our approach was to employ an atmospheric condition convenient way of synthesis method which avoid a high challenge like high pressure or reducing atmosphere to inhibit oxidation, etc. So our work particularly emphasizes the importance of sodium-rich intercalating cathode material, which will further avoid multi-step processing or complicated electrode design. So this has been realized to be a high-yield, high-efficient process which can be considered to be a practical approach. Further, this work is demonstrated that chemical reduction could be a potential process for the preparation of alkali and containing cathode materials. So these are my
Good.
reference, and thank you for listening.
Good, good, good. You made a comment that if it is lithiated, it is compression. If it is sodiated, it is expansion.
Yes, yes.
But the
Lithiation is not
dimension of the two ions are almost similar.
No, sir.
One is 0.63, the other one is
1.0.
I'm sorry, 0.76 and 1.03, if I'm correct.
Yes, it's 34% higher, right? Compared to lithium.
Yes.
So possibly because of that, lattice compression is happening.
Okay. Okay. और कोई क्वेश्चन किसी का?
No, let's.
Okay, thank you.
Thank
Dr.
you.
Tabish?
Thanks for listening.
Dr. Tabish, can you connect, please?
I'm audible?
Yes, yes. दोनों प्लीज अनशेयर.
कैसा हाल है?
अभी
तो ऑलमोस्ट एवरीबॉडी को हो रहा है.
So how to unshare?
Go to that point where from you had shared.
There is a one cross.
Yes, you have unshared.
Red color.
Yes, good. Tabish साहब शेयर करिए.
Okay, sir. So is my screen visible?
It will appear.
Right. कर रहा हूँ तो.
Yes. It is
Right का ना बहुत जरूरत होती है. बहुत यहाँ. Okay, so good evening to everyone. I welcome all the participants for ICEMD 2022. So my work is a bit different from what others have been presenting. My work is basically theoretical in nature, and again, what I've done, I have tried to design two novel dyes, and these dyes have the absorption profile in the infrared region. So quickly, I will move forward. So as we can see, these DSSCs, they can be made on the flexible substrates, and initially the idea for this was given by Michael Gratzel. And if we see the figure that the DSSCs, they have consistently improved in their efficiency. So here this graph actually compares all the non-silicon based solar cells, and DSSCs, they show a lot of promise. So now if we see the general structure of the DSSC, we can see that the dye, of course, this is the core element, which is actually producing our electrons. This dye is actually, it is absorbed on the TiO2 layer. And in fact, there are other layers also. So the main function of this dye is to generate the electron and the hole pairs. And of course, we can find that there can be two competing processes from here. One is the recombination of the electrons and the holes, and the other can be separation of the electrons and the holes. Now, Now, if we talk about this process, we want to increase this generation of the electron hole pairs. And if we can improve and we can increase the number of the electron hole pairs that are generated, of course, we can improve the efficiency of the dyes. So basically, the purpose of this study is to make the new and novel dyes and make a theoretical investigation so that it will be helpful for the experimentalists when they are actually designing and working with those particular dyes. So moving on, again, Now, what is new in this work? So if you can see this solar spectrum, so of course this part from 400 to 700 nanometers. So this part corresponds to the visible region. But outside this region, of course, beyond the 700 nanometers range, beyond this range, there is a lot of solar spectrum that is present in the infrared region. So we want to utilize this particular region also. And for utilizing this particular region, we have designed two novel organic dyes. So moving on, so I have discussed the necessity of these dyes in my video, and I will skip this and I will come to my main result. So these novel dyes, these are based on the D pi A and D pi AA model. So D and A, they are corresponding to the donor and the acceptors. Pi is the pi bridge, which provides the insulation between the donor and the acceptor. So the first dye is carbazole, thiophene, naphthalenimide, and the second dye is carbazole, thiophene, naphthalenimide, benzothiazole. So of course, the second dye, it contains the two dyes. And moving on, so we have done the calculations using DFT and the B3LYP, and again the software package of Gaussian is used. Again, you can see these figures. These are showing the HOMO and LUMO for the particular dyes, which have been calculated by the Gaussian software. And again, this is one more result that we have obtained. These are the charge density difference plots. So the blue regions correspond to the positive values of the changes from the excited state and the ground state. And the red region, it corresponds to the opposite one. And again, the HOMO and LUMO gaps, they are provided. And again, in the second table, we can see the maximum absorption wavelengths, which we can obtain from the two dyes. And again, this is another table which shows the electron injection energy, the dye oxidation potential. And again, if we see the open circuit voltage for the two dyes, we can see for the second dye, the open circuit voltage is higher, and we can see that this will be having a better efficiency. Moving on to the final results. So in order to design the good IR absorber sensitizer, the double acceptor moieties, they can be really very useful. From the results, the HOMO and LUMO charge distributions, it is clear that the HOMO lies mainly over the donor and the pi bridge in the both sensitizers. The LUMO is spread mainly over the acceptor moieties. And again, from the CDD plots, we can find that the charge is mostly seen over the whole of the molecule, whereas it shifts slightly towards the acceptor side, which is shown in the blue color. So the present result confirms that the model based on D pi A and D pi A design, so they can be suitable for absorption in the infrared region. So this was our objective, and we are able to achieve it. And we can see that the wavelengths, again, 1432 nanometers and 1351 nanometers for the two dyes, they will correspond to the infrared region. The light harvesting efficiency for both the systems is found to be similar. The charge injection energy is negative, which shows that the charge will be transferred at a faster rate to SnO2. So we are talking of SnO2. We will be replacing TiO2 with SnO2 because this will have a better alignment of the LUMO levels. The dye regeneration energy for dye 1 is higher, which is because of its lower.
Was the indication that you have caused 1 minute time.
Okay. So again, if we talk about the open circuit voltage, the dye 2, this is having a higher open circuit voltage as compared to the dye 1. And this shows that our double acceptor strategy, this is better. This is better in designing the dye sensitizer. So that's all from my side.
Good.
Thank you.
Dr. Saab, this dye that you have designed, it is something which you have assumed, let me say,
Yes,
that you
sir.
had assumed a molecule and then calculated.
Correct, sir. Correct, sir. So it is a completely theoretical work, and maybe in the future it can be taken up by experimentalists.
For my knowledge, can you tell me that if we have a molecule, then can we go back and calculate the HOMO-LUMO position? It is
Sure,
easy
sir.
to get the difference between HOMO-LUMO, but can we calculate the HOMO-LUMO position with respect to NHE?
Sure, sir, we can do that.
Okay, great.
We just need molecular structure, and in
I
the
will
gas
talk to you.
phase, we can very easily predict the HOMO and LUMO and all the
I will talk to you.
and everything.
So this is just the theoretical model actually, not experimental, right?
Yes, yes.
You didn't
Yes,
synthesize.
No, sir. No, sir. This is a completely theoretical study. It is based on DFT. So DFT formalism, as we know, like it is working on the solving of the Schrodinger's equation approximately. So initially there will be an optimization that will happen.
No, but in the in a solar cell in DSSC, actually we synthesize first, then we go for the theoretical work.
Right, sir. So we have done the theoretical work to predict the properties of these dyes, and if they are suitable, the experimentalists can take it forward. Of course, because we can also remove the use of infrastructure in this way, and it can predict better materials.
Because when you go for the publication, you have to give both, not single thing.
Yes, you are right, sir. However, people are also publishing theoretical work also, and what they will do, experimental data.
Yes.
So now somebody has to do the experimental and then compare with your.
No, we will definitely. Me and Guptaji would like to contact Dr. Tabish.
Yes.
Say Thank you so much.
Thank you, sir.
Professor Bhattacharya,
Yeah.
Instead of saying anything, I will play this music. It means that time has been crossed.
एक बार बजा दीजिए.
Participants,
एक बार बजा दीजिए.
बजाए तो अभी सुनाई नहीं पड़ रहा.
नहीं कुछ नहीं
दिया.
Oh, ठीक. Okay.
I will play this
So-
music. That means time has been crossed.
Okay. Then at that after that music, we will try to force that it is stopped.
Stopped. Yes.
Next is Silpa Sri.
Yes, sir, I'm here.
Yeah, please.
Because we are going 10 minutes in each case, na? So that is.
Oh.
10 बजेगा.
We are already 1 hour late now.
1 hour late. That's why I'm saying that we have to be fixed. Time matlab management is important.
Sir, is my screen visible?
Yes, it is visible.
Yeah, okay. So, hi everyone, myself Shilpa Sri SJ. I'm the PhD scholar from Center for Nanosciences and Molecular Medicine, Amrita Vishwavidyapitham. So, first of all, I thank the ICEMD-2022 for giving me an opportunity to present my topic, lithium-rich layered cathode for advanced lithium-ion batteries, the particle size and operation temperature effects. So as we all know, in the increased demand of energy, LIB plays a huge role in the day-to-day human life. And considering the soaring price of cobalt and increased demand of LIB, cobalt-free layered cathode materials take much interest as an advanced lithium-ion battery, considering its advanced energy density, and in specific, the layered lithium excess LNMO or lithium-rich LNMO. So it is basically a cathode material which comprises of a solid solution of both rhombohedral as well as monoclinic phases with a high reversible capacity of around 250 milliamp per gram, and it possesses an average voltage greater than 3.5 volt, and moreover the low cost easiness of synthesis, and the main thing to be noted that it is a cobalt free cathode which can be a sustainable cathode for the future. But the main challenges of these materials is the irreversible first cycle Coulombic efficiency, poor cycling stability, low rate capability, voltage decay, and further electrolyte decomposition. So what happens is, like, when cycled at a higher potential, transition metal ions will migrate to the lithium sites, and thereby it will trigger the oxygen loss from the lattice, which will lead to surface reconstruction from layer to spinel structure. And this caused to the mentioned challenges as mainly the irreversible first cycle Coulombic efficiency. So many strategies like surface modification, nanoscaling, doping, tuning of morphology, and electrolyte additives have been adopted by different groups in order to overcome these challenges. So herein what we are focused is, like, we present a detailed study on effect of two different nanoparticles size based on by adopting two different lithium precursors in the synthesis. So what we have done is, like, we have prepared two sets of samples in which
In the one, we use lithium acetate dihydrate as the precursor, whereas in the other, we use lithium acetate as the precursor. So as a result of the salt gel synthesis, we obtain two different samples having like particle size of 150 nanometer as well as 40 nanometer. So the 150 nanometer particle size samples is labeled as LR150 and the other is like LR40. And we believe that while taking the lithium acetate dihydrate, it triggers the slow nucleation that resulted in larger size particle, and in the other one, which is having not hydrated group, that resulted in fast nucleation and thereby the smaller particle size. So here comes the structural, morphological and surface chemical analysis of the synthesized two sets of samples. So from the XRD, it is seen that both the samples seem space pivot to the R3 barum space group of the normal layered structured materials, which is consistent with the literatures. And one thing it should be noted that for the LR40 sample, which having the particle size of 40 nanometer, there the peak width seems broader than the other one, and this corresponds to the lesser particle size. And while coming into the TM images, B and C corresponds to the TM images of the 150 nanometer particle sample, where D and E corresponds to the LR40 samples, and it is obvious that the particle size is clearly observed from the TM images. And when going to the XPS, like high resolution XPS spectra of like Mn2P and of LR40 as well as LR150 samples, in both the samples, manganese exists in 4+ oxidation states and nickel exists in 2+ oxidation state. And when coming to the electrochemical analysis, it is observed that for LR150 and LR40 samples, for both the samples at room temperatures, the initial Coulombic efficiency obtained is around 80%, which is typically high value compared to the literatures reported so far at a current rate of current density of 125 milliamp per gram, which is equivalent to C/2. 1C here we are considering as 250 milliamp per gram. And while looking into the rate capability test, it is seen that for both the samples at a current of 1000 milliamp per gram, which corresponds to 4C current rate, the capacity is almost similar, like almost same of around 132 milliamp per gram, but the difference between both the samples is clearly visible in terms of retention percentage corresponds to the current density. It is seen that for LR40 at current density of 1 amp per gram, the retention is only 64%, whereas for the, for LR150, the retention is only around 61%, whereas for LR40 samples, the retention is around 75%, which is much higher than that of 150 sample. And while looking into the cycling data, like long-term cycling stability of around 300 cycles as well as 500 cycles at 500 milliamp per gram as well as at a high current rate of 1 amp per gram, LR40 exhibited a better cycling retention compared to LR150. And we extended these studies to a high temperature of 55 degrees also.
Please conclude. You have already taken 5:30.
Yeah, so like at high temperature also, it is seen that LR40 performed much better retention compared to the LR150 sample, and here also the Coulombic efficiency was much better. And here comes the voltage fade analysis at room temperature and high temperature. But in the case of voltage fade analysis, it is observed that LR40 exhibited slightly higher voltage fade compared to LR150. That we are assuming that for the LR40 sample, due to the larger particle size, to the smaller particle size, surface area is much increased, and thereby implementing a proper surface engineering by like surface coating or something, it is possible to further enhance the performance by suppressing the oxygen release and thereby decreasing the voltage fade over cycling. And thereby the cobalt-free lithium-rich lithium excess LNMO with lesser particle size can be an eminent cathode material for future advanced lithium-ion battery applications. So these are the reference which I have been used for this work, and thank you for your attention.
Good. Good. Thank you.
Thank you, sir.
Next is Neeti Agrawal.
Just a minute.
Presenters are requested to maintain the time.
Neeti Agrawal?
Yes, sir.
Yeah, please connect. Yeah, we can see it.
Okay, good evening, everyone. My name is Neeti Agrawal from the Department of Physics, Shamlal College, University of Delhi, and I'm going to present in few minutes the results of the work that I have done, which is the monthly energy yield assessment of photovoltaic system under uniform irradiance and partial shading conditions. So I'll just skip this. So when we have a PV module, they are generally rated by the manufacturers. Not generally, they are. That's a standard that you rate the PV modules at standard test conditions of 1000 watt per meter square and 25 degrees Celsius. Whereas when the module is installed in the field, it experiences wide range of irradiance, temperature, humidity, wind speed. So the energy that it generates over a period of time is a result of all these conditions. So when we say that the power rating at STC in that sense is not sufficient to rate a module. So that makes the energy generation rating, rating the module on basis of the energy generation a very important thing. So along with these conditions of various temperature, then irradiance and other environmental conditions, there is one more condition which is very important, which is normally encountered by the installed panels, which we call as the partial shading conditions. So partial shading condition is basically it's the condition by which any object in the vicinity of the PV module it casts shadow on the PV module. So what happens is there is an irradiance mismatch among the different parts of the module, and this leads to the energy degradation. So in an attempt with this objective to estimate how much is the energy loss can happen over a period of time. So we performed this experiment where an array was constructed out of 3 modules of 45 watt peak each, making it a 135 watt peak panel. We installed this at the National Institute of Solar Energy, and where the real outdoor measurements were conducted. The experiment was basically divided into 2 parts. One where the array, as is shown in the first picture, it's like it's not shaded. So the uniform irradiance condition may there for various days, like we obtain the IV characteristic of this module, and to generate basically a power matrix of 22 conditions. That 22 conditions is basically 4 different conditions of temperature and 7 different conditions of irradiance. So, and then this again was repeated when the same system was partially shaded. The one row of 2 modules was shaded by a paper whose transmissivity we calculated and came to be 60%. So that means 40% shading strength was there. And again, we formed that power matrix. So that means we had this IV output power for 22 different conditions of temperature as well as the irradiance. So temperature was 15 degrees, 25 degrees, 50 degrees and 75 degrees, and irradiance was 1100, 1000, 800, 600, 400, 200 and 100 watt per meter square. And then these conditions were used as the reference condition, and then we using the appropriate equations, we actually calculated the instantaneous power for corresponding to the weather data that we had obtained for the entire year, and which gave us the condition which recorded the weather conditions after every 10 minutes. So we could calculate the power instantaneous power after every 10 minutes, and the total was used to form the energy generation. So basically, this is the important result, that this is the energy yield that was obtained for the entire year, right from January to December. It is shown that obviously the monthly, because the irradiance received in each month is very different from each other. So the energy generation is also different for different month. For this particular year, the highest was obtained in the month of March and least in the month of July. But when this was shaded with this condition, with this particular condition, we found that there was a significant increase in the energy yield. So just in terms of the monthly energy loss, in terms of percentage, this is the loss, which was like 50% loss was obtained. So this result highlights how this partial shading condition is so important. It can deteriorate the energy yield to a significant factor. Obviously, this energy yield, the percentage by which this energy yield is deteriorated depends upon the pattern of the shadow, depends upon the location of the shadow, depends upon the intensity of the shadow. So for particular case that we have considered, we found that the partially shaded condition can deteriorate the energy by more than 50% every month. And so there is need to address this issue. And so the result of the study are beneficial, especially for those locations where there is a high probability of getting installed PV arrays partially shaded for a longer period of time. And this is actually true for many cases which is like building integrated photovoltaics, where the panels are introduced at the design level in the building. And it's also the urban area rooftop building where the shading from the objects is actually unavoidable. Thank you.
Okay, good observation. Chandrabhal Singh.
Yes, I am here.
Oh, sorry. Was I supposed to? I stopped sharing.
No, it's fine. It's a good observation. Good observation.
Okay.
Probably the companies would like to have your data.
Okay, thank you.
Good evening to all. Myself Chandrabhal Singh. I am doing my PhD under supervision of Dr. Akhilesh Kumar Singh. I am going to present on topic band gap engineering of barium titanate perovskite oxide by vanadium doping and observation of photovoltaic response. So I am going to directly experimental results. We have prepared the vanadium doped barium titanate using ball milling, and after crystal structure analysis, we found that two crystallographic phases are obtained, tetragonal and rhomboidal. As we increasing the vanadium doping, we have found that rhomboidal phases increases, and thus is distorting the structure and changing the lattice parameters. So main objective of this work was to get the lowest band gap of barium titanate, as barium titanate had very high band gap around 3.2 electron volt. So we have doped this vanadium doping and found that with 7 mole percentage vanadium doping, it has high absorbance, and also the band gap is lowered, and we have found that when increasing the vanadium, the band gap is also decreases. And with 7 mole percent doping, we have obtained 1.42 electron volt band gap. So high band gap is reduced. It is explained on the basis of subband created between conduction band and valence band, and it is found due to vanadium 3D states. These substates are formed, and it reduces the distance between conduction band and valence band. Also, as we dope the material, there are oxygen vacancies are formed, and these also play important role, and thus these also created some low energy band below the conduction band, and thus both play important role, and thus we get a low band gap material after the doping. We have also measured the ferrotic polarization P loops and found that the P loop is decreases as we increase the vanadium doping. The reason behind decrease is due to creation of oxygen vacancies due to vanadium. But to get the bulk photovoltaic effect in these materials, we need at least some remnant polarization, and we have found that we are getting polarization in these materials even after doping. I have prepared the photovoltaic device using the 0.7 mole percent vanadium to be at its lowest band gap material, and we have taken the thin ceramic plate of around 400 micron, and first we had taken silicon substrate and silver paste and put this ceramic pellets, and on the top of used mask and deposit the aluminum doped zinc oxide which act as a top electrode, and this is we can see how this device is made. So we have measured the IV by changing the light intensity and found that as we increase the light intensity, the photocurrent increases, but what we are seeing, open circuit voltage is fixed. The reason we can see with the equation. As intensity increases, it is directly proportional to photocurrent, and we can obviously see, we can see here, but VOC, this should be also changed with intensity, but here in this case, it is not. I will explain in next slide. But how intensity is affecting the photocurrent, we can see here. When intensity is low, less number of charge carrier are generated, and this results in low photocurrent. As we increase the intensity, number of charge carrier increased, and we get the higher current. So here I will explain the mechanism of, it's not, we are getting positive photocurrent and negative open circuit voltage. That's the first sign that we have bulk photovoltaic effect in these materials. And I will explain why we are getting positive current, because polarization is in opposite direction from top electrode to bottom electron. So deep polarization field in this material will be on from bottom to top. Thus we are getting this photocurrent is positive. So another, in normal PN junction solar cell, the photocurrent is due to interface field, which is due to Schottky barrier height, and due to that net built-in potential form. So we have calculated, and we are using silver as bottom and AZO as a top electrode, and we have found that we are getting net potential values minus 0.36 volt. But what we are getting, our VOC is minus 2.02 volt. Thus we can say that our open circuit voltage not only come from this interface, but it is due to depolarization field of the material itself. It's not due to PN junction only. So we can say that this is the one first sign that it is a bulk photovoltaic effect in these materials. How this bulk photovoltaic is created is explained by some model. First model was P.S. Brody in 1975 proposed a model that some space charge region is created in grain side, and as grains are connected, so these total result can give a bulk photovoltage. But due to interface, we cannot say it is totally true. In another model, depolarization field model, they have said that due to disbalance between charge carriers, this total depolarization field is created, and it is explained in this manner. So we can say this is, we have bulk photovoltaic in these materials. So in conclusion,
कैसे रुका जाएगा?
So
टाइम
band
का
gap
कुछ
is reduced to
लिखना पड़ेगा.
3.2 electron volt to 1.42 electron volt, and we
कुछ
have
घंटी उंटी बजाने का नहीं?
photovoltaic effect
कहाँ
in
कुछ
these
नहीं सुनाई दे रहा.
materials. Thank you.
एक भी नहीं सुनाई दे रहा, इसीलिए तो बिल्कुल.
क्या हो गया?
ठीक है. थैंक यू चंद्रभाल.
हेलो सर.
थैंक यू. आपका बड़ा इंटरेस्टिंग था. मैं बहुत कुछ डिस्कस करना चाहता था, लेकिन टाइम इतना एक्सीड आप लोग कर रहे हैं, वी कैन नॉट डिस्कस. मे बी आई विल पर्सनली डिस्कस विथ यू, because this is not a photovoltaic cell what you are showing. Anyway, we will discuss it later personally. Let us go to M. Infanta Diana.
नो मैम.
नहीं सुनाई नहीं दे रहा है.
नहीं, मैंने भी नहीं सुना है.
सुनाई नहीं दे रहा है. वो नहीं हो रहा है.
That is not something.
ना बिल्कुल नहीं. आप ऐसा करें, उसके बाद ऐसे ठोक दें तो हम लोग सुन लेंगे. ना अब सुनाई दे रहा है, लेकिन उसके बीच में नहीं आ रहा है.
इस समय तो सुनाई दे रहा है, लेकिन जब बज रहा है.
Anyway, M. Infanta Diana, if he is not there, then Ramesh. रमेश है क्या?
यस सर, यस.
ओके.
बीच में रोक दिया करिए ना 4 मिनट के बाद.
इट इज विजिबल.
अब घड़ी देखना पड़ेगा ना, कोई घड़ी देख के वॉच करता रहे. तोमर साहब,
माय स्लाइड्स
4 मिनट में आप रोक दीजिए.
नहीं, डॉक्टर संदीप ये काम कर लेंगे. अब बता दिया कि आप कर लेंगे.
हेलो,
आप संदीप साहब को होस्ट बना दीजिए, वो स्टॉप कर देंगे. बस कर दें.
नहीं, ही इज अ प्राउड पर्सन.
रमेश जी का शेयर करिए भाई.
इट इज विजिबल सर.
नो,
नहीं, अभी तो नहीं भाई. अभी तो कोई विजिबल नहीं है.
यस. नाउ
नो बिल्कुल नहीं, आपका हाँ अब आ रहा है।
अब आए हैं आप।
ओके ना सर?
जी जी बोलिए।
Good evening to everyone. I am Ramesh from Department of Physics, Banaras Indian University, Varanasi. Here I am going to discuss about one of my research work, which is combustion synthesis of reduced graphene oxide for electrochemical supercapacitor application. So there are some common techniques to reduce the graphene oxide, which are chemically reduced graphene oxide, thermally and hydrothermally reduced graphene oxide. Here, the chemically reduced graphene oxide, we need to use high reducing agent, high reducing agent for remove the functional group from the graphite oxide. In the hydrothermal and thermal reduction, we need to use high temperature furnace and high temperature electric furnace usage to remove the functional group from graphite oxide. So to avoid the chemical strong reducing agent and usage of electric furnace usage, we are introduce the camphor assisted combustion method to reduce the graphene oxide. So here we are combust the graphite oxide with the camphor molecule, so which can produce the reduced graphene oxide along with carbon particle, so which can minimize the restocking effect of reduced graphene sheet, and as well as it will enhance the ionic permeability within the electrode. So here we know that camphor is one of the combustible sublimated carbon precursor, which can produce the carbon particle when during the combustion. So here we are changing the camphor concentration like 12 gram, 16 gram, 20 gram. So later we are named as RGO12C, RGO16C, RGO20C. The combustion material was confirmed by XRD measurement. Here the peak position of graphite was shifted towards the lower angle, which can during the acceleration. So later after combustion, the peak position of graphite oxide was shifted towards the higher angle, which confirms that most of the functional group were removed from the combusted material. So the microstructural sun image shows that the combusted material morphology was fluffy natured material, fluffy natured morphology, and respective temp image shows that RGO12C having higher carbon nanoparticle, higher concentrated carbon particle presence in the carbon graphene, and also RGO12C having less carbon particle on the surface. So which due to higher and lower camphor mediated combustion of graphite oxide. So here the BET surface area also tells that the RGO12C having higher surface area, RGO20C having lower surface area, which due to higher and lower concentrated carbon particle presence in the graphene sheet. And also specific capacitance versus current density value shows that combusted material having higher capacitance, which is comparably higher than chemically reduced graphene oxide. So here combusted graphene oxide having 241 Faraday per gram, which is comparably higher than chemically reduced one. So in the conclusion, the synthesis of RGO using camphor-assisted combustion of graphite oxide is reported for first time. The camphor-assisted combustion of graphite oxide is one of the cost-effective reduction techniques. Here we can produce the RGO along with carbon particles without utilizing any high-tech laboratory and instrument. The advantage of synthesis acquired carbon particle can prevent the self-restocking of graphene. Therefore, the electrochemical capacitance of combusted graphene oxide shows higher value than chemically reduced graphene oxide. So my motivation is, of work is, so how to overcome the lack of research facilities to produce the chemical synthesis or some other synthesis with limited facilities. So I would like to acknowledge Professor Voyan Srivastava and MESAS, Sterling Leo Hudson, Professor P. Ravindran.
Good.
Thank you.
Very good,
Thank you.
Ramesh.
Thank you, Ramesh ji. Yes,
Very
finished
good.
in 4.
And the work is
4
also
minutes and
very
10
good.
seconds.
Can I quickly ask one question,
So
Ramesh?
and also we can produce the graphene oxide when we need. We can combust and we can get it within
Ramesh,
15 minutes.
generally when we burn camphor,
Yes,
it gives out some fullerene also, fullerene and similar bulky
that's
things.
why we are getting some carbon shoot on the graphene sheet.
Okay.
Due to decomposed carbon particle form the carbon particle.
Okay.
Thank
Good.
you, sir. Thank you very much.
Next is Devesh Chandra Bharati. देवेश चंद्र भारती नहीं है?
No.
सचिन विजय देसारादा.
Yes, sir.
Yeah, please.
Is it visible?
Yes, you can start.
Okay. So namaste. I'm Sachin Desada. Now my topic is optimization of MOAC2 back interface layer for high efficient CIGS solar cells. So first of all, what is CIGS solar cell? These are this is the material used for the second generation thin film solar cells. It shows very high absorption coefficient. It has a tunable band gap between 1.1 to 1.7 electron volt, so we can tune the band gap as our application as our desired application. Now, what is the problem associate with it, or what my study problem? So generally we use this structure for CIGS solar cells. First we deposit MO, and then up to that p-type material CIGS, and then we make a junction with n-type CDS, and then multiple layers above it, ZNO and ALZNO. Now the interesting part is the most of the time we grow CIGS by selenization. That means we grow first copper, indium, gallium, and then selenize it with at higher temperature. When the selenization happens, MOAC2 layer grows at the MO and CIGS interface intrinsically. Now, if we can adjust MOAC2 properties, then we can improve the properties of the solar cell. So for that, I have simulated the CIGS solar cell with SCAPE's 1D program and changed the properties of MOAC2 layers, such as band gap and primarily band gap and thickness of the solar cell. Now all these parameters I have taken from the references. The application needs these parameters, so I have taken them from the references. Now finally, going to the result, this is the chart after changing the band gap of MOAC2 layer. Now I am getting highest efficiency of 20.4, nearly 20.4 at 1.4 to 1.5 electron volt, which is constantly which is linearly increasing after 1.3 electron volt and decreasing after 1.55 or 1.58 electron volt. Now this is the result of energy band gap optimization, and this is the result of thickness. Now after we grow CIGS, if we can somehow control the thickness of MOAC2 layer in between 0.05 micrometer to something like 200 nanometers, we can see the peak efficiency is higher for thickness above 0.05 micrometer. Now why this is happening? So back contact for the p-type and back contact layers are working as a whole collector layer. So once when we reduce the barrier between those between the contact, then there is a less combination between electron and holes coming to the back layer, which is reduced after which is reduced in the which is reduced when the energy band gap of the MOAC2 layer is 1.3 and 1.5 electron volt. This is the main region, and another limit is Shockley-Queisser limit, in which the recombination part is most prominent. So somehow, if we can reduce the recombination at the layers, we can optimize the performance of the solar cell. So in conclusion, MOAC2 layer back interface layer has been optimized with the properties of thickness and energy band gap layer. Now Now, from this simulation, I can say if we have if we want the good efficient CIGS solar cell, the property of MOAC2 layer required is band gap is 1.4 electron volt and thickness is above 100 nanometer. Thank you.
Thank you.
Good.
Thank you.
Good. Very good. बहुत बढ़िया. बहुत अच्छा काम.
Thank you, ma'am.
Nicely optimized data. Satyendra Kumar Satyarthi.
Yes, sir. Yes, sir.
Yeah, please do.
Good evening to everyone. I am Satyendra Kumar Satyarthi from IIT BHU. I am working under supervision of Dr. Akhilesh Kumar Singh. Today's my topic is enhancement in the dielectric properties in rare earth cerium dope lithium niobate for high temperature application. I will go through directly from the experimental part, which I have shown through some images, where I have shown in image 1 high energy ball mill, then I have shown here sample collection and then drying over the night. Then I have shown some images for the sintering purpose, where I have sintered my sample at by giving a closed environment by using MgO magnesium oxide sealing and sintered at 1100 degrees Celsius for 6 hours. This is the characterization part, where very firstly I have done XRD characterization to confirm the material which I have synthesized, where I have found that there is some XRD peaks are shifted toward the higher angle. It is might be due to instrumental error or might be due to atomic lattice parameter changing. It will be confirmed by the level fitting which I am doing for the paper. And from the calculation, I found that the average crystallite size also decreases after the doping, which is decreased by 4 nanometer, and found that it is 34.5593 nanometer. Then I have also performed the FTIR characterization for the confirmation of purity of the sample, and which is given here, and some peaks are obtained at 3445 centimeter inverse, and also here found that bonding between the lithium and oxygen and niobium and oxygen, which is shown in the figure, and nanocrystallinity is also confirmed by a peak which is at 425. I have also performed the dielectric for the sample which I have synthesized. I found that there is a huge difference between the pure lithium niobate dielectric constant and doped lithium niobate dielectric constant, and found that it is basically because of enhancement in density, and I found that there is rapidly change in dielectric constant after 350 degrees Celsius, which is because of more contribution of ionic polarization. And here I found that the hoping of lithium ion in oxygen vacancies is increased, so that the dielectric constant also enhance. I performed a dielectric constant at 100 Hertz and 1 kilohertz, which I have shown in the figure. I also performed the PE loop hysteresis, which at 250 Hertz and 150 Hertz, and found that the with at lower frequency it is lossy. And in the table for 250 Hertz, in the table I have shown here the remnant polarization and maximum electrical field which I have applied for the both frequency at 250 Hertz and 150 Hertz, and it is at higher frequency it is linear it's behave like linear dielectrics. And this is the conclusion parts, in which I have written here that I have successfully synthesized cerium doped lithium niobate, where cerium is used as the additive, and the XRD results confirm that there is some secondary phases also obtained in form of cerium oxide, and more dense palette is formed. That's mean I successfully synthesize and prevent the problem problem where lithium is and the average crystallite size also decrease, and the more grain boundaries formed, which work as the grain boundary capacitance, which is also help to enhance the permittivity of the system. And there is no any transition found up to 499 degrees Celsius, and the ferroelectric nature is also present in this system, and it is lossy.
Thank you.
Thank you,
Good.
sir.
Good. Good. बढ़िया. Adeline Helen.
Yes, sir.
Yeah, please connect.
Sir, is it visible now?
Not yet.
No, sir.
No, it is not indicating even that you have shared.
One sec, sir.
Yeah. Now it is coming. It will come, I hope. Yes, it has come.
Okay. Good evening, one and all present here. Myself, I'm Adeline Helen, research scholar from Department of Physics, Bharatiya University, doing research under the guidance of Dr. P. Christopher Selvin. And I'm here to present my work entitled Influence of Filler Content on Magnesium Conducting Titration Biopolymer Electrolyte. So these are my objectives: to prepare pure and magnesium nitrate incorporated chitosan biopolymer electrolyte, and to investigate its structural, thermal, and conductivity performance for magnesium batteries on adding the magnesium salt, and to improve its to further improve its conductivity and thermal stability by adding the filler MnO2. So there are many challenges with magnesium batteries, like reversibility of magnesium anode and lack of high conducting electrolyte, that limits the magnesium batteries in production of commercial for commercial applications. So here we have made an attempt to prepare magnesium containing biopolymer electrolyte using chitosan biopolymer. So we have prepared the electrolytes using solution casting technique, using the salt magnesium nitrate, and the filler incorporated as MnO2. So these are the various weight percentages of salt, and among the salt, 68% of the salt incorporated biopolymer electrolyte has shown the highest conductivity, and the same concentration has been fixed to prepare the filler incorporated MnO2 incorporated biopolymer electrolytes of different weight percentages. So from XRD, we confirm the semi-crystalline nature of the pure chitosan. And we can see that the intensity of the broad peak is found to be decreased on adding the salt and the filler, which is because of the composition that has taken place between the salt, filler, and the polymer in the respective polymer electrolytes. So from the XRD differentiograms, we have calculated the degree of crystallinity values. And among the salt incorporated polymer electrolytes, the degree of crystallinity value is found to be minimum for the polymer electrolyte with 68% of the salt. And this has been further decreased on adding the filler. And you can see that among the filler dispersed polymer electrolyte, the one with the 2% of the salt, filler has exhibited minimum degree of crystallinity. So this is expected to achieve the highest ionic conductivity, which has been confirmed using impedance analysis. And the addition, this decrease in degree of crystallinity on adding the filler it's because on adding the filler, it has disrupted the ordered arrangement of the polymer chain, making it more flexible, and it has resulted in increased in segmental motion inside the polymer chains. This is further supported with the DSC analysis that has been carried out. From the TG values are tabulated here. So you can from the graph you can see that the TJ value is found to be increased. Initially, it has been increased on adding the salt. However, it has been found to be decreased on adding the filler. So this confirms the interaction that is taking place between the ionic salt and amine groups present in the chitosan polymer matrix, and the decrease in the glass transition temperature is, indicates the reduction of flexibility of the polymer backbone. and the addition of filler has decreased the TG value further. So this is because the filler particle is able to penetrate the host matrix, developing a polar attractive force with the chain segment. That in turn separates the cohesive force existing between the polymer chains, thereby increasing the flexibility of the chains. So further, AC impedance analysis have been carried out to calculate the ionic conductivity values of the prepared electrolytes, and these are the Nyquist plots and the corresponding equivalent circuit fitted. So from the Nyquist plots, we find that the RB values found to be decreased on adding the salt, and it is found to be minimum for the polymer electrolyte 68% of the salt, and this is for this value is found to be the RB values found to be decreased further on adding the filler, and among the filler dispersed polymer electrolytes, the one with 28% of the salt has achieved the highest conductivity of 1.25 10 power minus 3 Siemens per centimeter. So on adding the filler,
come to conclusion.
sorry,
Come to conclusion part.
Yeah. Okay. Okay, so with that, we conclude that from XRD, the addition of filler in the salt has increased the amorphicity, which is supported with the TG values from the DSA demograms, and Nyquist from the Nyquist plots, the polymer conductivity has been found to be increased by 1 order of magnitude on adding the filler. So with that, we can say that the addition of filler has improvised the structural thermal conductivity properties of the chitosan bipolymer. Thank you.
Thank you. Thank you.
Glenn, why you had chosen this type of divalent cation? Divalent cations are known to move
considering
slower.
the limitations. Yes, that it has limitations like sluggish kinetics, but
Yes. So the system, in fact, there
needs
are
to be
inherent problems with the system.
But is with the divalent cation, sir.
Yeah, divalent cation. The
Yes, sir. Yes,
mangan,
sir.
mangan itself
That is the
is
problem.
a difficult thing. You should have
Yes,
chosen
sir.
some smaller cation, then the property would have been much enhanced and better.
Okay. Sir.
Okay, thank you. Thank you.
Thank you, sir.
Next is Kamana Kumari Mishra.
Yes, sir. Sorry, sir, taking time, I guess. Okay.
I think it will take time. We can take the next one. By that time she can ready.
इसको कामना रेडी कर लो, तब तक अगले को हम लोग कॉल कर लेते हैं.
Yes,
Okay?
sir, yes, sir. Sure. Yes, sir.
Next is Kiruthika. Kiruthika. Kiruthika, can
Hello,
you hear
sir.
me? Yeah, please.
I don't.
Yes, sir.
Tejas is there?
Kiruthika is there.
She's there.
Yes, sir.
Yeah, she is there. Please share.
Yes, sir. Sir, it's visible.
Yeah, it's coming.
It is coming.
Yes, sir. Can I start, sir?
Yeah, please.
Yeah,
it has come.
You can start.
Yes, sir. Good evening, sir. I'm Kritika, research scholar, Department of Physics, Bardar University from Coimbatore. I'm pleasure to present my work. One step. Sir,
Carry on.
one-step green synthesis of zinc ferrite anode material for lithium-ion battery. Zinc ferrite synthesis in many methods, but we focus on green synthesis because green synthesis of transition metal oxide nanoparticle offer
many advantage over other than the traditional chemical methods. Simple, safe, and cost effect. Moreover, it's eco-friendly as no harmless byproduct it introduced into the environmental because of this route, as well as this green synthesis method suitable and affordable synthesis of nanomaterial. That's why we are choosing the green synthesis method. In the green synthesis method, we choose Actinidia delicia. It's nothing but kiwi fruit, because kiwi fruit available in a crude extract are rich in vitamin C and contain vitamin A and E. This extract acts as both reducing and capping agent for the phase formation of zinc ferrite. In this merit, zinc ferrite we choose for the synthesis of zinc ferrite nanomaterial. Next. Synthesis of zinc ferrite anode material, the required amount of zinc nitrate. Sorry, sir.
Please go back. Don't worry. Don't worry. Don't worry. Go back to your back. One more.
Yes, sir. Yes.
One more.
Synthesis of zinc ferrite anode material when green synthesis method required amount of zinc nitrate, iron nitrate, and citric acid was dissolved in freshly prepared kiwi fruit extract. The mixture was blended with stirrer at 800 degrees Celsius after it dried it oven after the calcinated at 700 degree in furnace. Finally, we got the zinc ferrite nano powder. Next, result and discussion. The XRD analysis were carried out to confirm the crystal structure of the formation of zinc ferrite material. The XRD pattern of the zinc ferrite was shown in the figure. The obtained diffraction peaks are well indexed to the cubic spinal structure. It's matched with this place called 22, 10, 12 with a space group of FD3M. We are calculating the crystallite size, dislocation density, and strain of the zinc ferrite material. The obtained average crystallite size of the zinc ferrite material is around 28 nanometer. Next, morphological analysis. The figure exhibits shows the cubic shape. The obtained HRT micrograph uniform distribution of nanoparticle with less agglomeration. The agglomeration might be occurring due to the presence of the magnetic interaction among the nanoparticle. The found grain size in the range of nanoparticle of 300 nanometer to 40 nanometer, which is similar result to the XRD analysis. The cubic shape of the ferrite nanoparticle formation has induced by the fruit enzyme and other compounds like potassium presence in the reagent might be influenced in the morphology of this spinal material. Next, the elemental analysis. The figure shows the chemical composition of the zinc ferrite. The IDAC spectrum of the spinal Z10FO material contains only Z10FeO elements. From the IDAC spectrum, which also a further confirmation of the purity of the sample, and also the atomic percentage of confirmed elements are tabulated. We are taking the elemental analysis. The mapping image of zinc ferrite anode is also another evidence of the there is no purity in the zinc ferrite anode material. This is the FTRT spectrum for the prepared zinc ferrite material. These are the obtained peaks are tabulated. Raman analysis. The green synthesis zinc ferrite nanomaterial was analyzed by Raman analysis. The different Raman active modes are obtained. Next, CV voltammetric analysis. The electrochemical analysis of the prepared zinc ferrite sample with voltammetric analysis. The electrochemical
Show the
setup
result.
of
Show the result.
employed.
Result. Only
You
the
understand
graphic.
this? Show the result.
This is a cyclic voltammetric analysis. The potential window from minus 0.3 to 0.7 voltage. In the normal spinal structure, zinc ferrite, Z10 cations are preferentially occupied tetragonal side, and the Fe cations are occupied in the octahedral side.
Good.
Go to the next
Conclusion
slide.
after my work, the
Yeah.
XRD results reveal the
Good work. Very good.
Thank you.
the uniform
Thank you.
cubic nature of
This is very good. Very good. Rutika. Thank you. Thank you.
Thank you, sir.
It is a very good technique. Good. Kamana Mishra.
Yes, sir. Yes, sir. Yes, sir. I'm ready.
Please connect.
Especially with kiwi fruit.
हाँ, अच्छा बढ़िया. The only trouble is to get kiwi fruit, which is expensive.
But nowadays it is very much easier because of
Yes,
everybody
commonly
is saying,
available.
okay, take the kiwi fruit.
Yes,
Sharing
Kamana
place.
Mishra, please.
Sir, is it visible?
Yeah.
Yes, it is busy.
Yes. Go ahead.
So, good evening to everyone.
Yes.
This happens to be Kamna Mishra from Department of Physics, IIT BHU. So, the topic of my presentation is catalytic behavior of hydrothermal processed nickel oxide. And I have done this work under the guidance of Professor Prabhakar Singh sir. And so these are the contents. And before moving to the result and discussion part, first of all, I would like to explain why do we prefer nanoparticles over bulk material, and what material we have chosen and which method and why. So nanomaterials have advantages over bulk materials because of its high surface to volume ratio, high porosity, and very high and very different physiochemical properties. And these properties are asked for sensing, biosensing, and many other applications. And different metal oxides have also been studied, but among these, nickel oxide shows very good chemical stability, and that is why it has very wide range of applications such as catalyst, electrochromic devices, fuel cell, and gas sensors. And there are several methods to prepare NIO nanoparticles, as I have listed here, but we have chosen hydrothermal method because it is beneficial for producing highly crystallized nanopowders with high purity without any heat treatment in a short time. And as we can see that in this picture, we have seen that the different methods are used to prepare different kind of nanostructures. Structural properties. Now, this is the literature review which shows different synthesis
Can you
methods
skip
and
all
their
this and you can come to your work?
Sure, sir, sure. So this is the experimental technique that is the hydrothermal process which I have chosen to prepare anion nanoparticles. For this, I have taken nickel nitrate hexahydrate as precursor, and then have gone through some processes which is listed here, and then finally got the anion nanopowders. So I'll be moving on characterization technique, results, and discussion. So first of all, I have done the XRD of calcined anion nanoparticle. And as we know, XRD is a technique which is used to examine the phase crystallinity and purity of the sample. In this XRD plot, which I got, some of the extra peaks are coming, which shows that phase is not exactly matched because the sample was calcined only, not sintered. And we are expecting these extra peaks to be removed after sintering. And I have already sintered the sample, and but the results have not come yet, so I'm not showing that. And this is the UV visible study. Band gap calculated from this plot is 1.74 electron volt and 3.01 electron volt that I have calculated. Now, next, I have done the electrochemical analysis of the nanoparticle, anion nanoparticle. So, as we know that CV is used to investigate the reduction and oxidation process.
Show the graph.
Yes, sir.
Yeah, that's good.
So this is the plot which I have got. So from this plot, we can see that the area under the curve in third quadrant is more than any other part, which shows that it has high ORR, that is oxygen reduction rate, and it also shows the high cathodic current. And these results are in accordance with our application purpose, that is cathode material for SOFC. Now I would like to conclude my presentation here. So I have prepared anion nanoparticle by hydrothermal method, have done the XRD of calcined sample to understand the structural change in the sample after sintering and before sintering. And then I have calculated the band gap, and then have done the electrochemical analysis of the sample, and my work is still going on. Several characterization techniques are still left to do.
To be done.
So this
Good,
was the
good.
result, sir. Thank you, sir. Thank you,
Thank you.
everyone.
Good. बढ़िया.
So these are the differences.
Check the XRT that indicates something very complex. Anna?
Sure, sir.
Yeah. Good. Tejas Sharma. Tejas Sharma.
He's there. He is there.
It just has a
Yeah.
start timer also.
हाँ, लेकिन audible नहीं है.
हाँ.
Am I audible?
Yes, now you're audible.
But where is presentation gone? Yeah.
Yeah.
Can you start?
So, can I start?
Yes, you can start.
Please.
Good evening, one and all. I'm here to present a small topic on that is ionic liquid doped polymethyl methacrylate for energy applications under the supervision of Professor Pramod Kumar Singh. This is my presentation flow. So before I move further, I would like to discuss what current problem in my system is. That the main problem is the low conductivity. Here are numerous approach to that. The first one is use of plasticizer, addition of ceramics, and the doping of ionic liquid. In this work, we have work on ionic liquid to enhance our electrical conductivity. So, ionic liquid play the role of a kind of charge carrier, we can say, in non-volatile plasticizer. Also, it provides a good source of iodide to good performance in DSSC. Also, it's a good novel candidate for electrochemical devices. So this is a device based on the polymer electrolytes. First one is battery, fuel cell, sensor, electrochromic display, DSSC, and the supercapacitor. My main work is on the last 2 points, that is DSSC and the supercapacitor. So this is a general representation of both the devices, EDLC and DSSC. So as you can see from both the devices that electrolyte material is common. We can see from the EDLC as we can on the DSSC part. The electrolyte portion is common. So my main work on this portion. This is the preparation of polymer electrolyte. I'm not going to discuss this as this is very obvious as we have the shortage of time. So I'm directly coming to the result and discussion part. The first one we have the impedance plot. So in the impedance we can see that high frequency region the graph contain a semi-circular spore that attributes the parallel permutation of bulk resistance and capacitance of our developed polymer electrolyte film. And second we have the conductivity. As we all know that conductivity increases with increase in the number of charge carriers. So in this case, we can see from the graph that there is increase in ionic conductivity with increase in concentration of ionic liquid. And the third one, we have the dielectric constant. It is very clear from the graph that the dielectric follows the same pattern as we observed in the conductivity figure. And next we have the FTI spectra. In the FTI spectra, we can see the pure PMMA curve shows CH stretching, carbonyl group that is CEO, and the CH bending respectively. And the other common peaks are of PMMA are also present in ILDO polymer matrix, which can be confirmed from the FTI spectra. And next we have the XRD and the TGA plot. In the XRD, you can see that both the samples, that is of pure PMMA, shown in red color, and the IL doped PMMA, that is shown in the black color. There are two broad peaks observed at 13.8 degree and the 13.2 degree, which is confirmed as a semi-crystalline nature observed in PMMA matrix. On the other side, the IL doped PMMA film XRD spectra clearly showed broadness in peak, which interrupts the decrease in crystallinity nature. Next, we have the fabrication. In order to fabricate EDLC, we have employed the same optimized IL doped polymer film in polymer matrix, sandwich in between activated porous carbon, synthesized from cornstarch material coated on current collector, that is our graphite sheet. This is the CV of the prepared cell. calculating for calculating the specific emission, we simply use the formula I upon S, and here we get the specific emission value of 130 millifarad per gram at the scan rate of 50 millivolt per second. So this is the next we have fabricate second device, that is a DSSC. So to develop a laboratory scale DSSC, we have used high conducting fluorine doped tin oxide glass plate, which is washed with double distilled water and acetone. To prepare a working electrode, first we have a blocking layer, that is of TiO2 paste, was coated on
Tejas,
the
can you come to the
Tejas,
conclusion?
show the result, Tejas. We know this.
Go ahead.
Okay, so this is the photovoltaic parameter extracted from the current density voltage curve of DSSC.
Okay.
We have optimized first the maximize polymer electrolyte film and fabricate the device and obtain a efficiency of 3.54% at the current density 7.23 milliampere per centimeter square at the voltage of 0.61 volt. So at the last we have conclude we have synthesized high doped polymer electrolyte film in to attain maximum conductivity. In order, you can see that 10 to the power minus 5 C1 per centimeter. Also, we have developed a supercapacitor based on maximum conducting polymer electrolyte film, which shows the specific capacitance of 130 millifarad per gram. Using the same optimized film, we have developed a DSSC which shows a short circuit current density of 7.23 milliampere, and the efficiency is you can see that 3.54% at Bunsen condition.
Good.
So,
Tejas ji, do you have any idea what is the TG of PMMA?
Sorry?
What is the glass transition temperature of PMMA?
PMMA?
TG of PMMA.
Sir, I think it's around 303 degrees Celsius.
No, not that high. That is, you are talking about the melting. I'm talking about glass transition temperature. Second thing, the conductivity that you are reporting, that is of the order of 10 power minus 5 Siemens per centimeter square. So the effective thickness of the polymer inside the DSSC, that is of around 10 to 20 micron, that will offer internal resistance of around 100 ohm. Please check the current that you are reporting. Right? डॉक्टर साहब से पूछ लीजिएगा, वो डिटेल समझा देंगे आपको.
Okay, sir. Thank you, sir.
Sushant?
Yes, sir.
Yeah,
Stop
please.
sharing. Tejas, stop sharing.
सर सुशांत ने अभी ढपोला का प्रेजेंट किया था ना?
हाँ, वो ढपोला का किया था, इसका अपना भी पेपर है.
अच्छा.
वो ऑन बिहाफ ऑफ ढपोला था.
Okay.
Am I visible, sir?
Yes, yes.
You're not visible.
Yeah.
Slides are visible.
Yes, sir. My slides are. I'm
bolo,
talking
bolo.
about.
Candidates and participants should also be visible.
Yeah, it
Okay,
should
okay.
be, because it should
वो
be.
पता नहीं वीडियो उसका नेटवर्क सपोर्ट करेगा नहीं करेगा.
That's why.
बोलो बेटा, सुशांत बोलो.
Good evening, everyone. I am Sushant Kumar from Center of Excellence on Solar Cells and Renewable Energy, Sarda University. I'm doing PhD under the supervision of Professor Pramod Kumar Singh. And I am going to present my recent work on preparation, characterization, and application of low viscosity ionic liquid doped solid polymer electrolyte. This is the method which I have used for the preparation of polymer electrolytes. I have used simple solution cast technique, and I have used EMIM TCM ionic liquid for the doping, and I have directly goes to the results. So these are the XRD and FTIR graphs for the pure PVDF HFP film and ionic liquid doped pure PVDF HFP film. So the black portion is showing the pure PVDF HFP and the red portion is showing the ionic liquid doped PVDF HFP. So in the XRD graph, you can see that the pure PVDF HFP showing the 3 peaks at 17.7, 20.3, and 26.6, sorry, 4, 38.9 degree. And by seeing these peaks are showing the semi-crystalline nature of PVDF HFP copolymer. And when ionic liquid is doped into them, then we can see that there are two peaks, 26.6 and 38.9 degree 2 theta values are disappear, and the other peaks are broadened, which showing that the crystallinity of the PVDF HFP is decreased when ionic liquid is doped into them. And in the FTIR graph, you can see that the peak at 487 centimeter inverse is downshifted to the 481 centimeter inverse when ionic liquid is doped into it, and the peaks at 524 and 976 centimeter inverse is are disappear when we doped ionic liquid in them. And the peak at 872.74 centimeter inverse, which is correspondence to the amorphous phase of the polymer, is gets narrower. Sorry.
Go ahead. Go ahead.
Directly come to the conclusion. I think most of people, they already know it. Directly come to conclusion.
Oh, okay, sir. So these are the TGA and POM micrographs, and this is the conductivity graph and LSV and T-ion graph. Here you can see the dielectric studies, and now I directly come to the conclusion. That, I have prepared gel polymer electrolyte by using PVDF HFP as a copolymer and ionic liquid EMIM TCM as the doping agent, and I have done XRD and POM, which indicates the semi-crystalline nature of PVDF HFP film is decreasing when I have doped ionic liquid in them. And the interaction of ions from ionic liquid with polymer chain and functional group present in the films are revealed by the FTR analysis. And by TIN studies, I have concluded that there are the major charge carriers are ionic, which is 93%, which confirmed by the DC polarization technique. And the relaxation time corresponds to relaxation frequency, which is in the in my dielectric studies in 10 delta graph, that the 300, 200, 300 and 400 weight percent of ionic liquid doped films, showing the nearly 10 raised to power minus 7 second. It shows that they have fast ion migration. The value of ionic conductivity varies with ionic liquid content and reached a maximum value of 3.7 into 10 to the power minus 2, which is for the 300 weight percent ionic liquid doped PVDF HFP film. The same film, that means 300 weight percent doped ionic liquid film, is showing LSV, that means electrochemical windows, stability window is a 2.0 volt range, which is I think sufficient for the energy storing devices. Dielectric plots also follow the same trend as conductivity, and increasing dielectric constant with increasing weight percent of ionic liquid is observed. The blend gel polymer electrolyte is substantially for electrochemical devices, practically for supercapacitors. Thank you.
Thank you, Sushant. Good work.
Sushant, may
Yes, sir.
I? Conductivity is 3.7 into 10 to the power minus 2. This is ionic
Yes.
liquid based. So
Yes,
is
sir.
it possible?
Yes, sir, it is possible, and I know why you are asking, because this order conductivity is also shown by the ionic liquid which I have using.
Okay.
So yes, sir, this is possible, and I have rechecked it many times.
You just check that whether the ionic liquid is segregating out or not, because you have added 500 weight percent, close to 500 weight percent.
Sir, actually, that's why I have taken 300 weight percent film, because after that the ionic liquid is not completely trapped in inside the polymer. That's why I have chosen the
300 is also quite high. You check with some other parameters if there is any segregation. No?
Okay, sir.
गुप्ता जी यही पूछ रहे थे ना?
नहीं, मैं पूछा था अच्छा है कंडक्टिविटी 10
हाँ
-2
हाँ वो
लिक्विड
सेग्रीगेट अगर होने
इलेक्ट्रोलाइट के
लगेगा तो
बराबर है, तो
बिल्कुल
अच्छा है,
बिल्कुल
बहुत
बिल्कुल
अच्छा है।
सेग्रीगेट अगर हो गया तो बिल्कुल आ जाए।
अरे वाह, अच्छा है।
गुड गुड, ठीक है,
वेरी
थैंक यू
गुड,
सुशांत।
वेरी गुड।
Thank you, sir.
अभिमन्यु सिंह।
Yes, sir. Yes, sir. Is my screen visible?
Yes, it is visible.
Okay, sir. So can I start?
Please.
Okay. So a very warm good evening, everyone present here. I am Abhimanyu Singh from Gautam Buddha University. I am master's student, and I am here to give my presentation on the topic of electrical structure and electrochemical performance of polyethylene oxide doped with 1-ethyl 3-methyl imidazolium tricyanomethanide ionic liquid. So my layout of my presentation, it will include the introduction, motivation, methodology, results and discussion, and finally the conclusion part. Let's start with the introduction part. There are several difficulties to increase the production, storage, and the energy distribution which are faced by the researchers around the world in meeting this energy demand. So in order to find the answer to these challenges, an adequate ion conducting polymer electrolyte is highly required. So my motivation of today is to synthesis the high ion conducting solid polymer electrolyte having very high ionic conductivity in the range of 10 to the power -1 to 10 to the power -4 Siemens per centimeter with a high capacitance in our electrochemical devices. So the solid polymer electrolyte films were synthesized using the simple approach, that is solution cast technique. I'll not go into the details of this. Next, we have the schematic of the electric double layer capacitor, which was fabricated using graphite sheets as a current collector and laboratory scale dried porous carbon. Next, we have the results and discussion part. As you can see from the impedance plot, the focal plot at a high frequency region, a semicircular spur is seen, followed by a very hike at a very speedy rate towards the low frequency region. The semicircular spur at frequency area corresponds to the parallel permutation of bulk resistance and the capacitances of the solid polymer electrolyte freestanding films. The bulk resistance attributes to the dielectric polarization and the ionic moment in a polymer electrolyte. Next, we have the conductivity plot. We can see that on adding the ionic liquid in the polymer, the ionic conductivity increases sharply up to 8% of ion concentration in polymer matrix, which is due to the increase in the degree of ion dissociation, which is because of the increase in number of charge carriers. After 8% ion concentration in polymer matrix, the ionic conductivity decreases and it reaches up to the range of 10 to the power -6 Siemens per centimeter, which is due to the formation of maybe the ion clusters with the reconjugation of the ions in the PEO polymer. Next, we have the dielectric measurement. We can see that after 8% there is a certain decline in the value of the dielectric constant, which is because of the formation of the cluster of the ions. Hence, we can conclude that this trend in this dielectric measurement figure, it shows a very good agreement with the ion conductivity data. Next, we have the FTIR data. In the FTIR, the formation of the new peaks at 2164 per centimeter and 1339, remember, due to the alkynes and the nitro groups, it shows the confirmation of the molecular interaction between the ionic liquid and the polymer chains. In the XRD data, it was noticed that the doping of the IL, the peak intensities, it goes down, which suggests the enhancement towards the amorphous behavior. It was well documented that the amorphous region is conductivity rich portion, and hence the doping IL in PO could be novel approach and well correlated with our conductivity measurements. Next, we have the TG analysis. It is clearly seen that there was no major weight loss till 350 degrees Celsius. If beyond this temperature, polymer PEO, it completely degraded at 400 degrees Celsius. Whereas in ionic liquid doped PEO polymer, as shown in the figure, the solid polymer electrolyte was stable up to 380 degrees Celsius and completely degraded at 400 degrees Celsius. The increase in thermal stability of the ionic liquid doped SPE suggests the effect of IL on thermal stability after incorporating with polymer matrix, which increases by 20 degrees Celsius. Next, we have the cyclic voltammetry performance of our supercapacitor. It was evacuated at scan rate of 50 millivolt per second on a voltage range of 0 to 1 volt, as shown in the given figure. The CV profile shows an undistinguishable square-shaped hysteresis loop, which is the basic feature of the EDLC. The deviation from the square shape in the CV profile suggests the equivalent series resistance, which is present in the real capacitor. The calculated value of the specific capacitance shown by the fabricated EDLC at 50 millivolt per scan rate. It reaches up to 13.6 farad per gram. Now coming to the conclusion part, we have successfully synthesized the ionic liquid 1-methyl-3-methyl indazolium doped in PEO polymer electrolyte using solution cast technique. The structural and the optical properties were characterized by XRD and FTR techniques that shows that the synthesized solid polymer electrolyte is homogeneous in nature. The electrical properties of the aldol polymer electrolyte films were successfully characterized via conductivity and correlated with the dielectric constant. Finally, we have fabricated the supercapacitor device by sandwiching the optimized solid polymer electrolyte film in between the porous carbon electrodes, which shows the specific capacitance of 13.6 farad per gram at the scan rate of 50 millivolt per second on a voltage range of 0 to 1 volt. Still the study on this research is still going on. This is my team, and thank you for your attention.
Good, good. You are a PG student?
Yes, sir.
Oh, so nice. Very good.
Good
Very
work.
good.
Really
Thank you,
good work.
Next is Deepti Yadav.
Yes, sir. I'm here.
Please share.
It is not Deepti, it is Dipti.
Sir, are my slides visible?
It is coming. Yes, it is visible.
Yes, sir. My name is Deepti Yadav and I am research scholar from Department of Physics, MMB, Banaras Hindu University. The topic of my presentation is magnesium perchlorate mixed cross-linked cornstarch, a flexible and highly conducting polymer in salt electrolyte. I have synthesized this film where the starch is taken as host polymer and magnesium perchlorate is taken as a salt, which is mixed and homogeneous mixture is made, which is finally by using the solution cast technique is casted, and the picture of the sample is there in the slide, which is transparent, and at the back side you can see the name of the lab, which is where the alphabets are clearly visible, which indicates that the film is completely transparent. And these are the actual pictures of the synthesized sample, where you can see the sample is stretched to 1.2 times, and it is stretchable or bendable and can be twisted multiple times. And these are the ESR plots, which is equivalent series resistance. Here we can see with the increase in the salt concentration, the value of the ESR is decreasing. And at the lowest salt concentration, where 1 gram starch and 0.5 gram salt was used, the resistance is high, which are indicated by the black dots. Coming to the conductivity values, here we can see with the increase in the salt concentration, conductivity is also increasing, but there is a peculiar point at 150 weight%. The point is slightly raised and is not in just like the trend which is being followed up, and this is in line with the same images which I'll show in the upcoming slides. These are the structural analysis, where you can see that there are certain peaks in the pure salt XRD, but those peaks have disappeared, and with the increase in the concentration of the salt, the hump in the XRD patterns is decreasing, which indicates the amorphous nature of the film. And the absence of the signature peaks of the salt confirms that whatever amount of salt is being added in the starch, it is easily accommodating in its host matrix. And these are the FTIR patterns. Here we can see that at 3600 wave number, the width of the peak is increasing with the increase in salt concentration, which indicates the variety of OH bondings. Like there are different H present, the hydrogen of the starch, the hydrogen of the water, they are interbonding, and there are intermolecular bondings and intermolecular bondings, which are increasing, and the amorphous nature of the film is indicated, and the acceptance of the water. And these are the same analysis, where at the lowest salt concentration, some starch granules are visible, and with the increasing salt concentration, as I pointed out in the conductivity graph, there is one peculiar point which is not in line with the conductivity graph. That is the salt concentration, where starch is 1 gram and the salt is 1.5 gram. you can see there are some salt segregations. Because of the salt segregations at this concentration, the conductivity slightly got increased, but they are not in order, structural order. With the then when the salt to starch ratio is 1:2 and 1:2.5, you can see some small dots getting visible. These are small structures which are lesser than the micro structures in the range of nanometers, which are developing, and as resultantly in the salt to starch ratio, which is 300 weight%, the salt segregation is clearly visible, which indicates the increase in conductivity that is in the range of 10 to the power minus 2. And finally, the conclusion that the study system is low cost because we have used starch as a host polymer, which is environmental friendly, and the preparation does not require any expensive technique because it is a salt cast solution cast technique, and the conductivity of the system is in the range of 10 to the power minus 2. And XRD, FTIR, and SEM patterns are in line with each other, which indicates cluster formation, and the salt is easily getting accommodated. Hydrogen bonding is present, which makes the which makes the synthesized sample flexible, bendable, and twisted, and can be twisted to any shape. So it is a potential candidate for electrochemical applications. Thank you.
Good. Good.
Very good.
Badhiya, badhiya.
So conductivity is very, very high. 10 to the minus 2, 5, 5.6.
5.6, 7 10 to power minus 2.
Minus 2. It is liquid electrolyte conductivity.
No, so this is jet electrolyte.
Yeah, of course, but we get
Comparable to that.
It is very good. Excellent. Excellent.
She has got in other material, she has got 0.2 Siemens per centimeter.
Wow.
In this, she is getting 0.05. In one of the material, she has got 0.2 something Siemens per centimeter.
Thank you, Deepti.
Thank you.
Badhiya.
Thank you, sir.
Next is Kalyan Chavan.
Yes, sir. Am I audible?
Yeah, yes, you are audible.
Can share.
Wait a minute. My screen visible, sir?
Yeah, it is coming. Please start.
Yes.
Good evening, all. My name is
Yes.
Kalyan Chavan. Today I am going to present my work entitled Structural and Optical Investigations on Direct Current Magnetron Sputtered CZTS Thin Film. I'll come to directly my experimental details. In this work, I have deposited CZTS thin film on glass substrate by using DC magnetron sputtering technique. In this experiment, I have chosen 4 different temperature, that is deposition temperatures, starting from room temperature to 400 degrees Celsius in the steps of 100 degrees Celsius. These depositions I have carried out in argon ambient at 80 SCCM flow rate, and deposition time I keep for 20 minutes, and the deposition power, DC power, it is 50 watt throughout the deposition. So if I talk about my characterization, this is what first characterization, it is X-ray diffractogram. If you look at these X-ray diffractograms A, B, C, D, and E, I have arranged these diffractograms as per the temperature. So the topmost E is CZTS grown at 400 degrees Celsius, and D is at 300 degrees Celsius. So it is quite, if you look at these two plots and if you compare these two plots, it is quite interesting that here in X-ray plot E, it is near about 28 degree and it is 112 plane. And if you compare that plot with D, here there is a complete change in orientation of my material. and definitely it will helpful for me in order to address the lattice mismatch issue while fabricating substrate solar cell. Now, if you compare, if you talk about C and D, as upon decreasing deposition temperature, the crystallinity of thin film goes on decreasing. Rather than saying this, I can say that at room temperature, whatever the material I have grown, it is purely amorphous. So this is what the X-ray diffraction technique tells us. From this X-ray diffractogram, I have obtained several parameters, that is crystallite size and dislocation density. Here it is, this plot shows us as substrate temperature goes on increasing, the crystallite size increases and dislocation density decreases. This may be because of what? As substrate temperature increases, we know that in order to grow bigger crystals, we must have requirement of energy. And in sputtering technique, we know that atoms are there which stick to substrate, but after sticking, we need energy to mobilize those atoms so that bigger crystal can grow. So here this plot shows us as substrate temperature goes on increasing, the crystallite size also goes on increasing. On the other hand, we know that when crystallites are bigger and bigger, definitely the defects or dislocations they decreases. Here, exactly that kind of trend one can observe in this plot. This is another one technique I have used to probe my thin film, that is optical technique, that is UV visible spectroscopy. Here, this is a talk plot, and if you look at these talk plots, I have arranged these talk plots as per the deposition temperature, and it is very clear that upon increasing substrate temperature, band gap goes on decreasing. So here, with the help of this finding, what I can do, I can go for the band gap tuning while fabricating my substrate solar cell device. And here my results and conclusion. So with the help of DC sputtering, I have deposited CZTS thin film on glass substrate. These depositions I have carried out at 5 different deposition temperatures. X-ray spectroscopy depicts that a deposited CZTS possesses tetragonal crystal structure, and also it is very clear that as the substrate temperature increases, crystallinity of thin film also increases. And with the help of top plot, we can conclude that upon increasing substrate temperature, there is a decrement in band gap. Thank you.
Good. Kalyan, what was the substrate? Ordinary
It is glass substrate, sir.
Soda glass?
Yes, sir.
Okay, good, good.
Yes,
in the,
sir.
yeah, in the crystallite size
Yes.
and this
Thank you, sir.
You showed. Can you show the graph? Crystallite size.
Yes, sir.
Here you have a 300 double.
Yes, sir. Here it is.
Yeah, two data. How?
Yes, sir. Yes, sir. Here it is. Can you see this?
At 300 degree, you have 2 points. That is, Professor Gupta is asking.
Why? There should be.
It is some mistake, sir. Actually, it is not like that. Sorry, sir. I will rectify, sir. I will rectify this, sir.
Because you are presenting, so you have to make it okay, you know.
Good, good. Next is Deep Taraka Roy.
Yes, sir.
Yeah, Deep
Sorry,
Taraka
sir.
Roy. Kalyan, please stop sharing.
Kalyan, stop sharing.
Yes, sir.
Yeah, okay, good.
Yes, please.
After Deep Taraka, we will have one talk which was left over yesterday, Dr. Amit Saxena. That will be the last one for today's session.
And the last one of the conference also.
Correct.
So,
So today's session.
Tarka, please start. Yeah, correct. Fine.
Sir, full screen.
Yeah, we can see. We can see this. Fine. Go ahead.
Okay, sir.
Yeah, it has become full screen.
Good evening. I am Tarka from Department of Physics, University, Lucknow. I am presenting the topic grid synthesis of bismuth ferrite nanoparticles for PVA bonding bismuth ferrite nanocomposite membrane to study the ionic conductivity with varying relative permeability. First of all, I have synthesized the bismuth ferrite nanoparticles using the leaf extract of Moringa oleifera. Then it is employed to construct the nanocomposite membrane PVA pani BA4. This is the synthesis process. Now the characterization techniques. This is the excited pattern of the green synthesized bismuth ferrite nanoparticles. The excited pattern matches well with the Vespitius card number, and it confirms the existence of BMFE03, and the calculated average crystallite size is 12.16 nanometer. This is the efficient images of the synthesized bismuth ferrite nanoparticles. Most of the particles are spherical in nature, spherical in shapes, and some are the disc-like, and all the particles are in the nanoscale. This is the EDS spectrum. It confirms the existence of oxygen, iron, and bismuth. So it confirms the formation of bismuth ferrite nanoparticles. This is the round spectrum of the green synthesized bismuth ferrite nanoparticles, and the peaks corresponds to wave number 140.226, 407.539 represents the peaks of synthesized BiFeO3. These are the API spectra of both the plant Moringa oleifera plant extract and the green synthesized bismuth ferrite nanoparticles. The sum from the APR spectrum of the green synthesized bismuth ferrite nanoparticles, it is seen that the peaks represents the peaks as well as the plant extract. It confirms the presence of some plant components as a functional group in the synthesized materials. These are the effective pattern of the PVA pani and PVA BFO membranes. Here we have done a comparative study between PVA pani membrane and PVA pani BFO membrane. The start peak represents the peaks of pani, and the peak corresponds to 39 and 47 degree, represents the composite effect of PVA pani, and the single peaks at 57 degree is the same for the PVA pani BFO membrane. It represents the peaks of BFO. It's not correct. Okay. These are the images of the synthesized PVA pani BFO membrane. Represents by figure C and D. The ARP represent the PVA pani membrane. The PVA pani BFO membrane shows the homogeneous structures in surface morphology, and it is similar like flower petals. They have some dark surface are observed. Probably the dark surface because the high contact and water contact angle there because the little hydrophobic nature than PVA pani membrane for the PVA pani membrane. These are the Raman spectrum of the PVA pani and PVA pani BFO membranes. The peaks represents the polyaniline, existence of polyaniline and PVA. This is the optical images of the PVA pani membrane and PVA pani BFO membrane. PVA pani BFO membrane represents an uniform homogeneous surface morphology. These are the FTI spectra the PVA pani and PVA pani BFO membranes at different humidity conditions. The API band between the range is 3,000 to 4,000. The number represents the higher nutrients and peaks in comparison to the PVA pani BFO. That represents the more wavelength. That means the PVA pani membranes can absorb more moisture from the environment. This is the weight variation from relative humidity for the two different membranes. And the picture represents the PVA pani membrane absorb more water particles from the surroundings in comparison to the PVA pani membranes. So now I have calculated the ionic conductivity. This is the impedance total data, and from this I have calculated the ionic conductivity with different humidity conditions. And from this plot, it is seen that the PVA pani shows a stable ionic conductivity with all humidity conditions. But PVA pani membranes shows some variation in conductivity. It also shows some higher conductivity with respect to PVA pani membrane. That means after inserting the BFO as an nanofiller in the PVA membrane, it makes stable the membrane system against the humidity of the ambient. Conclusions: the synthesis process, green process is environment friendly and cooperative process, and the changing ionic conductivity membrane humidity can apply for humidity sensing applications and electrochemical devices, which will be stable for environmental application at any humidity conditions.
Diptorg, I have two comments.
Yes, sir.
Number one, your size calculation from the XRD and from ACM, they differ by multiple orders, because the particle size that is visible in ACM, that is much larger than some 10, 12 nanometer that you have reported. Please verify it. You know?
Okay.
Second thing, the plot that is now visible, PVA pani is known to have strong humidity dependence. Your result is showing almost constant.
Constant.
PVA, sir, after
I'm talking about only PVA pani. PVA pani BFO is your system. I won't get into that easily. But PVA pani, the base polymer, it is strongly humidity dependent. So please recheck it.
Okay. Thank you, sir.
Good. So the last talk speaker is Dr. Amit Saxena.
तो ये कल वाला है ना? तो
हाँ, कल वाला है.
तो हम लोग को
नंबर बता
तो
दो.
जोड़ने का नहीं है इसको.
अरे जोड़ लीजिए भाई गुप्ता जी, क्यों नाराज हैं? C18.
जोड़ दीजिए सर.
C18.
C18 नीचे लिख के जोड़ दीजिए. पीयूष सर, डॉक्टर पीयूष सोनकर, प्लीज नोट दैट वन ऑफ द पार्टिसिपेंट ग्रुप
सीरियल नंबर में है मैडम, लिस्ट में है वो, Day-2 वाले में
C18 में है, वहां से आज ले लिया.
48 के बाद है वो,
लिस्ट में लिखा हुआ है.
नहीं. अमित सक्सेना इज C18.
हाँ मैं वो लिस्ट में है, बीच में है.
कल के लिस्ट में था ना?
नहीं, सेकेंड डे में भी आज डाला गया है. C18 डाला गया है 48
चला
के
गया
बाद.
है. ओके,
इट इज इंक्लूडेड.
चलिए अच्छा.
आज के लिस्ट में भी है सर, आज के लिस्ट में है C18.
अच्छी बात. अमित प्लीज स्टार्ट.
48 के बाद.
स्क्रीन दिख रही है? स्क्रीन शेयरिंग लिख के आ रहा है, अभी तक आया नहीं है. होपफुली आ जाएगा.
कहीं और पे भेज दीजिए अपनी पीपीटी, कोई और प्रेजेंट कर देगा, आप बोल देना.
अरे नहीं, अभी आ जाएगा. अमित को सुन के हम लोग क्लोज करेंगे.
यहाँ से चलने में समय लगेगा ना संदीप जी.
ये वो अमित जी का, ये भास्कर भट्टाचार्य जी के स्टूडेंट हैं, तो हैवी फाइल होगा शायद, इस वजह से नहीं हो पाएगा.
नहीं, ये अब जो है वो इंदौर में अपना इंडिपेंडेंट चमका रहा है।
वो भी हमारे गुरुजी के अंडर में है।
हाँ हाँ हाँ।
ठीक ठीक है।
तीनों बातों का स्वभाव अलग अलग है।
नेटवर्क इशू दिखा रहा है अमित सक्सेना।
जो वाटिका है ये योग वाटिका है। योग
अमित एक बार उसको शेयरिंग स्टॉप करके फिर से कनेक्ट करो, आ जाएगा।
गुरु की वाटिका उपयोग वाटिका है।
हाँ गुड, अब करो। ये न्यूज़ कौन देख रहा है यार?
So can you see my screen?
Yes, we can see your screen. PPT is not yet open.
But only our 4 photographs are coming.
Yes.
Photographs. Acha.
That too, our photographs are still in the still.
नेटवर्क प्रॉब्लम है इसमें।
हाँ, नेटवर्क प्रॉब्लम है।
So actually, I've been connected with the mobile data, and I think 90% of data is already shrink.
Amit, you can send to anybody or to us. We can just present.
मुझे भेज दो।
गुरुजी को भेज दो आप। गुरुजी का डाटा पूरा बचा हुआ है।
डाटा तो यहाँ देना
नहीं तो वहां से प्रेजेंट कर दें बिना पीपीटी के ना, वो पीपीटी देख के।
अरे रिजल्ट बता दे बस सीधा क्या नया किया।
हाँ।
कॉन्फ्रेंस का लास्ट प्रेजेंटेशन भी हो सकता है,
कुछ भी हो सकता है।
बैकग्राउंड क्या है?
पीपीटी विजिबल हुआ
नहीं यार,
नहीं, बस यही लिखा आ रहा है, अमित सक्सेना इज स्टार्टिंग टू शेयर।
इंडिया में 8:30 हो गया। 8:40
8:40 हो गया गुप्ता जी। सऊदी में कितना बजा?
अभी 6:10 हुआ है।
जाओ तब। आज पूछ के आए थे कि नहीं?
नहीं, 6:10 पे पूछने की जरूरत नहीं पड़ेगी ना।
अरे नहीं पांडे जी,
मैंने बोल दिया था आई विल बी लेट।
देखिए,
अरे गुप्ता जी हैं, कोई बात नहीं है।
अमित भाई मुझे भेज दो।
आवाज भी तो नहीं आ रही।
प्रॉब्लम है, नेटवर्क प्रॉब्लम।
मैं उसको कॉल कर लेता हूँ।
लग रहा है सर कि बाद में कहीं अपने सुपरवाइजर का नाम न बता दे, इसलिए बंद ही करवाना ज्यादा अच्छा है।
पावर आ गई क्या डॉक्टर सिंह?
हाँ,
पावर आ गया क्या?
अरे पावर बहुत देर से आया हुआ है भाई।
पर मैं
मुझे लग रहा है कि अगले वाले प्रेजेंटर को अगर हो कोई तो उसको मौका दे।
अब अगला आई नहीं है ना।
कोई नहीं है भाई साहब, कितना
ये लास्ट है। नहीं तो लोगों को टाइम मिल गया कैलकुलेशन करने के लिए ना।
अच्छा अच्छा अच्छा।
कहाँ
हाँ, सब लोग
कैलकुलेशन?
गुणा-
बातचीत कर रहे हैं तो कहाँ से कैलकुलेशन होगा?
कैलकुलेट करिए भाई साहब, उसके बाद टाइम नहीं देंगे।
गुप्ता जी जल्दी से कैलकुलेट करिए, 9 बजने वाला है यहाँ।
मैं तो एक्सेल में नंबर डालूंगा, बस भेज दूंगा तुरंत।
गुप्ता जी नंबर डाल चुके होंगे सर।
All the experts,
मैं पेपर में
please
लिखा हूँ। मैं
गुप्ता
पेपर
जी
में
बाद
लिखा
में
हूँ।
डालेंगे।
पेपर में लिखा
करिए प्लीज,
share
फटाफट करिए।
your result.
9
Professor
बजे
Bhattacharya,
हम लोग शटर डाउन कर देंगे जी।
please ask all the experts to send their results to the Dr. Piyush. He will only add up the result of the Dr. Amit. No? Please, all
हाँ
the
हाँ हाँ,
experts, please share your results with the in the group with the
हमको अभी एनर्जी नहीं है, बिना एनर्जी के कैसे भेजेंगे? कुछ खाने
नहीं तो
पीने
एनर्जी ले लो पहले कहीं
खाने पीने का दो, चाय पिलाओ या फिर
भास्कर यहाँ से थोड़ी एनर्जी बूस्ट उसको दीजिए।
वर्चुअली नाश्ता करा सकते हैं।
नहीं SMS से दे दो ना।
नीलम दी देखो वो अपना बैठ के खा रही थी, देखो ना नीलम दी अपने
नीलम दीदी सवेरे से 8:30 बजे चेयर पे आती है, फिर 9 बजे उठेंगी। आज 9 बजे भी
दीदी
नहीं उठेंगी, आज तो 10
दीदी
बजे
हम लोग भी सुबह कितना 8 बजे से मैं भी आया हूँ।
नहीं हम लोगों को कौन आप छोड़े हुए हैं।
आप लोग हिलते डुलते हैं ना, हम तो जरा भी हिलते डुलते भी नहीं। ओके, फॉरगेट अबाउट दैट। प्लीज सेंड द रिजल्ट टू द Dr. Piyush. All of you, please send the result to Dr. Piyush so that he can compile.
I will send just after finish the last talk.
No, last talk don't wait for the last.
5 minutes. Within 5 minutes I will send. Within 5 minutes.
Hello.
हाँ जी,
Send that last one separately.
ये तो बाकी लोगों के लिए तो अब काम खत्म हो गया ना।
सक्सेना जी का प्लान लिया के प्रेजेंट हो गया है।
बैठे रहिए लास्ट तक।
नहीं पूछ के बताइए भाई।
Time information online on YouTube.
अमित रहने दो भैया, ये नहीं आ पाएगा। सभी एक्सपर्ट्स ने मान लिया, आपने प्रेजेंट कर दिया है।
ठीक है डॉक्टर, तुम पर भी कुछ खाने पीने लगे।
एसपी पांडे, हम लोगों का काम खत्म हो गया।
नहीं सर, अभी कैसे खत्म हुआ?
हाँ, हम कल वाले में थे।
कर रहा है।
हाँ तो कोई बात नहीं, कल वाला कैंडिडेट है, ध्यान रखिए।
एक ही तो है, वो बोल ही नहीं पाया।
लास्ट कैंडिडेट कल वाला है। जो लास्ट कैंडिडेट है सर, वो आप ही के बैच का है, इसलिए आपको बैठे रहना पड़ेगा।
लेकिन वो आज भी तो लास्ट हो गया।
आज भी लास्ट हो गया।
आज भी यही प्रॉब्लम थी, कनेक्ट नहीं हुआ था।
मैं कल तो उसके किसी का कुछ इमरजेंसी हो गया था, चला गया था, इसीलिए।
क्या पोस्ट की तरफ से इतनी आवाजें आ रही हैं क्या?
नहीं, हमारी तो हम समझ नहीं पा रहे कि किसका है। सब कोई म्यूट भी है। विवेक कुमार सोनू जी म्यूट नहीं है।
नहीं, मैं तो म्यूट नहीं, लेकिन मेरे यहाँ कुछ है नहीं, मैं तो कॉलेज में ही बैठा हूँ।
अभी ठीक हो गया ना?
हाँ जी, अब ठीक हो गया।
हाँ, वो पार्टिसिपेंट्स भी क्या क्या करते हैं ना, ढूंढ रहे थे, हम देख नहीं रहा था कोई विवेक कुमार।
अरे भैया, ये तो मेल भी नहीं जा रहा है गुरुजी को। ऐसे सेंड दबाने से नहीं जाएगा।
लास्ट प्रेजेंटेशन है।
अरे अमित, तुम दोबारा से क्यों उसको डाउनलोड करने लगे, जो अपलोड करने लगे? जो मुझे शेयर किए थे वो आगे बढ़ा देते, फॉरवर्ड कर देते। जो मुझे YouTube पे डालने के लिए शेयर किए थे वो फॉरवर्ड कर देते।
मैम वो गूगल ड्राइव के थ्रू था, वो डिलीट कर दिया मैंने वहां से।
पक्का गुरुजी का चेला है।
इस टीम पे आ गए भाई।
सर सोचा पीपीटी नहीं आ रहा।
कौन सा मोबाइल डाटा लियो यार, आजकल तो सब कहते हैं बहुत अच्छा अच्छा पैकेज आ रहा है।
BSNL तो नहीं है।
हो सकता है वही होगा भाई साहब, नहीं लगेगा।
हाँ।
आई होप कि सबने नंबर भेज दिया है उनको।
नीलम दी किसको भेजना है मेल
आ गया। अमित जी बोलने के लिए तो डाटा है ना।
एक्सपर्ट ग्रुप में ही।
बहुत सारी सर।
ठीक है।
सीधे रिजल्ट डिस्कशन पे भेजिए ना।
थैंक यू सर, थैंक यू जी सर। सर ये तो फिल्म प्रिपरेशन मैथोलॉजी है सॉल्यूशन कास्ट टेक्निक से। बेसिकली मैंने जो इसमें वर्कआउट किया वो चेंज इन कंडक्टिविटी है उसको एक्सप्लेन करने के लिए डिफरेंट थियोरेटिकल मॉडल अप्लाई किए। I use rice and roth model, Thurkan model, skirt and grid model, and green band model. So this is the formula for rice and roth model. The Elmore and West model. I have not used this one for the graphical one. Thurkan model based on the diffusion coefficients. Skirt and green model and green band model. So these two models are broadly depends upon the impedance spectroscopy data, and we calculated the concentration of charge carrier based on these three models. These all models to understand the change in conductivity based on the concentration. So this is the conductivity pattern for my system based on the different weight percent of C60 dispersed with PU NAI. And the pattern to change in to hikes in conductivity can be explained by the percolation model. But when we try to calculate the concentration of charge carriers based on the conductivity and implementing the Hölker model, this is the graph pattern. Carrier is correlated with the change in conductivity. Certain grid model is closely associated, while the green model has a small change in their values, maybe of the order of one order, well, change in one order, and this is what we have did. And further, I'm trying to get the calculation of concentration based on Rice and Roth model, and the two more models based on like. Hello.
Yes, you are audible.
Continue.
This is all about my theoretical work on the calculation part. Thank you very much, sir.
So that's all with the series of presentations. Thank you, experts. Thank you, participants. Madam, over to you. No, you remove. Yeah.
Okay. Thank you, ma'am. Good evening to all of you. It's my great pleasure and honor to summarize today's sessions and yesterday's sessions of this grand event. The conference began with a welcome by Professor Inumeda Principal of Mahila Mahavidyalaya, then addressed by Director Professor A.K. Tripathi and Dean Professor Matulika Agarwal, Institute of Science. Subsequently, we had wonderful inaugural address by Chief Guest Dr. N. Kalachalvi, then followed by a remarkable speech by our Rector Professor V.K. Sukla. In this 2 days conference, we had one keynote presentation, 4 plenary presentation, and 2 invited talks. All invited speakers are well expertise in theme of conference. Besides, we also had 54 oral presentation from young researchers across the country. This event brought together 100 participants, including faculty fraternity, as well as scientists and researchers. The speakers at the conference are uniquely placed to highlight the key themes of conference. The development of energy and device concept has becoming the emerging trend of challenges for all us. We had significant presentation from innovative speakers. They have highlighted ongoing research on batteries, solar cell, fuel cell, supercapacitor, and electrochemical studies. Invited speakers are provide the knowledge, engagement, and innovative of energy and device for future potential application. I'm sure that you have enjoyed today and yesterday's sessions and discussion. Before coming to close summary, I would like to thank Professor Neelam Srivastava, Professor Bhaskar Patashev, Professor Mr. Dr. A.K. Kankali, Dr. Andy Fanai, Dr. Mansi Kose, and Dr. Sonlata Singh for the successful completion of this conference. I also thank all committee members and students who tirelessly devoted their time and effort to prepare and organize this conference. I thank you for your participants. Once again, I thank all of you for kind cooperation. Thank you, ma'am.
Thank you very much. I would like to thank all of you for nice organization and very good presentations. I couldn't see all of them because of this different hours we have jet lag. So, but I have the opportunity to see some of them this morning, and I like very much. So I would like to thank once more to all of you for the organization and the presenters for their nice presentations. Thank you very much.
Thank you very much, and I think you've done very good job. Okay, and also including all the organizers and all talks are excellent. I think especially more focused conference on energy storage materials, including batteries, supercapacitor, solar cell. I think especially for the students, a lot of number already you've seen many good attendance also. I think it clearly indicate that talks are very useful, and keep do, and then thank you very much for your support and all the organizing team. Okay, thank you very much, madam. Thank you. Good luck.
Thank you. Thank you. Yeah, Abhimanyu Singh is here.
Yes, ma'am. Yes, ma'am. Yes, ma'am. I'm a MSc student. Yes, ma'am. Yes, ma'am. Personally, I'm very impressed with the efficiency of the organizers who planned the conference, especially the BHU team, and I really enjoyed my time at the conference, and I'm looking forward for the next year conference also. Mm, I didn't count the number of lectures that I attended. Yes, but overall it was very informative for me since I'm at the learning stage. So yeah.
Good, good, very good.
Pranam, and thank you so much. Actually, frankly speaking, after a long time, I'm on the conferences because we don't have the facilities here, funding problem like that, so many things. But this online program actually has given us lot of beneficiaries. Actually, we are very, very happy. I'm especially really thank you so much. I'm like a student. I'm learning, frankly speaking, because when you listen anything from others, it is a, you have the juice. So I'm learning. I'm just a listener. I'm also learning from everybody, not from the experts, from the students also. So thank you so much. Really, it is highly beneficial for us. Of course, India, Saudi Arabia, if you see, very, very far, but still we are enjoying. I'm really grateful to. I can see the faces. For me, I remember my old days, what we had in our 90s, during our PhDs, and then my RSC. So really, I'm very, very happy. मेरा तो दिल पागल है, मैं साफ साफ बता रहा हूँ. I'm very, very happy. Very, very happy.
Hello, may I? Good evening, everyone. Ma'am, just I want to say that first of all, every speaker was very eminent and they give a really very nice talk and informative one. Just ma'am, I want to say that in the for coming seminar or conferences, we would like to hear about some characterization based also, since they have done their work and that is being shown. We would also like to know or get some knowledge about few characterizations also. Yes, ma'am.
So then, can I say something else? Yeah, okay. So very thanks and I mean to the Professor Bhaskar, and I because I among all I actually
know Professor Bhaskar. And last time in 2019 also I joined the conference, and that was my first time when I met with Professor Bhaskar, and such a wow person. Or I always enjoy his wordings and his the way he carries on. So and Professor Neelam, about you. It's a wonderful. However you have setting from 8:30 to 9 o'clock. Amazingly you have done this. और आपका जो एक बोलते हैं आप जैसे वो एक डांटने से कम नहीं लगता है हर बार. So, so this is something which I really felt very connected. That's something very nice, and I hope that this will be the series which you are running on. नहीं वो कल जब yeah. नहीं वो आपका जो आपका तो स्टाइल में ही डांट है. No, that is fine. So then this I just wanted to say, and I enjoyed this whole. And see, I'm doing the theoretical and molecular simulations, and I really learned a lot of things about the experimental, physics, which the way the people have been showing their works. It was very good for me as a to look up this, because we never care about these lot of things, because when you are on a system, you just really feel good that okay, you designed something, you are getting some results, and you are happy to match it with some experimental data if it is available. Otherwise, you are happy, because in past simple calculations, always the papers are coming like that way. So in general, it was a good learning for me, and thanks again for this whole wonderful experience of 2 days. Thanks sir, and thanks ma'am, and thanks all.
I would like to say something. Ma'am, I would like to say something. And first of all, I'd like to thank you all of the organizing team who utilized this COVID time, and I highly appreciate all of them. And this conference is highly informative for me. And next month I will go Malaysia for my master degree, and I would like to collaborate. I would like to collaborate with BHU people in the coming year, hopefully. Thank you so much. Yes, ma'am. Yes, ma'am. Ma'am, right now I'm just completing my bachelor from Sharda University in physics. Mhm. Yes, ma'am. Thank you, ma'am. Thank you, ma'am.
I I guess I guess experts are taking time to give their score. So maybe we need to defer that for one day. There's only one.
We will do it immediately.
Huh?
So within 10 minutes. 10 minutes.
यार 9 बज गया.
नहीं हो जाएगा.
You sir. Yeah, there. Yeah, they are there. Huh? Rhea is continuously attending all. नहीं
नहीं होना तो चाहिए.
Yes. Yeah. I think. Neelam, now I am online. I think. Yeah. No. I think this is Neelam. Please do not say like this. I think this is a common platform where at least we are able to see in this COVID pandemic situation at least virtually, because now you all believe that we are just in cave, just saving for good health and wealth. Each one is doing these kind of things, but I think I must congratulate particularly you and your team that this during COVID pandemic situation especially, where we are getting, we means I am talking about researchers and scientists. Basically, they are got frustration. They want to say something in front of speakers and anybody, but the problem is where we need to collect. So you already organized this conference in a suitable time, I can say, because we want to collaborate, we want to discuss, we want to say our healthy researchers like Professor Paul Elka and many professors from abroad. And we are, of course, we want to discuss something which is ongoing, but maybe for better future perspective point of view, without discussion, without providing such a nice platform, it is not possible. So I am personally thankful to my seniors like you and many more. They are in queue, but I believe that it's just to provide not a platform to promote our young researcher. Because when I just told my BSc student, Tejas, who is in front of you, that there is a nice conference organized by Neelam Dee in Banaras Hindu University, without taking a second, they all agreed just to see their seniors, their nice discussion and everything. So I think this one is a very good step forward in this COVID pandemic situation. So I must congratulate you and your team.
Yes, thank you, Nilamdi. Yeah, so it's a good reunion of all the researchers, I think the very first thing, and see all the faces, after a long time, as PK Bhai is saying, because we all are just waiting to a platform where we can meet, and you provide such platform. And I'm very glad to see the next generation, as Bhaiya is saying, Tejas, Abhimanyu, and I can say that they are much better presenter than us.
Very correct. Very correct.
Yeah.
Very
Yeah,
correct.
the way they have presented, I think, and within the time constraint they have presented. And the very good thing which I see this time, that you have put all the presentation in the YouTube. That was a very great initiatives, because within 5 minutes you cannot judge okay, what they have done. But the experts can look the complete presentation during the YouTube, and they can just see that okay, what the presenter want to say that one. So it's a good initiative for the YouTube. And thanks again to all of the faces here, PK Bhaiya, Neelam Deep, morning with Dalvi sir, Bhaskar Bhattacharya, no need to take the name of him. It is good to see all of you. Thank you for providing this platform. Man, it's good. Good.
नहीं पांडे जी नहीं है.
Yes.
Okay, sorry, ma'am. Yeah, first of all, ma'am, I want to congratulate everyone, participants, organizing committee, you, Bhaskar sir, for this successful conference. And actually, ma'am, there is one problem with me. That was time. You should increase the time for the next conference. 5 minutes are very less now. Yeah, that's that YouTube is great.
हाँ नहीं वो आपके बोलने में नहीं आपके बोलने में डांटना ही है
सबको उस डांट से डर लग रहा था मैम.
मैं तो कल ये देख रहा था प्रोफेसर भास्कर वाज आल्सो सेड दिस कि आप धमकी दे रहे हो तो मैं कहा भाई जो
It's I think it's a good learning for all
it
of
was a
us.
nice your way is very dominating
She is senior to all of us, so she can do it. Professor Pandey just left. He phoned me because
How
it
he
is
can
already
without
9:18,
permission.
so he left. Oh.
Sorry.
Yep. Okay. मुझे फॉर्मली कुछ बात करनी है लोगों से. If I can search out students in this list, our students, even if Shreya, if you are there, not yet. To all participants, I would like to mention that these students, undergraduate PhD third year students, they did excellent job starting from the preparation of the conference. Because currently only 2 of our research scholars are coming offline activities. So the BSc third year students, if I can start counting, better I should not. If I miss any name, they will feel it hard. But they did it. Yeah, Professor Paulika is saying that she has to leave. Okay. Bye bye. मेरे ख्याल से हम लोग इसको क्लोज करें, अगर, क्योंकि पीयूष जी के पास कितना आया, सबका आया नहीं है अभी तक. कल उसको भेज दिया जाएगा.
That's good. That's good. Inaugural.
Yes.
Thank you, ma'am.
Thank you, ma'am.
थैंक यू सो मच. मैं भेज भी दिया जस्ट.